check, check test, check, 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 check test, check. Copy there.
Dear professors, delegates, a very warm good morning. Today we are in the third day of the 24th International Shock Interaction Symposium, SIS-2022. So we begin with the technical session chaired by Dr. Srisha Rao from IISc Bangalore. Sir, I welcome you here. Please introduce the speakers and begin the session.
Welcome one and all. I think, yeah, third day of the conference. Yeah. So today, the first session, we have about 5 presentations, and we'll start with Sumesh Babu. So the co-authors are Manoj, PJ, Leo AG, Nikhil Jacob, and B. Lijo. And it's on numerical investigation of the effect of unsteady generator conditions on supersonic ejector performance. So Sumesh Babu. It's not working. Full mode. Okay.
Good morning to all.
Sir, PPT is
myself
not
is
seen on the
Sumesh
Zoom
Babu
window,
CV
sir.
from Government Engineering College, Thrissur. My topic is
Sir,
numerical
PPT is
investigation
not shown on the Zoom, sir.
steady generator pressure on supersonic ejector performance. This work was done under the guidance of Professor V. Lijo. This is the outline. Ejector refrigeration system. This is the introduction. Ejector refrigeration system. We are making use of supersonic ejector. Supersonic ejector. We are replacing we are replacing a conventional compressor by a supersonic ejector, having the advantage that there is no moving parts. And also, the major advantage is that we can make use of waste heat or solar energy for the generation of high pressure primary fluid. Here, this primary fluid MP is from the generator, and the secondary fluid is from second MS is from the evaporator. Compression can be done in the by the shock assisted compression or with the help of subsonic diffuser. The major parameter, one of the major parameter for the performance evaluation is entrainment ratio, which is the ratio of MS by MP. This is the typical characteristics of entrainment ratio, which moves linearly, almost linearly with the generator pressure. So in the subcritical mode, we have this is the subcritical mode. This entrainment increases almost linearly with primary pressure. In that mode, only the primary fluid is chocked condition, and it reaches to a maximum value of entrainment at a generator pressure called critical generator pressure. After that region, it is in the critical mode where both the primary and secondary fluid is in the chocked position. Or in this chocked position is not common in all the supersonic ejector. It depends on the operating conditions and the geometry. The secondary choking phenomena was introduced by Fabry, but that is visualized by Lamberts by the numerical investigation in the steady state analysis with the help of a sonic line contour, which is introduced by Bartovics. But that study was steady state only. But in most of the engineering applications, here the steady state is not possible. The waste heat or solar energy is almost transient in nature, which initiated the transient analysis of the study. We are motivated from this, and we have conducted a transient analysis based on this. This is the computational domain we have taken from the experiment of Gilbert and Hill, where we have the pressure, velocity, and temperature distribution inside the domain. So we have done this 2D transient implicit analysis using this K omega SST model. And we have increased the pressure of primary flow or generator pressure from 9 bar to 11 bar in 40 milliseconds. This is the numerical validation. We have done SST K omega, RSM, and K epsilon, and we got a better match for SST K omega and RSM model. We have choose SST K omega for the better computation stability. Coming to the result part, initially we have done a steady state analysis up to the steady state analysis by keeping the primary pressure 9, and we have increased the pressure from 9 to 11 bar in 40 milliseconds. So at the pressure, primary pressure of 9.92 bar, we have seen first Fabry choke, and interestingly, another Fabry choke also is visible on the pressure of 10.09 bar. This is the contour. So first one, this is the unchoked condition of 9 bar, and at the formation of first Fabry choke, we have at the time 18 millisecond, we have a linear the lateral growth of that sonic line. This is a sonic line, and this sonic line is growth in the lateral direction. At the second Fabry choke position, the growth is actually increased, and another second Fabry is also in that region. This is the sonic line development during the analysis, and here this primary jet grows and the under expansion growth, and at the time t equal to 18.4 millisecond, this growth has been increased, and the area available for the secondary flow is minimized, and the secondary flows get accelerated and reaches the sonic condition at a particular position of mixing deck. So we have plotted the Mach number versus mixing duct height at that location, at that fabric choke location. We can see that at 17 point, the previous slide, this is 17 millisecond, there is no fabric choke is visible. Here, that is a pink line, and this is, we have not achieved the secondary Mach number reaches to unity. At 18.4 millisecond, that secondary, this is the mixing duct height, this is the top portion, and the secondary flow velocity increases to sonic condition. We have again increased the pressure. We can see, we have seen that there is another peak has been developed in the downstream of secondary or downstream of first fabric position. But that this position is not altered, and this primary jet growth is stabilized due to fabric. In the formation of first fabric, this primary jet growth is stabilized, and the mass flow rate is actually maximized at that position. During the formation of second fabric, there is no effect on this entrainment, and the entrainment is actually decreased due to the lowering of suction pressure created due to the enhancement of primary pressure. This is the entrainment history during the analysis. So during the formation of first fabric choke, this entrainment reaches to the maximum value, and then again decreases on with the enhancement of generator pressure. So the desired condition for the ejector to be operation to be done at the critical pressure. This is the corresponding wall pressure and pressure contour of this section. So this is the unchoked condition of the beginning, and during the formation of first fabric, the pressure here it is reduced. The pressure is dropped here. This is the first fabric blue line, the dotted blue line, that is reduced to the critical choking limit, and then again increases. And here you can see that this is again the pressure increases, and this first shock cell is moved from here to here. This is first shock cell moves to here, and again we increase the pressure. This low pressure region increases. This is moving forward, and the first shock cell is actually appeared here only, and the low pressure is prevailed here, and we can see this again undergo supersonic condition here. We have plotted the shock, and during when t equal to 0, there is only regular reflections are here, and during the formation of fabric, there is a Mach reflection also seen from here. So RR to MR transition also taken place during the formation of fabric. So this is the conclusion. So the fabric choke is the desired operating condition position. The occurrence of fabric choke can be considered as an operating position. Then sonic line can be used to predict the fabric choke numerical analysis. Thank you.
Yeah, questions? Questions? Let me ask you some questions. Firstly, fabric choking, why do you call the second point as fabric choking? The first point is called fabric choking, which is more or less standard. But the second point is also visible. I mean, it's been shown in many studies, basically numerical studies. In experimental studies, you won't be able to capture it much. But numerical studies have shown, once the uh, pressure, it actually goes up and down until it reaches subsonic conditions. So you are bound to expect it. It's not a surprise. Uh, but why you specifically chose to call it as a second Fabry choking? Because what I would have expected when I saw second Fabry choking is you're probably going from Fabry choke, somehow it is unchoking, and then you are coming back to choke conditions. But once choking happens in the first case, thereafter your mass flow doesn't change, right? Will it, unless you change secondary generator conditions? Hmm? If secondary generator condition, I mean the secondary flow conditions, that is, yeah. Mm. But nice simulations. Okay. Right. And the other one is the max term that you observe, it's in secondary flow, right? It's not in the primary flow.
No, that's in the secondary flow.
Yeah. So that's a different shock system, right?
Yeah, there's another.
Yeah.
That is not common in the
Yeah, because in the first case,
first case.
the shock is bounded within the mixing area. And once this it starts becoming supersonic on the secondary flow, yeah, only then. So that's a different shock system altogether, isn't it? Yeah, uh, good work. You can check. There are some new work on this by the people Bartsowitz and Lambert's group. They have given a different choking theory compared to Fabry. Fabry has some issues.
They are the compound.
Yeah, you're aware of it. Good. Yeah, thank you. Yeah. Next we have Nikita Reddy, and she's going to talk on computational study on inlet unstart prediction of scramjet, and the work is done along with Gopal Krishna Narayan. Okay.
Good morning, everyone. I'm Nikita. I'm an undergraduate student at MS Ramaya University of Applied Sciences. Today, I'll be talking about numerical investigation on unstart prediction of scramjet inlet. This work was done under the supervision of Dr. Gopal Krishna. The outline of the presentation goes like, firstly, I'll be introducing the basic topic, then the history of the unstart, geometry and free stream conditions that I've used for simulating, grid details, solution methodology adopted, discussion of the results, and then the conclusions. Working in the aerospace field, it is always fascinating to know about hypersonic and supersonic vehicles. Scramjet being one of such vehicles, it is always subjected to low atmospheric pressures and low temperatures when flying at greater altitudes and greater Mach numbers. Although scramjet has many advantages, but then the working of the scramjet has been limited due to the challenges being faced by the scramjet. One of the challenges that is being faced is unstart condition. As seen here, the scramjet has three basic components: inlet, combustor, and nozzle part. But there exists a duct that connects the inlet part and the combustor part of the scramjet, in which oblique shock reflections are formed. That is termed as a start condition of the scramjet. Scramjet engines are extensively being studied from 1930s. What is unstart basically? The raise in the pressure in the combustion chamber leads to the oblique shock reflections expulsion out of the inlet part, which causes engine failure completely. So that is unstart. It's basically disturbances in combustion leads to transient process termed as unstart. Few research works have been done on unstart condition, but prominent works were done by Rodi and MKK Devraj. They conducted experiments on an intake that had a movable cowl and a movable flap. Movable flap was kept to mimic the back pressure of the combustion chamber. Along with them, Wagner also studied the effect of back pressure on the starting characteristics of an inlet isolator model by deflecting the flap at the end of the isolator. So this is the geometry that I have used. It was taken from Wagner's paper on which the experimental investigation was done. It has a 6-degree compression ramp followed by 242.3 mm length of isolator. It has the flap at x by h is equal to 12.9. As seen here, P1, P2 till P7 are the pressure sensor locations from which the data has been obtained. And numerical investigation was done with respect to the data that has been obtained from the pressure sensors. The free stream conditions that I have used to simulate the model are Mach number 4.9, total pressure 2.5 megapascal with a total temperature of 333 Kelvin. The wall temperature was kept constant. Here you can see the pressure sensor locations. The grid details. Grids were generated using commercially available software. The coarse mesh was generated using 2.26 million cells and medium mesh using 7.97 million cells and fine mesh using 11.98 million cells. The grid independent study was done. The first layer spacing was maintained at 10 microns to get a uniform Y place throughout the wall boundary. The solution methodology that was adopted, finite volume method was used and ANSYS fluent solver was used. It was done under implicit formulation and AUSM implicit flux compression was used. Sutherland viscosity model and 2 turbulence models were used, Rance-based Spelater-Maris model and detached eddy simulations. Coming to the results and discussions part, here you see the Schlieren flow visualization for the start condition of the scramjet. This was done by Wagner, and these are the contours, pressure contour obtained for the Rance-based Spelater-Maris model and pressure contour obtained for DES model. As you see, the shock locations wherever in the experiment are matching with the shock locations in the contours as well. There is no much difference between the Rance-based SA model and DES model because there are no eddies formation because the flap angle is kept at 0 degrees. So the data surface pressure distribution comparison between Rance-based SA model and DES model. At pressure port 3, there is a raise in the pressure due to the separation strong separation bubble sitting over here. So there is a raise in pressure. So there is a raise in the pressure at pressure sensor 3, whereas the raise in the pressure at P6 is observed in the experiment due to the shock that was coming from flap. As seen, the experimental data and the simulated data gave good agreement with the results. This was the grid independent study. After doing the grid independent study, medium mesh was chosen. Unstart observed for a flap deflection of 20 degrees and 28 degrees. When the flap was deflected to 20 degrees, this was the unstart. These are the pressure fluctuations that we have observed. And it was ran for 18 milliseconds. This is Rance model, and that was DES. Interestingly, we have observed that the raise in the pressures at P7 was earlier when DES was adopted, whereas the raise in the pressure at P7 port was observed at 2 milliseconds. Here it was observed at 0.75 milliseconds. There is a difference of almost 1.25 milliseconds. And as you see that there is a raise in the pressure at P3 pressure sensor location 3 because there is a strong separation bubble over there. So there is a raise in the pressure there. And the pressure ratios were decreased when DES model was adopted. So this is for 28 degrees. When the flap was deflected to 28 degrees, As you see, the pressure ratios increased and the unstart happened very soon. Not very soon, although at 1.75 milliseconds, the unstart shock system started propagating upstream from 1.75 millisecond when flap was deflected to 28 degrees. Whereas when flap was deflected to 20 degrees, the unstart shock system started propagating upstream from 2 milliseconds. This is a streamline flow visualization. At t is equal to 1, flow time is equal to 1 millisecond, the unstart shock system was seen here. From t is equal to 1 millisecond to 3.6 millisecond, there is a strong boundary layer flow started separating and the isolator sealing flow started separating and separation bubbles are seen. From t is equal to 3.6 millisecond to 4.5 millisecond, these started growing. The separation bubbles started growing and it started, the unstart shock system started moving further upstream. From t is equal to 4.5 millisecond to 8.2 millisecond, it is seen that the unstart shock system completely propagated towards the inlet part of the scramjet, and there are no separation bubbles seen in the isolator part. So this flow is entirely subsonic now. From t is equal to 8.2 milliseconds to t is equal to, it's actually 13 milliseconds. It is wrong here. So from t is equal to 8.2 millisecond to 13 millisecond, the oblique shock that was formed during the start condition was completely detached and a bow shock was formed. So for different flap locations, when flap locations are changed, initially the flap was kept at 12.9. Now the flap locations are changed. The flap location is at x by h is equal to 10 here, and the flap location is at x by h is equal to 15 over here. The respective pressure fluctuations data are this. So for the similar flow times of 1.2 millisecond, the unstart shock system almost propagated is at the inlet tip now. So here, but still for the similar flow time, the unstart shock system is still propagating towards the inlet. So as the flap location is reduced from x by h is equal to 12.9 to x by h is equal to 10. So the unstart shock system also propagated earlier. So unstart was seen early. Whereas for x by h, when the flap was kept at x by h is equal to 10, the pressure raise was abnormal due to the strong shocks. I'd like to show a small video. This is how the pressure
You can play it without going to full screen. It is playing there. Yeah, just play it over here. You go to slide 13. Yeah, and just play it over there. Yeah.
I would like to show how pressure contour varies with unstart. This is how the Mach counter varies. Coming to the conclusions part. So for the start condition, RANS-based SI model and DES model almost displayed the similar results. And as the flap angle is deflected higher, the unstart was earlier. And in order to know the effect of the length of the isolator, we had to change the flap locations from x by h is equal to 12.9 to x by h is equal to 10 and x by h is equal to 15. That is indirectly we are increasing and decreasing the isolator lengths. So as the unstart was observed, initially there was an oblique shock that was formed during the start condition. And as the unstart shock system propagated towards the inlet, there is a bow shock formation that causes a subsonic. This is a subsonic flow in the inlet and isolator part. So this leads to the engine failure. The pressure ratios were comparatively low when DES model was adopted. These are the references that I have used. Thank you.
Thank you. Questions?
When you're doing the simulation, what is the starting condition? It looked like in the video, it was all uniform flow at the beginning.
This was the start condition, sir. Actually, when the
No,
flap,
not that. When the video began, right?
Yeah.
It started with some flow in the duct. Is there a flow in the duct or there is no flow in the duct right now?
no, sir. So
There is no flow in the
here
duct.
we have unstart shock system. Wait, I'll show the Mach counter. This is how the flow looks like in the duct.
Okay. And
So
at
there
this
is a flow.
point-
There is a flow. So we have because the flap was deflected because there is a certain deflection in the flap. There is an unstart shock system that had developed at the end of the flap, at the end of the isolator, wherever the flap was located.
Just pay attention. What professor is asking you. This is an unsteady simulation, right? So at t equal to 0,
T is equal to 0.
what was your initial condition?
That is, initial condition was the start condition itself.
So this particular situation is the start condition. From
unstart-
here, you
but
just change the grid. Is it? What did you do to get to that new
Yeah.
status?
Flap was deflected to 20 degrees. So
So the previous case was 18 degrees or something.
28 degrees. That was 28 degrees. When there was no flap deflection, we had a oblique shock reflections in the isolator duct. So when the flap was deflected to 20 degrees, there is a flow, but then here because of the flap, the shock that comes from the flap, and there is a third reflection towards the isolator ceiling wall, the flow has been separated there. That shock and this shock, both of them combine to form an unstart shock system. So this starts propagating.
So the question is, did you gradually move the flap in, or was it like from 0 degrees, just suddenly it became 28 degrees?
No, so there was no gradual movement. It's not dynamically moved.
Your
We just,
flow field that was at 0 degree flap
Yeah.
condition.
Ah.
From there, you just superimposed the new wall in the flow
yes,
and then studied what is happening.
yes.
That's why the shock structure is moving very suddenly, right?
Yes, sir.
So in real life, that won't happen.
In real life, that won't happen because actually, the unstart was seen at 28 degrees from the experiment. We just, with a plus or minus 3 degrees uncertainty, we just wanted to check for 20 degrees what is happening. So for 20 degrees itself, the unstart took place.
Yeah, that's because you are having a sudden change.
Sudden
That
change.
sudden
Yes.
change will send out a shock out suddenly.
Yes.
That could also cause. Okay, thank you.
Could you please show the Wagner geometry? So these transducers were mounted on the bottom wall of the wind tunnel.
Yeah, floor.
Wagner reported, I don't remember the exact, a thick boundary layer, around 10 millimeter height
Mm.
at the entrance.
Yes.
Did you account for that in your simulation? A thick boundary layer was seen.
Yes, yes, yes.
Did you account for that? At the inlet, it is around 5, Mach 5.
Huh.
The boundary layer thickness he measured was around 10 mm. It's
Uh,
reported that a thick boundary layer is formed. It's
Yes.
hypersonic. It's a long floor of the wind tunnel. So how did you account for that thick boundary layer?
No, we had a boundary layer of 1 mm thickness
From where?
from the wall itself. That is what I have told.
A long wall
Yes.
of the wind tunnel. And he reported at the inlet, the thickness is around 10 millimeter.
It's okay.
So it is sufficient to cause separation.
Yeah, this one is fine to cause a separation. We have already seen the
No,
separation.
what professor is mentioning is, if you're trying to look at your numerical results in comparison to what Wagner had done, you would also have to look at getting at least their boundary layer thicknesses right. Okay, so did you impose? You can impose. It's a numerical study, so you can impose a boundary layer at the inlet. Give a velocity profile, which is similar to what was observed by Wagner, since he has given you the results. I think that's what you were
Maybe
trying
she
to
has
say.
given a uniform inlet at the entrance.
Yeah. So
But actually it is a thick boundary layer at the inlet. So you can account for that.
Okay, okay.
It is
So,
not a uniform flow at the inlet.
yeah, it's a suggestion to
Oh,
improve
okay.
your results.
Thank you.
Okay. Okay, so if you go to your comparison between RANS and DES, you seem to say these are the same pressures, is it? Why
Almost
do the contours
Similar,
look different?
it's almost same. It's just the. Yeah.
Because your plot seems, I think you just have to, just pay attention to these finer details, because your plot seems to say that they are reasonably close,
The contours are
but the contour seems to say they're different.
no, because it was maybe because it was different color adopted using that. maybe.
Just pay attention to these
Okay, so
details.
okay. But
Okay,
the
good.
surface pressure distributions are almost
Yeah,
like
this is
it's
fine,
same.
this is
They're
fine.
almost overlapping.
Okay. Thank you.
Thank you.
Okay, now we have the third talk, and this is by Manoj PJ, Sumesh Babu, Leo AJ, Nikhil Jacob, and Billy Joe. It's on numerical study of Fabry choking assisted secondary flow bypass to enhance the entrainment of a supersonic ejector.
Slide 20.
Good morning, all of you. Myself is Manoj PJ from Government Engineering College, Thrissur. I'm working under the supervision of Dr. Lijo. My topic is numerical study of Fabry choking assisted secondary flow bypass to enhance the entrainment of a supersonic ejector. Outline, introduction, operating modes of ejector, Fabry choke, literature review, proposed geometrical modification, results and discussion, and conclusions. Supersonic ejectors. Supersonic ejectors can function as a compressor, vacuum pump, or refrigerator. The absence of moving parts with zero maintenance, easy of manufacture, and cost effectiveness are the reasons for widespread use of supersonic ejectors in many engineering applications. Ejector basically consists of a converging diverging nozzle. A primary flow at high pressure is supplied through converging diverging nozzle. There is a outer envelope. It's having three parts. One is the suction chamber, constant area section, and diffuser section. The ejector in a refrigeration system actually replaces the compressor part of a vapor compression refrigeration system. The primary flow at high pressure expands through the converging diverging nozzle, and it forms a hypothetical aerodynamic throat in the constant area section. That will create a low pressure that will draw the secondary flow from this bottom path, and that will flow like this, like the green arrow. As the secondary flow happens, the secondary fluid gets evaporated, and that leads to refrigeration effects. This primary flow and secondary flow mix in the mixing chamber in the constant area sections. Further, it moves to the diffuser, there it gets compressed, and further going to the condenser side. Normally, the primary flow gets choked at the throat portion. Then it will form a hypothetical aerodynamic throat, and that will create a secondary choking area in this region. That is known as Fabry choke. Fabry first find out this particular, observe this particular choking effect, Fabry choking. So in this particular condition, we'll call it as double choked condition. First choking happens in the throat portion, and second choking happens in this particular hypothetical aerodynamic throat. The operating modes of ejector. The ejector can work in three different modes. One is the critical mode, subcritical mode, backflow mode. Backflow mode is malfunctioning operation mode. That is a backflow mode. Critical mode, we are interested with critical mode. Critical mode means there will be double choking. As I already explained, first choking happens at the throat, and second choking happens at the Fabry choke. So in this particular case, we will get maximum entrainment ratio. And entrainment ratio is the ratio of mass flow rate of secondary flow to mass flow rate of primary flow. That actually we are interested with entrainment ratio in refrigeration. As the entrainment ratio increases, refrigeration effect gets enhanced. So maximum entrainment ratio happens in the critical mode. If you further increase the condenser pressure, there will be single choking. That is known as subcritical mode. Only choking happens in the throat. No choking, no Fabry choking in this particular middle mode or subcritical mode. So we are interested with critical mode. There will be happening double choking or Fabry choked conditions, where we'll get maximum entrainment and maximum refrigeration effects. Literature review. Many scientists are tried to improve the entrainment ratio. So entrainment ratio can be improved either by increasing the secondary flow, mass flow rate, or decreasing the primary flow rate, mass flow rate, for the same secondary flow. So the first reference, Ini et al. Bypass ejector with an annular cavity on the nozzle. So they try to improve the nozzle for reducing the primary mass flow rate and to increase the entrainment ratio. The second reference, Chin et al., a novel ejector with a bypass to enhance the performance. There, they tried to improve the secondary mass flow rate by additionally there is a giving a bypass, but the bypass is given in the diffuser area. If you give even though there is an increase in the secondary mass flow rate, if you give the bypass to the diffuser section, that will affect the compression effect of the ejector. So ejector is also working as a compressor. The third reference, Chin et al., impact of operational and geometrical factors on geometrical performance with bypass. Again, they provided a bypass to the diffuser sections. The fourth reference, Bixing Chin et al. Did a numerical assessment of ejector performance enhancement by means of 2 bypass inlets. So they have given an additional bypass for the secondary flow. That also you can see it is provided to the diffuser section. That will affect the compression effect of the ejector. The fifth reference, Jacob Bodies et al. Did a experiment performance improvement of R7744 carbon dioxide 2-phase ejector with an implemented suction nozzle bypass. They also tried to improve the secondary mass flow rate by additional bypass lines. This additional bypass line opens to the diffuser section again. None of the study conducted or considered the Fabry effect of the ejector. They make use of Fabry choking. As I already mentioned, it is a secondary choking happening in the mixing sections. Lamberts et al. Did numerical experiment evidence of Fabry choking in supersonic ejectors. They investigated Fabry choke numerically and experimentally. The first effect of Fabry was observed by Fabry supersonic air ejectors. So Lamberts did experiment further investigations on the Fabry chokes. So none of this particular work, previous work, secondary flow bypass is provided near the all the works, the secondary bypass provided at the diffuser sections. Fabry choke effects are not considered in none of the studies. Actually, Fabry choke regions is the lowest pressure regions in the ejector, and if you give the bypass to the Fabry choke area, you will get better enhancement in the secondary mass flow rate. This paper proposes novel geometrical modifications called Fabry choke assisted secondary flow bypass that overcome the mass flow restrictions imposed by Fabry choke. So Fabry choke actually restrict the secondary mass flow rate. That will limit the secondary mass flow rate. Further enhancement is not possible. So we have tried to overcome these restrictions by providing a bypass to the Fabry choke regions. So that will bypass the secondary flow, that will overcome the mass restriction, mass limit of imposed by Fabry chokes. So this is the computational domain methodology. We have adopted domain from Gilbert's baseline geometry adopted on Gilbert and Gills. We have did the modifications on the geometry for getting the Fabry choke conditions. We have changed the area ratio. We have used 2D study analysis. We have assumed dry air Sutherland viscosity models, K omega SST turbulence model, grid 0.3 million control volumes. Primary flow, we are assumed pressure inlet. Secondary flow, we are assumed pressure inlet. Outlet is pressure inlet, pressure outlet. And we are assumed symmetric boundary conditions, walls conditions, adiabatic, no slip conditions we are assuming. So this is the numerical validations. We did the geometrical validations of Gilbert's. We have tried with 3 different models, SST, K omega, RSM, and KE models. Both SST, K omega, and RSM is very close to the experimental results, but RSM is computationally more expensive, so we'll adopted SST, K omega. This is the velocity variations at a distance of x equal to 10.5 inch from the nozzle, and this is the temperature variations. Also, we have used 3 different models. One is the SST, K omega, RSM, and KE models. Both SST, K omega, and RSM matches with the experimental results, but we are adopted SST, K omega because of the RSM is computationally more intensive. And this is the ball static pressure variations along the length of the ejector. So that also matches with the SST K omega model. So finally, we are selected SST K omega models for our analysis. Bypass is provided. We tried with two different locations. We have the first choking here, second fabric choke happens here, again it is choked here. So first we tried the bypass fabric choke happens at 70 mm from the nozzle. So first we provided the bypass exactly at the fabric choked regions. Then we have tried second location as 85 mm from the nozzle, that is midway between fabric choke and third choking region. So we have tried the entrainment ratio in two different locations, and we also tried with the different shapes of bypass. One is type at the end, we are used converging diverging nozzle, and constant area nozzle exit. Three different shapes here are used. So Mach number variation with bypass closed and open. At 85 mm, second position, just shown one graph. So here 85 mm, we have provided the bypass. At 85 mm, red line shows the bypass open, blue line shows the bypass closed or without bypass. So we can see a sudden depression in the Mach number at the region of bypass openings. This clearly indicates a oblique shock happens in the particular bypass opening regions. And we are analyzed the improvement in entrainment ratio at two different locations and three different configuration shapes. We have found that maximum entrainment we have observed in 7.7% enhancement in entrainment ratio at 85 mm from the nozzle position and converging divergent shape of the bypass. This is the sling shock structure with and without bypass. You can see when the bypass is closed, there is a Mach reflected shocks here. When it's opened, that particular bypass, Mach reflection become regular reflections that eliminate the fabric choke restrictions in this particular flow. This is a graph when the bypass is given at 70 mm. The same graph when we open the bypass at 85 mm from the nozzle. This is without bypass, or when the bypass is closed, there is a Mach reflection conduce here. That Mach reflection conduce is eliminated, become regular reflection shocks when the bypass is open. This is the graph Mach conduce with overlaid sonic lines. We are used to find out the exact fabric choked conditions, locations in the constant area depth. This is the sonic lines. Sonic line clearly shows the choking positions. So we have provided the bypass accordingly. So sonic lines shows that fabric choke restrictions are removed by providing this particular bypass. So this is at 70 mm, and the same graph, similar graph we are used for with and without bypass. When the bypass is closed, you can see the sonic lines. There are two positions. You can see the choking, and when the bypass is open, the effect of fabric choking or restrictions of fabric choking is eliminated, and the flow is expanded through this particular constant area sections. To conclusion, present study numerically investigate a method by which mass flow restrictions caused by choking of secondary flow can be eliminated. It was found that there is a sudden decrease in the static pressure in the region where fabric choke occurs. The low pressure created due to fabric choke is utilized to drive the secondary flow using bypass. Various geometrical configurations were tried for bypass depth and geometry. The main objectives of the present effort is to optimize the location of mass injections to maximize entrainment ratio and the shape of the bypass depth and on ejector refrigeration. The maximum entrainment ratio observed observed is 7.7% with bypass provided at 85 mm midway between first and secondary choking with a converging diverging exit. Secondary mass injection by bypass duct post MAC reflection to regular reflections type of shock transformations, and hence it eliminates the restrictions of Fabry choke conditions. So these are my reference. Thank you.
Yeah, the work is open for questions.
I've never seen this kind of study before. So anyways, I just learned about Fabry choking. Anyway, but when you are trying to change the primary jet from going up and blocking the secondary jet, that's what you call Fabry choking, right?
Yeah.
So you're pushing the primary jet down by sending another supersonic jet at that location.
Okay.
But won't the secondary flow be blocked by that jet?
No, that is not happening. Actually, this the primary flow make a hypothetical aerodynamic throat here. That actually, because of the throat position, that restrict the mass flow rate. So further, we want to further enhancement is not possible with this particular throat. So somehow we want to eliminate this particular throat restrictions, second Fabry choke restrictions. For that, we are provided secondary chokes. So why we provided here is it is the lowest pressure area. So that will draw additional secondary mass through the line, through the secondary chamber. That won't restrict the primary flow. That won't make any restrictions. That will draw only.
No, I'm talking about restrictions on the secondary.
Secondary.
The new injected jet is going to occupy some space.
Okay.
And so that will block the secondary flow.
From the numerical study, we are not observed any, always improved the secondary mass flow rate, even though with this secondary bypass open. So that is not making any restrictions or limits for the secondary mass flow rate.
Possibly, the point is that you are taking the bypass from the secondary flow itself.
Yeah.
You are taking the bypass, right?
Yes.
From the secondary flow itself.
Yes. We are
So
taking
you're adding the same flow to the flow.
So in some
So
sense, you're
in some
giving
sense, it
from this
is,
side,
yeah,
you're
it
giving
is sort of increasing the.
and also helping pushing the jet down a little bit.
Yes.
Okay, have you tried some other shapes on that primary jet? Is it a 2D simulation or 3D?
2D simulation.
2D simulation. Okay, then
Yeah.
I'll talk to you later about that. Okay.
We have a question over the online platform. So, yeah, Pradeep, please ask your question.
Yes. May I know that what is the Mach number of the secondary from the jet? You have put CD nozzle there. So what is the Mach number of the secondary flow bypassing from this bypassing in the constant area section?
2.2.
And what is the primary nozzle Mach number at nozzle exit?
Select it. It is. Is 3.
Okay. What are the input parameters? Means the primary flow and secondary flow, inlet pressures and temperature.
Primary inlet, we have used 9 bar pressure.
Yes.
And
And
0.8 bar.
And secondary inlet.
0.8 bar.
Okay.
0.8.
And temperatures are same, right? Means atmospheric temperature, or you have used any heated air or whatever.
Pardon?
What about the temperatures of the primary and secondary flow at inlet?
Compression. You mean compression?
Temperature.
Temperature is 300 Kelvin.
Okay. Both temperatures are same, right? 300.
Both temperature we assume same 300 Kelvin.
So in your temperature plot, you have shown that temperature has increased to 312 degrees Celsius, 312 Kelvin. May I know why the temperature is increasing in the constant area section? Can you go to your temperature plot?
Do you have a temperature?
Temperature plot is not there.
No, you have section some 10 inches in the constant area section. You have plot temperature profile.
Well,
In I don't know the slide number, but it was there some slide where you have compare your experimental result with the experimental and these three different
dots are shown the experimental variation of temperature.
yeah. So here in this slide you shown your temperature increased to 320 degrees Celsius, 320 Kelvin somewhere.
Yeah, 320. Yeah, 320.
But
That is-
why temperature increased in this case?
That's a different conditions actually. That's a different condition. Experiment is conducted in different conditions. So we have taken only the
is there
geometry.
a total temperature difference between the primary and secondary flow here? In this condition? It's a different condition?
Different.
It's heated. So Pradeep, the flow is heated.
Or actually just it mentioned that both are at 300. Oh, no issues. If it's heated, then it has to be increased. Oh, thank you.
This is a different simulation for validation where it has been heated. So I think
Oh,
that.
thank you.
Any more questions? Okay, just one quick question. Actually, your when you put the bypass,
Yes.
Your flow choking just changes to another location from your results. So why do you say that the Fabry choking has disappeared? Your sonic line is going to the wall
Yes.
at a different location.
The choking is actually happening after the secondary.
Yeah, but
bypass.
it is still in the same constant area duct.
But actually that is improved the entrainment ratio.
Yeah,
The
because
results shows
you're
like-
having another flow. I
Yes.
mean, another area. So if I had just to tell you, if I had instead of putting that bypass, let's say that bypass, I had removed that and made the area slightly higher, I would have got the same effect.
So actually, Fabry choked condition gives the maximum entrainment. With that conditions, actually, we are trying to improve further.
No, my question is, do you want Fabry choking or don't you want? I mean, you don't want it. Then you can design the ejector for not having Fabry choking condition.
Firstly, we actually made the flow Fabry choke.
Yeah, no, I understood what my question is.
Mm.
What is your see?
Actually,
This is
finally-
a designer's choice, right? Whether I
Yes.
choose to operate in Fabry choking or I do not choose to, and I can make the change accordingly. So, what is the need?
Actually, final aim is to improve the entrainment. We don't want the Fabry choke or no Fabry choke, but it is observed that Fabry choke condition gives the maximum entrainment
Mm.
as per the studies.
Mm.
With that conditions, we are trying to improve that. If it is
Mm.
not Fabry choke,
No,
That
that is
initially-
for a particular geometry. So
Yeah.
for a particular, area ratio of
Yeah.
your secondary flow, I mean, your mixing duct, you get a certain maximum. But if I change area, I will get more. I won't get Fabry choke, that's all.
the Fabry choke. So with that different area ratio,
You
Yeah.
understand because
yeah, if
So
you change the
ejector
area
is very
ratio,
tricky.
suddenly you won't get the Fabry choke conditions.
Yeah. So that's
So
what
in
I'm
that
trying to ask
condition-
you.
That entrainment get reduced.
No, not necessarily. You're changing, if I change the area slightly, for the
So area
same
change- area ratio-
primary jet condition, I'll get more entrainment.
Then we have to, I think.
No,
Yes,
I'm just asking you to think. This is a very nice work. Please don't mistake that. But I'm just trying to understand whether, because the sonic line just goes to another point. If I see
Yes.
from your
Yeah.
plots. So still the secondary flow is choked. And this is under fabric choking. You move the, can you understand the point?
yeah,
You have
yes,
just
yes.
moved the location of choking
Mm.
to a different point. That's all.
This locations.
Yeah,
Move
to
this
that location. So it is still under fabric choking.
Yeah, actually, if you provide, I think, one more bypass at the particular location, again, environment,
Yeah,
there's a chance to improve that.
that's yeah, it's okay.
We are
Thank
going
you.
to try that.
Thank you. Thank you. Yeah, yeah, just this. Okay. Thanks for the nice, interesting. Okay, so now now we have the fourth presentation. Leo AJ, Sumesh Babu, Manoj, Nikhil Jacob, and Rekha and Lijo. So this is numerical evaluation of the performance of supersonic exhaust diffuser with and without ejected mass.
Hello. Good morning to all. I am Leo AJ. I am a PhD scholar from Department of Mechanical Engineering from Government Engineering College, Thrissur. And today I am going to talk about my research topic, that is numerical evaluation of the performance of supersonic exhaust diffuser with and without ejected mass. And my co-author is my professor, Dr. V. Liju. The content of my presentation is the introduction, literature review, the research gap identified, and then objectives. And the computational geometry and boundary conditions are described, and the validation, results and discussion, conclusion, and references. First of all, you guys are already know that supersonic ejectors. Generally, we know that supersonic ejectors are simple mechanical components with generally perform mixing and recompression of two fluid streams. In HAT, high altitude test facility, high vacuum level in the secondary chamber is created by dragging mass from a closed secondary chamber in which the rocket engine is placed. That means the ejector is functioning as a vacuum pump. The rocket motors and jet aircraft engines use supersonic exhaust diffusers in HAT facilities for ground test since 1949. The SED, mainly the SED configurations are classified into two. That is, first one, that is constant area duct diffuser, and second one, that is second thought diffuser. And here my interest is on straight cylindrical duct diffuser. That is simple form of high altitude facility that consists of a straight cylindrical duct that is attached to a chamber surrounding the engine. The supersonic exhaust diffuser consists of the primary nozzle. The primary nozzle that is surrounded with, that is a vacuum chamber, that is followed by that is a straight diffuser. Here, we guys already know that the momentum of the engine exhaust is utilized to lower the nozzle back pressure, and the static pressure recovery in the diffuser is accomplished through momentum exchange that is caused by shock wave system and it is decelerated to the subsonic velocity. Here, the SCD, the two operating in two modes. That is first one, that is unstarted mode. That for unstarted mode, the primary jet is partially expanded to the diffuser mode. That means the shock trains does not fill the entire cross section of the deck, and consequently the vacuum chamber is not shielded the ambient condition. And second mode is that is a started mode. That means the primary jet is completely expanded to the diffuser mode. That means the branch shocks are fully established to isolate the vacuum chamber from the downstream ambient state. Here, we are concentrating on vacuum chamber attains its high vacuum state in started mode. The more interest we have considered on that is started mode. From the literature review, SCDs are often sized or designed for a particular rocket engine. They are not readily adaptable to accommodate engines of different size and provide only limited range of altitude simulation pressures can be done with the particular SCD. And the HAT attains the required vacuum by arresting the backflow from the atmosphere into the vacuum chamber. Hence, the controlling the backflow or recirculation bubble often results in the substantial performance improvement. The large improvements in SCD performances are reported by backflow controlling devices, such as orifice plate at the inlet of the SCD and backflow arrestor device in the vacuum chamber and nozzle lip thickness, etc. And here we concentrated on that is Arun Kumar sir paper. He's already studied in the vacuum ejector. The vacuum ejector that paper, it's clearly described that the vacuum ejector startup is associated with a gradual initial vacuum generation stage, which is followed by the rapid vacuum generation. And we have concentrating on we have the baseline geometry can take taken from the Arun Kumar sir paper. And the another good interesting idea that the Hale already experimentally investigated the ejector diffuser system with and without mass ejection and reported that when the mass ejected from the test cell, the low pressure is achieved. Okay, so the research gap. From the above literature review, it's clearly mentioned that by the means of mass ejection from the test cell, that is Hale already experimentally investigated at started condition. That means the low pressure already achieved. So from the inference of the literature review, the slow phase of initial vacuum generation is observed in SCD can be accelerated by mass ejection. To the best of our authors' knowledge, there are no detailed studies on the effect of mass ejection on the vacuum chamber pressure history. Okay, mass ejection can result in much lower vacuum chamber pressure that without altering the basic geometry of the HAT. Hence, the mass ejection with the mass ejection, HAT can simulate various altitude levels, thereby increasing its flexibility. Objective. The numerically here, we have done a numerical investigation on the effect of mass ejection on the starting transient of a supersonic ejector diffuser system. That can be done by two cases. First one, that is mass ejected in the started mode only. Then started mode means we have considered the fixed rocket engine pressure. That means no starter transient are considered. That is a steady state condition. That was done in rectangular ejector, steady state condition. And second case, we have considered the mass ejection during the rocket engine startup. That is rocket engine startup. That is means primary pressure ramps up. Primary pressure ramps up from around 1.5 bar to that is 5.6 bar. That was done in the numerical simulation was done in round ejector. Okay. Here the computational geometry. Here the baseline geometry was taken from Arun Kumar sir paper. Here the geometry clearly shows that the primary flow, which is surrounded with a vacuum chamber, and the vacuum chamber is followed with a diffuser. Here the inlet of the mass is ejected from the test chamber by vacuum, by jet pump. Okay. Here the simulation can be done at the steady state condition, and from the experiment itself, from the experiment, it clearly shows that the started condition at the primary pressure of 4.5 bar. So we have take stagnation pressure at 5 bar, and the mass is ejected from the test chamber. Mass is ejected from the test chamber by the jet pump. We have considered the 2D simulation, and the K omega SST is taken as a turbulence model, and back pressure is fixed, constant at 1 bar, and stagnation temperature is taken as constant as 300 Kelvin. The baseline is already discussed that the baseline geometry is taken from Arun Kumar's paper, and here we consider the two-dimensional steady state simulation were performed. Okay, from the experiment, it's clearly stated that HAT starting pressure for rectangular ejector, HAT starting pressure is 4.5 bar. Okay, so we have considered for the simulation, we have considered the primary stagnation pressure for the steady simulation is 5 bar. Okay, the computational mesh. Here we consider the structural quadrilateral cells, and here the coarse grid has about 50,000 cells, and medium grid has 1,10,000 cells, and then fine grid has 2,46,000 cells. No, there is no substantial differences with regard to the evolution of centerline Mach number with medium and fine grid. So the results present in this work for the medium grid set. Here the validation of rectangular ejector. The orange line which indicate the starting pressure of HAT for the experiment, that is taken from Arun Kumar's paper, and presently we are already conducted the numerical simulation on rectangular ejector, and we got starting pressure. The blue line which represent the starting pressure represent the present safety. From the numerical investigation, it is clearly described that the starting pressure is under predicted by code, because due to the low aspect ratio, and also there is a lot of end wall effects are predominant. So better match with the experiment may be achieved by that is a full scale 3D simulation. Okay. However, the agreement between the predicted chamber pressure PC and the external values provided a reasonable trend, and this validated model has been used to obtain the flow features. Here, this is the numerical simulation. There is a Mach contour of that is primary pressure that is taken as a 5 bar. That means the primary jet is fully expanded to the diffuser wall. From the experiment itself, it's clearly stated that from the 4.5 bar itself, the primary primary stagnation pressure is fully expanded. That is a started condition. So we have for the consideration, for the interest, we have take the primary operating pressure is 5 bar. After the started condition, we have use mass ejection from the test chamber. Okay. Here it is clearly stated that operating pressure 5 bar. It is clearly stated that the primary jet is fully expanded to the diffuser wall. And it is the two cases are investigated for the steady state simulation. First one, the second figure that is clearly shows that that is a jet pump which is attached to the test chamber. Jet pump which is attached to the test chamber, which is used to eject the mass from the test chamber. Here we consider only after the started condition mode only. you have already know that from the standard from the 4.5 bar, the stagnation pressure, primary stagnation pressure itself, the flow is flow is in started mode. So from the simulation, it's clearly stated that with the mass ejection, the mass ejection can be controlled by jet pump. So jet pump.
You have to speed up a little bit. You have less time. So you have to.
Oh,
you may have some 5 minutes, 3 to 4 minutes.
okay. With jet pump operating with 6 bar, the vacuum pressure PC is 64.6 kilopascal, and the jet pump operating with 8 bar, the vacuum pressure is 41 kilopascal. It's clearly stated that the vacuum performance is improved with a higher jet pump pressure. Okay. So without modifying the geometry of the HAT, the same facility can simulate the higher altitude with the aid of supplementary, that is jet pump. And this is a numerical Schlieren, that is the darker region represents the shocks, and lighter shade that is indicate the that is expansion phase. Here, when we reduce when the PC is reduced, the primary jet becomes more and more underexpanded, resulting in stronger shock and shock-induced boundary layer separation can be seen at the foot of the that is oblique shock. Okay, and we have already studied the unsteady simulation in round ejector, and that also we have studied from that. Okay, from that it's clearly seen that that is with the aid of mass ejection, the pressure, the PC, the vacuum chamber pressure is lowered. With the mass ejection, the test cell pressure is lowered from that is 0.2 bar to 0.15 bar, that is started pressure. That means 25% reduction in vacuum pressure can be achieved with the aid of mass ejection. So the mass ejection is capable of that is altering the entire vacuum pressure history. That means without the change of that is HAT facility or SAD, the lower pressure can be simulated. The conclusion, it clearly found that the mass ejection of about 1% of rocket engine flow from the test cell can result in significant reduction in the test cell pressure, around 25%. Then, moreover, the mass ejection from the test cell is capable of altering its entire vacuum chamber pressure evacuation history. Okay, thank you. These are the references, and thank you.
Yeah, there's time for one question.
Okay, so you have done it in 2D simulation.
Yeah.
right?
So rectangular ejector we have studied, that is 2D simulation. For the round ejector, we are going on that that is 3D, that is 2D, that is axisymmetric.
Yeah, but you cannot have an axisymmetric ejection system all around, right? Then that means the tube will just fly off.
Okay, that is mass flow outlet boundary conditions are used for axisymmetric round ejector. For round ejector, we have used the that is mass flow outlet boundary condition. That is from the test chamber itself, we have used a that is a outlet.
But you have to now put some particular holes at some point.
Oh, here. Geometry itself, it is clearly shown that that is a round ejector. I didn't describe that one. Here.
Okay. So that's
The
that
mass
model
ejection
is not
here.
done. So that's what is going to
So
decrease your efficiency.
I didn't describe that one. That
Okay, but
for-
that portion, whatever you're going to put holes on the sides, is what is going to change your efficiency. Currently, it looks like you have very high efficiency
yes.
in the 2D.
Yes.
When you go to 3D, it will come down because of that distribution of this mass into individual holes that comes out.
Okay.
Yeah. Anyways,
Thank you.
it's a good one. Thank you.
Thank you.
Thank you. We are short of time, so we'll have the next speaker, Sandeep Soman, Abhilash Suryan, a study on shock interactions in a linear aerospike nozzle.
Hello. Respected professors, all other delegates, warm good morning to one and all. Today I would like to present some results from my PhD work. It is regarding an unsteady simulation in a linear aerospike nozzle. This work was done under the guidance of Professor Dr. Abhilaj Suryan from College of Engineering, Trivandrum. So this is the outline of my presentation. We all know the concepts of altitude adaptive nozzle. There are different types of altitude adaptive nozzles like aerospike nozzles, expansion deflection nozzles, dual bell nozzles, etc. My area of work is mainly concentrated on linear or planar aerospike nozzle, and these are different configurations in which we can materialize aerospike nozzle. The first one is an axisymmetric nozzle. This one is a planar nozzle, where it will be having a rectangular cross section. And this is nozzle in which the length is truncated. You can see there a base will be formed due to truncation, and some primary nozzles are arranged around the central plug. So that configuration is called a clustered axisymmetric plug nozzle. Same configuration is possible in the case of planar nozzle as well, where we divide the main primary nozzle into different modules to get the clustered configuration. So in my analysis, I had taken a full-length aerospike nozzle, and this is the geometry details of the aerospike nozzle which I had taken for my analysis. The plug surface is having a total length of 100 mm, and the design Mach number is 3. It is designed for an overall pressure ratio of 36.74. The primary nozzle is having a design pressure ratio of around 15. So this is the computational domain which I had taken. The inlet conditions are taken as pressure inlet. The outlet condition is taken as pressure outlet, and all other walls are considered as adiabatic walls. And this is the governing equations. So coming to the numerical setup, I had used the ANSYS Fluent for my simulation. I have used a pressure-based coupled solver for getting fast convergence. And here, second order upwind scheme is used for spatial discretization, and first order implicit scheme for time transient formulation with a time step of 1 e raised to -5. And the boundary conditions I have already discussed. And for presenting the results, hello. All the length scales are normalized with the length of the plug surface L, as well as the time is non-dimensionalized according to the equation T star is equal to Tc divided by L, where T is the instantaneous time, C is the flow speed of sound at the stagnation condition, and L is the length of the plug surface, and the time is T star is taken as 0 where the flow is fully developed. So for the sampling of the data, I had taken from T star is equal to 0 to T star is equal to 140. So this is a turbulence study in which I had studied 4 different turbulence models at 2 different NBRs. One is at 4.7 and other is at 8.8. And I found that the transition SST model is having a close match with the experimental results. And the mesh independent study is done based on methods specified by Roche, where I had taken 3 meshes, and the Mach number at the central line for the primary nozzle exit was taken as the property to check the grid convergence index. And we can see that the error estimate for the fine mesh has reduced considerably when considered to the coarse mesh. And I've taken the second mesh for my analysis, 2 different, and also the Mach contour along the central line of the primary nozzle exit is also plotted to see how check whether the solution is independent of the mesh resolution. So this is the validation. I had plotted the static wall pressure along the plug surface at different NPRs, and the error is estimated using a RMS error is calculated to check the match of experimental and numerical results, and on average, I had the error is less than 2%. This is a qualitative validation where I had compared the shock structure with the numerical density gradient contour and experimental Schlieren, and at NPR 11.3. So moving over to the results and discussion. So this is the basic flow structure that will be happening inside a full-length aerospike nozzle. These figures shows with the progress of NPR from 3.1, 4.7, 8.8, and NPR 12. You can see here that at very low NPR, two overexpansion shocks will be formed. One from the upper upper side of the primary nozzle. One overexpansion shock will be forming from the plug surface. They will interact to form a MAC disk at very low NPR. With further increase in NPR, this turns into a regular reflection, where we'll be having two overexpansion shock and one recirculation bubble forming here. With increase in NPR, we can see that the overexpansion shock as well as the recirculation bubble is moving downstream along the plug surface. And finally, at NPR 12, we can see that this recirculation bubble have just reached the tip of this plug surface. So accordingly, we will be getting the pressure profile which I had shown before. Initially, we will be having in between, we will be having a wave type pressure profile in between. Actually, that is what helps the nozzle to adapt to the ambient atmosphere through a system of multiple compression and expansion waves here on the plug surface. Once it reaches the overexpansion shock reaches the tip, it will act similar to a conventional bell nozzle. So what I had observed is that once the recirculation bubble has reached at the tip of this plug surface, they will start to interact with each other, causing an asymmetry in the flow, as well as the recirculation bubble will also interact with the separation shock here, and it will cause the shock to oscillate about a mean position. That will actually create a fluctuating pressure over this plug surface. As we know that this fluctuating pressure will initiates a side load. This fluctuating pressure can lead to side loads on that nozzle. So this phenomenon has to be eliminated in order for a steady operation of this nozzle. So we can see that with increase in NPR 15 also we can see the asymmetry is happening in 17 also, and finally we can see that once the recirculation bubble is pushed out from the nozzle, the flow again becomes steady. So this is what happens in the case of linear aerospike nozzle. In the full-length linear aerospike nozzle, you can see that till NPR 12, the flow is steady, and there is some unsteadiness happening from NPR 13 to 15, 13, 15, and 17. And finally, when the recirculation bubble moves out of the domain, the flow again becomes steady. So this is again streamline and plot just to confirm the unsteadiness. This is taken as two random timestamps, T stars, and we can see that the shock is oscillating about a mean position, and as well as the two recirculation bubbles are also interacting with each other. So this is again one more plot to confirm the unsteadiness. This is the separation locations at above the plug surface and below the plug surface at different NPRs. You can see that up to NPR 12, both the flow the flow is separating from the same location from both the surfaces, and after it is fluctuating, randomly fluctuating. So this is the pressure profile at the separation location and a few locations downstream the plug surface. We can see that there is a pressure fluctuation, and this is the frequency of the pressure fluctuation. I had plotted it for NPR 13, 15 as well as for 17. You can see that there is a pressure fluctuation happening over the plug surface. So this is the again the movement of the shock from point 1 to point 2 at two different times. So this is what I taken from the unsteady data. We can see the pressure is the foot is oscillating between point 1 and 2. So when we calculate the frequency corresponding to this is taken for NPR 15. And if we calculate the frequency corresponding to these two times, we can observe that the frequency is close to the 952 hertz. Sorry, 902 hertz, which is the main frequency observed in the case of NPR 15. So what I had done is, you can see that up to NPR 12, the flow is steady. So what I had done is, I had just truncated the nozzle at X by L. So here the flow is steady up to X by L is equal to 0.53. So I truncated the nozzle at a safer location of X by L equal to 50. So we can say that the shock will move downstream, and it will be fixed at the tip of this plug surface, so that there won't be any further fluctuation happening over the plug surface. But we can see that in the case of a truncated plug, we can see the overexpansion shock is arrested at the tip of the plug surface at all different NBRs. But due to the interaction of these two recirculation bubbles formed over the just behind the plug surface, there can be some kind of pressure fluctuations happening over the base surface. So there won't be any fluctuations here, but the base surface will be having some amount of pressure fluctuation. So in order to find the pressure fluctuations over the base surface, I had plotted the pressure profile around the base surface like here. And I had taken three different points, Y0, Y1 and Y2, where the pressure, we can see here is an inflection point. So I plotted the pressure at these 3 points with the maximum pressure fluctuation was observed at NBR 15 at X by L is equal to 0.68. When considering with that fluctuation, we can see that the fluctuation happening over the base surface is considerably reduced or it is negligible when compared to the overall fluctuation in the case of a full length plug. So again, I had from here also we can see that the point Y0 is having the maximum pressure. So I had plotted the pressure fluctuation at Y0 for all the NPR starting from 10, 11, 12 to NPR 17. You can see that the flow is steady at 10, 11. There is a small fluctuation at 12 and 13 and a very small fluctuation at NPR 15. And again at NPR 17, the flow becomes steady, completely steady. Okay, then one more confirmation I had taken, like I had plotted the normalized moment with respect to the Z axis. And we can see that in the case of full length plug, there is an unbalanced moment happen at the NPR 12 to NPR 17, you can see. But in the case of the 50% truncated plug, it is completely stable in terms of its operation. So that was my, this was part of my PhD work. And as a conclusion, I would like to say that in the case of full length plug, there will always be an asymmetry associated with a certain NPR. So while designing a full length aerospace nozzle, we have to take into consideration these NPRs where the flow can become asymmetric. So it is better to truncate the nozzle at a particular F by L ratio where we can eliminate the unsteadiness associated with these full length nozzles. So that's all my references. And thank you so much for listening to me.
Yeah, interesting book. It's open to questions. Yeah.
Can you go to slide 23? Yeah, here. So the lower curve is what? Downstream or upstream? I didn't. Or the same location? What is it?
17, sir. This one.
Yeah. So this is what location?
These fluctuations are taken over the base surface only.
At the base surface, then for different NPR is what you have plotted there.
Different NPRs.
Okay. So at so even for this, there is some kind of oscillation.
Here, a very small oscillation is observed, but it was very less when compared to the overall the pressure fluctuation observed in the case of full length plug. Okay. And I think that is because of the interaction of these two bubbles, which is formed behind the plug.
That is the larger oscillation. For this small oscillation, what is it? What reason do you?
This one, sir. This one.
Yeah.
That is because of the interaction between these two bubbles formed behind the base. I think that too can be eliminated with the help of a secondary flow injection from the center of this plug, so that it will prevent the interaction between these two bubbles. We are investigating on that also.
For the uncut nose ejector, the nozzle, how long did you run? If you run it for a long time, will this bubble just go away? You saw. Okay, this oscillation, that oscillation that you're showing there, that pressure oscillation, the signal that you have just now shown. So that is for what time?
That was taken from actually these results are taken once the flow is fully developed and the oscillation just continued throughout.
Okay, so there is a shedding kind of pattern that is coming out.
But I haven't observed as shedding, but these
But the signal is clearly shedding.
yes,
pattern.
yes. In the video also, I can see these two kind of oscillating there, these two bubbles. I haven't taken a video to my presentation, but it was just these bubbles are moving up and down like this.
Oh, that's, I don't understand this. This is at what Mach number?
This is at the design Mach number is 3, and this is at NPR 13, 15, and 17.
Talk about it.
Did you have any experimental data on unsteadiness to compare this with? Because when one, I mean, the shedding, I don't know if you with RANs you were actually resolving that properly. So did you have any experimental data to compare this with?
No, I'm having only steady, this one only, one static wall pressure data is only available with respect to experiment.
There is no fluctuating pressure data.
No.
Any other questions? Not. Thanks a lot for the interesting presentation. And with that, we come to the end of the session and we break for tea.
Now I request Professor R. Sriram to hand over a small memento to our session chair. Now let's break for tea. We have a 10 minutes break. Let's assemble back at 11. Thank you.
Good morning, good afternoon, and good evening. I am Hidong Kim, the chairman of the 34th International Symposium on Shock Waves. It is a great honor to present a brief introduction to the 34th ISSW. Today, I will be talking the venue, special event, and accommodation. Finally, you can enjoy the video clip for the ISSW 2023. This is an overview of the 34th ISSW venue. We will be hosting the symposium at Daegu Expo, which is well equipped with advanced IT facilities as well as modern convenience for international symposia. During the ISSW, 5G Wi-Fi network system is available for free use, and the participants can visit and enjoy a number of restaurants, cafeteria, and shops inside and around the venue. We are going to use Exco's third and fifth floors. The third floor has the grand volume for welcome session, exhibitions, and 16 oral presentation rooms. The fifth floor will be ready for opening ceremony, closing ceremony, and plenary lectures. And the Sky Garden will be also available for special events and other small group meetings. And we have a kite-wide exhibition space for poster presentations of more than 500 posters, books, and corporate communications as well. Key date for submission of abstract, full papers, and registration will be like this. We would like to start abstract submission as early as possible so that authors can have enough time to make the extract. This time we expect more than 500 abstracts. All the submitted paper will be reviewed by scientific review committees, which will be fixed in a couple of months. will make the book of abstract for symposium participants, and the full papers presented will be published in the proceedings shortly after the symposium. We have already fixed the International Advisory Committee and the local organizing committee, and now is contacting scientists and scholars over the world for the scientific review committee. This is the tentative program for the 34th ISSW. We will have 3 plenary lectures, which will be delivered in the mornings of Monday, Wednesday, and Friday. The keynote lectures will be 2 parallel sessions in the afternoon every day, and the oral presentation in more than 12 parallel sessions, depending on the number of abstracts. As you can see here, we will make use of a smart registration system which has been successfully applied to some previous international symposia. This is a real-time management system in which participants can check all the data regarding registration, abstract, hotels, and technical program on their own mobile and tablet PC. You see here an example of the smart registration system. The regular registration will include technical sessions, welcome session, coffee break, lunch, banquet, symposium tour, and the book of abstract. And the symposium proceeding will be available for additional registration. Daegu is quite convenient to access from your countries. You can come to Daegu through Incheon International Airport and Kinmei International Airport. Otherwise, you can directly come to Daegu International Airport, which has many flights from Asian countries. From the Incheon and Kinmei Airport, there are many traffic means to access Daegu, and the venue Exco is located in less than 15 minutes distance from Daegu Airport and train station. Prices in Daegu are much lower compared with other big cities. Especially hotels and accommodations are relatively cheap. Daegu are quite good. Within 10 kilometers from the venue, more than 20 hotels and accommodation facilities are available. In addition, school dormitories and guest houses will be available for student participants at quite a cheap rate. Transportations between hotels, the venue, and some major points in downtown. We will have a lot of lavish special events during the symposium. As in the previous symposia, we will have the welcome reception, banquet, opening ceremony, closing ceremony, student competition award, and some committee meetings. The symposium tour will be Gyeongju, which is one of Korea's most popular tourist attractions. In addition, we will have daily city tours and cultural tours for participants and spouse. During the symposium tours, you can enjoy ancient Korean relics as well as a variety of delicious food. In case of emergency situation like COVID-19, hospital ambulance and medical staff will be ready on site. We will have well-arranged quarantine system, and participants can take PCR test at the venue whenever they want. And also, we will provide personal sanitation kit to all the participants. In addition, the LOC of the 34th ISSW will buy a medical insurance for participants. The homepage of the 34th ISSW will be opening just after this international colloquium of shockwaves. You are going to design this website to provide various useful information for participants. Here you can see the cover page of ISSW 2023 homepage. We will do our very best to make the 34th ISSW a grand success, and we are looking forward to welcoming you all at Daegu Expo in 2023. Thank you very much. Good morning, good afternoon, and good evening. I am Hidong Kim, the chairman of the 34th International Symposium on Shock Waves. It is a great honor to present a brief introduction to the 34th ISSW. Today, I will be talking about the symposium overview, committee, tentative program, key date, the venue, special event, and accommodation. Finally, you can enjoy the video clip for the ISSW 2023. This is an overview of the 34th ISSW venue. We will be hosting the symposium at Daegu Expo, which is well equipped with advanced IT facilities as well as modern convenience for international symposia. During the ISSW, 5G Wi-Fi network system is available for free use, and the participants can visit and enjoy a number of restaurants, cafeteria, and shops inside and around the venue. We are going to use Exco's third and fifth floors. The third floor has the grand volume for welcome session, exhibitions, and 16 oral presentation rooms. The fifth floor will be ready for opening ceremony, closing ceremony, and plenary lectures. And the Sky Garden will be also available for special events and other small group meetings. And we have a kite-wide exhibition space for poster presentations of more than 500 posters, books, and corporate communications as well. Key date for submission of abstract, full papers, and registration will be like this. We would like to start abstract submission as early as possible so that authors can have enough time to make the extract. This time we expect more than 500 abstracts. All the submitted paper will be reviewed by scientific review committees, which will be fixed in a couple of months. We'll make the book of abstract for symposium participants, and the full papers presented will be published in the proceedings shortly after the symposium. We have already fixed the International Advisory Committee and the local organizing committee, and now is contacting scientists and scholars over the world for the scientific review committee. This is the tentative program for the 34th ISSW. We will have 3 plenary lectures, which will be delivered in the mornings of Monday, Wednesday, and Friday. The keynote lectures will be 2 parallel sessions in the afternoon every day, and the oral presentation in more than 12 parallel sessions, depending on the number of abstracts. As you can see here, we will make use of a smart registration system, which has been successfully applied to some previous international symposia. This is a real-time management system in which participants can check all the data regarding registration, abstract, hotels, and technical program on their own mobile and tablet PC. You see here an example.
Yeah, Kanan, can you hear me? Can I?
Hello, DP Singh, sir.
Yeah, can you hear me? Hello? Can you hear me?
Hello.
Hello?
DP Singh, sir.
Yeah,
Can
can
you
you
hear
hear me? Hello?
Can't hear you, sir. Let me check
Uh,
here. Is your mic okay, sir? Please
Yeah,
check
your
your mic.
voice is clear to me.
You're not audible.
Mm, Okay,
Can you
just
just log
connect
out
the
and log in again?
earphone.
Possible?
Just give me 1 minute.
Problem with the mic.
There's a variety of delicious food. In
yeah.
case of emergency situation like COVID-19, hospital ambulance and medical staff will be ready on site. We will have well-arranged quarantine system.
Hello?
Yeah, now it's audible.
Yeah. Can I share my presentation and check whether it is working?
Sir, is your
Personal presentation
YouTube streamer on? Because we can hear
In addition, the
another
LOC,
presentation voice also.
The post ISSW will buy
Yeah, can you just stop it?
medical insurance for participants.
Sorry?
Yeah, please share your presentation.
Okay, is it visible?
Yeah, it's visible.
Just a minute. Shall I change the slides and see? It is moving?
It's not moving. Can you try that again?
Yeah, I'm in third slide, whether it is
No,
visible.
it's not changed to, it's still in the first slide.
Yeah, because earlier also I faced this problem in one of the presentation. That's why I'm little worried.
Okay. Can you go to the full screen mode, sir?
Yeah, I'm in full screen mode here.
Please share your full screen mode only, sir.
Okay, just a
When
minute.
when you share the presentation, you share that full screen mode only.
Okay. So just here. Is it visible?
Yeah, it's visible.
Can I make it full screen now?
Now, go to slideshow, sir. Slideshow. Other slideshow. Yeah. Start from the first slide.
Okay. Shall I change the slide?
Yeah, sure. Try changing the slide.
It's changing?
No. Can you do one thing? Can you just save this presentation as a PDF file? And
Okay, I'm having that also. Shall I open that?
yeah, sure. And put it in full screen.
Yeah, just a minute.
Yeah, now it's visible. Can you change this one? Good.
So it's
Yeah,
changing.
Yeah, absolutely fine. Do you have any
Yeah,
video?
unfortunately, I'm having one video, but now that cannot run. So
No,
it's okay.
you can actually come out and play the video if you can.
Yeah, it's okay. Otherwise, I will explain with this. That's fine. No issues.
Yeah.
So I will run PPT that time, right?
Yeah, yours is the last presentation, sir. Something
Yeah.
like that. Well,
Yeah, it's okay.
please be online.
Yeah, sure. So I will stop sharing now.
We'll contact you shortly.
Yeah.
Okay, thank you, sir.
Hello. 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 Welcome back to the second part of the morning session. So we will continue with the technical session. This session is chaired by Dr. Bharat Govindarajan, Department of Aerospace Engineering, IIT Madras. I welcome the chair to introduce the speakers and begin.
Thank you very much. Good morning, everyone, and welcome to the second session of the day. Yeah, so we have 5 papers in this session. So I guess we can start off with the first one. I'd just like to request the speakers to adhere to their 15-minute time limit so that we can have time for some questions. We can begin with the first paper. It's presented by Divya. It's on a numerical study of laminar transitional shock boundary layer interaction on hypersonic double wedge using a modified gamma transition.
Good morning, everyone. I'm Divya Harshavardhani, working under Professor Rajesh and Professor Arul Prakash. Today, my talk is on the numerical study of laminar or transitional boundary layer interaction on hypersonic double wedge using a modified gamma model. We all know the major problems occurring in the hypersonic aerodynamics are basically stagnation flow field analysis, hypersonic boundary layer transition, and the shock boundary layer interaction or shock-shock interactions. In this study, I'm going to concentrate only on the shock boundary layer interaction. Based on the applications, the shock boundary layer interactions can be classified into 3 types. One is a normal shock SBLA, where the normal shock interacts with the boundary layer. Second is the compression ramp SBLA, where due to the compression, a shock is formed and it will interact with the boundary layer. Third is the oblique shock impinging SBLA, where the oblique shock will interact with the boundary layer. All these 3 SBLA will have a different characteristics. Also, the SBLA can be classified as laminar, transitional, or turbulent SBLA based on the incoming boundary layer state. The main real applications of to predict this as a shock boundary layer interaction is mainly to find the heat transfer characteristics, because when in the hypersonic flows compared to the turbulent or the laminar boundary layer, the transitional boundary layer will have a very high heat transfer rate, which will affect the thermal protection system or the engine inlet and the control surfaces. The factors basically affecting the compression ramp SBLA are as given here: Mach number, temperature, deflection angle, and the Reynolds number, and the incoming boundary layer state. The main motivation for this study is because there are many researchers happened in the studied on the turbulent SBLI, but very few studies are reported in the literature on the laminar SBLI in the hypersonic regime. Also, one study by Delary et al. In 1970, he found that the wall cooling has a different effect on the laminar and the transitional SBLI. And also, Hu et al. Found that the viscous effect has a different solution on the inviscid FBLI. One more major drawback is that the existing RANS model do not predict the separation as well as the separation bubble length as well as the transition simultaneously. The same authors we have developed a modified gamma model, which was published in the literature. The main objective of this work is to assess that the modified gamma model to predict the transition location and separation bubble length on the hypersonic double wedge. Here the configuration chosen is a hypersonic double wedge because the control surfaces and the engine inlet ramp can be conveniently modeled as a 2D double wedge configuration. Thus, this configuration is chosen for this study. And also, as I discussed earlier, the effect of θ2, that is the second wedge angle, wall temperature, and the length of the first ramp, and how it changes the transition and the separation bubble length is also studied in this work. This is the geometrical and the computational details. This was an experimental study done by Oliver et al. Here there are two. It is a double wedge where the first wedge is 9 degree and the second wedge is 20.5 degree. And this figure shows the boundary condition and the free stream conditions which is given for this study. This is exactly the same as the experimental condition given in the literature. For this study, we use the in-house solver code to analyze the double wedge configuration. Basically, in this, two results are analyzed. One is a numerical Schlieren to quantitatively analyze the shock boundary layer interaction and basically on the separation bubble length, and qualitatively analyze the heat transfer rate using the Stanton number distribution. This is a brief description of the computational methodology, which is the in-house solver code is a 2D finite volume based solver, which solves the all grid part grid format, and the solver is OpenMP parallelized, and the flux is reconstructed using the second order HLLC scheme with the Venkatakrishnan limiter, and the time marching is done using the fourth order Range-Kota method. For this turbulence model used is the K omega SST turbulence model, and the transition model is the modified gamma model developed by us is used for this. The main advantage of this modified gamma model is that here it is basically from the Mentor's low speed model where we have added the compressibility correction effect to the transition prediction, and also the inlet turbulent intensity and the viscosity ratios are not randomly chosen, but it is chosen based on the correlations. These are the modified gamma model where we have developed. For further details regarding the model, please refer to the literature which is published. This is a flow field analysis, which is numerical Schlieren of the flow over the double wedge, which is obtained by using the modified gamma model. We can see that the model could predict both the separation bubble and there are two interaction points where one is a leading edge point which is interacting with the reflected shock from the separation and the reattachment shock. First, TP1 is basically the interaction of the separation shock as well as the reattachment shock, and TP2 is the interaction of leading edge shock wave with the reflected shock from the TP1. Coming to the CP contour, we can see that this model can predict the recirculation bubble well, as well as in the ST contour, we can see that the separation bubble as well as the transition in the reattachment region is also predicted properly. When we see these results, we can see that the fully turbulent model actually doesn't predict the separation bubble, whereas the fully laminar model doesn't predict the peak heat transfer rate at the reattachment point. So from this analysis, we found that our model is capable of predicting both transition and the rear separation bubble length properly. Next is, as I discussed earlier, the effect of the wall temperature, second wedge angle, and the first length of the first ramp is also studied. From this figure, we see that as we increase the wall temperature, is this a point where there is a separation, location of the separation shock, or is the reattachment? We increase the wall temperature, actually the separation bubble increases in length, which is typically a characteristics of the laminar interaction. This is actually properly predicted by the model. This is mainly because in the hypersonic case, second mode instability, when we increase the temperature, the second mode instability will be stabilized so that the flow is more laminar, which is than the turbulence, and hence the laminar interaction is the effect of the laminar interaction is as we increase the temperature, it will increase the bubble size. Second parameter is the effect of the second wedge angle. From the first figure, we can see that when θ2 is put in, that is, the shock is very weak, where it could not create a separation. I mean, it could not interact with the, even though it interact with the boundary layer, it doesn't have a adverse much pressure gradient to create a separation bubble. Whereas as we increase the second wedge angle, we can see that slowly the separation bubble is forming and it is increasing, which is also seen in the experiments. So the model can predict this effect also. Coming to the quantitative analysis, we have plotted the Stanton number across the double wedge configuration. The same phenomena is actually seen as we increase the temperature, the separation bubble is actually increasing for both the case, for θ equal to 20.5 degree and θ equal to 27 degree. And when we see in the 14 degree test case, in the 14-degree test case, we can see that this is the SST model results and the dotted lines are the modified model results. We can see that the flow is not actually become transition here. It is still in the transition state. It has not gone to the turbulent state. But this is actually the opposite trend which is found, which is showing here. This test case needs some further investigation, because usually when we increase the θ2, when the θ2 is less, actually this parameter needs to be more laminar, but here it is showing the transitional results. So this test case needs further investigation. The third parameter is the effect of first ramp, that is wedge length, where the ledge length is increased from 0.1 meter to 0.3 meters. As we can see, as we increase the wedge length, the boundary layer is becoming transition to turbulent. So when we go to 0.3, the boundary layer become completely turbulent, so that here we could not see any separation bubble. This is mainly because the turbulent boundary layer has doesn't have a separate, it won't separate easier when compared to the laminar boundary layer. For L1 equal to 0.1 meter, we have tested the effect of temperature. Again, it is similar to the laminar interaction, which is already discussed before. When we quantitatively analyze the Stanton number, we can see that as we increase the length, the flow is becoming the transition in the first ramp itself. When we compare with the turbulence model, we can see that here the flow is actually become turbulent here. So from this results, we can see that the developed modified gamma model can predict all the condition, all the parametric effects properly, except for L1 equal to θ2 equal to 14 degree. And the double wedge configuration, to conclude my talk, I'm saying that the double wedge configuration is studied numerically using a modified gamma model. And this modified gamma model predicts the separation bubble and the transition, both quantitatively and qualitatively. Effect of wall heating for length of the first ramp and the wedge angle is also studied. Altogether, 21 test cases have been studied. Out of these cases, only θ2 equal to 14 degrees shows some different results, which needs further investigation. Thank you.
you very much. Do we have any questions?
Inference, can you hear me? Yeah. So this is regarding your inference with this higher wall temperatures. You said this second mode of instability. The flow getting stabilized because of which the bubble growing bigger and so on. Will the gamma model be able to predict that actually? Does it actually inherently have? Does it inherently have that ability to predict where it becomes unstable?
Actually, this model, it does not explicitly do it, but it is having a framework where the del 2 values is actually correlated in the gamma model. Boundary layer thickness is correlated in the gamma model, so that it will have some effect that can be.
Because this thickening, separation bubble becoming larger with the laminar bubble might be for other reasons.
Okay, so
Because the viscosity gets modified near the wall.
Okay, sir.
So when the viscosity becomes, and the Mach number becomes different. So when your temperatures are higher, the sonic portion is probably larger.
Furthermore.
So which means your upstream influence might be more.
Okay.
So there might be other reasons. So I'm not sure if the inference based on the
Okay, sir.
suppression
I'll
of
look
these
into it.
instabilities.
Thank you. Professor Sami. Yeah, it's in continuation. Can you hear me? So in continuation with what Sriram has asked, that bubble that you see there, is it a stationary bubble or was it oscillating?
As of now, it's a stationary bubble. And we have simulated only the steady state solution.
Maybe a steady state solution, but the point of stagnation point just in front of the bubble, that may not be stationary. Will that affect your model is what, because that
Shock
creates an instability. Now, will that affect your?
I couldn't hear you.
Okay. So the stagnation point in front of the separation bubble, that's never going to be stable.
I see.
It's going to move around,
Oscillate.
fluctuate. So will that instability create something in your model? Second part of this question, which may have the same answer, is have you tried another test case rather than RAM, where you don't have a bubble, but probably have a shock?
It has not been tried, sir. Maybe
That is
we'll
not
try.
being tried. So you have only tried these double.
Only this,
double pitch.
only this test configuration.
So you have not tried a conical.
Yes, sir. It has not been tried.
Any such thing. Okay, maybe that's a thing that you could.
I'll see to it, sir.
Right. Yeah. Okay.
Yes, sir.
And what about the low Mach number? Will your model work?
The low Mach number, it is already been published. It is predicting the transition properly in low Mach number also.
Your model.
Sir?
Your model.
Yes.
Okay. How low is low?
One test case which I tried is on flat plate 0.15
Oh, okay.
Mach number.
Any other questions? Maybe I have one, just a clarification. So your gamma, the intermittency, it goes between 0 and 1?
Here at the wall, it is going between 0 to 0.
No, in general, gamma can take a value.
In general, it goes
So when
from
you
0
say,
to.
and in your study, when you say you notice transition, is it when gamma becomes 1, or how do you define it is now transition? Is it
Basically, we are predicting it from the Stanton number values. When the Stanton number increases from the laminar to turbulent, there is a change in the heat transfer rate, where it is suddenly increased from lower value to a higher value. So that is how we are saying that the boundary layer is transitioning.
Okay, yeah, just a comment. Maybe if you also have a contour plot of gamma, that might be interesting to see how.
Okay, sir.
Thank you.
Yes, sir.
Okay, if there are no other, there was a Shantanu.
Good question. So
Yes, sir.
have you tried any flow where there's no shock but just transition?
Sorry, sir.
Have you tried any test case with no shock, but just transition in the hypersonic regime?
Flat plate
Hypersonic
test
boundary
case.
layer, yeah.
Flat plate test case has been tested for max 6.3, 6.2
And it's working over, I mean.
working.
Only one issue with gamma intermittency model compared to the two equation model is that the length of the separation, sorry, the length of the transition
Yes,
state
sir.
is not well predicted. How does it do for your model?
Actually, for most of the test cases, the length of the transition has been predicted properly. For only one test case, it has not predicted where the temperature is increased to some 800 Kelvin. Except for the test case, for all other test cases, it has almost predicted the transition length.
And this code, it's using only one, there's no non-equilibrium effects you have modeled in your code, right?
Sir?
Any non-equilibrium effects?
No, so non-equilibrium respects has not been added because all the experiments which are done are assumed as a perfect gas. It follows the perfect. The experimental test validation test cases which I have tested in the paper itself, literature itself, they assume that it's a perfect gas, and they didn't see any real gas effects. Those models only is validated for this. Those test cases only validated for this model.
Okay. The hypersonic boundary layer is in that paper, published paper, not.
Yes, sir.
Okay, thank you.
Okay, thank you very much. We'd like to thank the speaker again. Our next presentation is by Siva. It's on detached eddy simulations of an incident shock induced separation.
Hello. Good morning, everyone. My name is Shiva, and now I'm presenting my research work on detached eddy simulations of an incident shock-induced separation. Initially, we'll have some introduction about shockwave boundary layer interaction, followed by sources of unsteadiness, which will give us motivation and objective, and we'll discuss some computational methodology considered for the present study, and we'll wind up with conclusions. Shockwave boundary layer interaction. It is an interaction of a shock with a boundary layer forms on a solid surface. So the presence of shocks and boundary layers in high-speed compressible flows makes it an inevitable phenomena. So when a shock wave interacts with the boundary layer, it imposes an adverse pressure gradient for which boundary layer responds by bulging or creating a separation region locally, depending upon the adverse pressure gradient magnitude. Since most of the practical flows involves turbulent boundary layer, shockwave turbulent boundary layer interaction is a common phenomenon. So this is a typical example of an incident shock interacting with the boundary layer on a solid surface and forming a separation bubble. Often separation bubble is accompanied by other additional shocks like separation shock and reattachment shock. So these shocks inherently found to be unsteady with the frequencies of the order of 500 Hz, and this frequencies are termed as low frequencies considered with regards to the upstream boundary layer frequency, which is of the order of 50 kHz. So these low frequency unsteadiness has undesirable consequences by generating unsteady pressure and thermal loads, which will leads to the resonance phenomena and further structural catastrophe of the vehicle. So like aircraft buffeting and intake buzz and unstart are the few examples of these consequences. So thus it is very important to be analyzed. So in research community, it is widely believed that there are two main possible mechanisms for this flow unsteadiness, and there are two separate sections of people working on these two like mechanisms. A few people like Plotkin, Berish, and Tauber and Sandham, they claiming that the sources for these unsteadiness could be coming from the turbulent boundary layer, upstream turbulent boundary layer, while other people like Pirojoli and Piponia and Preb and Martin, they are claiming that there could be an inherent instability inside the separation bubble downstream of the shock. So that could be triggering these low frequency unsteadiness. Like these are like two kind of different arguments which are on continuous debate for the last 4 or 5 decades. And these unsteadiness are found to be very challenging to be analyzed through numerical approaches. Like Marshall and Doling, they stated that RANS does not have a mechanism to capture these unsteadiness, while DNS and LES has. And Pirojoli and Grasso and Preba and Martin conducted some DNS studies for 2D ST-Belay cases, but their conclusions, their opinions became questionable because of their low flow times. And Garnier obtained some time averaged flow characteristics for the same 2D ST-Belay. And from the unsteady aspects of 2D ST-Belay, from the studies of Tauber and Sandham, it is evident that at least 30 cycles of 30 frequency cycles are required to characterize this unsteadiness, which is quite a lot of time. And to address these issues in high Reynolds number cases, Spalart in 97 and proposed a hybrid RANS-LES model, which is a DES 97, to address these issues, and he enhanced it to the delayed DDS in 2006. And in 2015, and 2016, Durbin et al. Implemented a dynamic procedure and enhanced this DES model to adaptive DES by implementing a dynamic procedure which is similar to Smagorensky model. So, and it is found to be relatively more accurate than standard DES models. So with this motivation, like due to inability of RAN simulation and longer computational time associated with LES and DNS models, so these hybrid LES, RANS-LES models or detached eddy simulations seems to be a solution. And we are just trying to develop that. So our main objective is to develop a 3D compressible Navier-Stokes solver with DES or adaptive DES models to characterize these frequencies associated with shock wave turbulent boundary layer interactions. So as a part of initial step, like we developed a K-omega turbulence model. So in K-omega turbulence model, we solve 2 more additional equations besides our main governing equations, that is for turbulent kinetic energy and turbulent dissipation rate. Upon solving these 2 equations, we calculate turbulent viscosity as a ratio of these 2 quantities and coupled to the main governing equations to calculate the mean flow field. And these are the modeling coefficients associated with this. And boundary conditions at the wall, turbulent kinetic energy is 0, and turbulent dissipation rate behaves as an asymptotic condition as we approach the wall. And we implemented production limiter as well to restrict the values to the physical domain. As a validation case for this, we have taken 2D zero pressure gradient flat plate. This is the geometry along with appropriate boundary condition, and it is adapted from the NASA turbulence model website. And this particular case is of Mach number 0.2 and free stream Reynolds number of 5 million, free stream temperature of 300 kelvins. Numerical parameters like convective, like spatial discretization is treated with fourth order compact scheme, and temporal discretization is treated with fourth order Runge-Kutta scheme, and implicit filtering of 10th order is used for non-turbulent quantities, while second order filtering is used for turbulent quantities due to their stiffness towards higher order filtering, and CFL number is of 0.5 is maintained for the simulation. So from the plots of skin friction coefficients and velocity profiles, and it is evident that the present solver results are in fair agreement with the reference results of CFL 3D solver from the NASA turbulence modeling. And there is a small discrepancy in turbulent eddy viscosity that could be due to a lower order filtering that we are using. It could be corrected if you go for a higher order filtering coefficient, high filtering coefficient. And like, since we are working with compressible flows, like we enhance the present RANS solver with the shock capturing ability, we using adaptive filtering method. So in adaptive filtering method, the smooth flow regions are treated with higher order filtering, while the shock regions or discontinuity regions are treated with lower order filtering. So for this method to apply, first we need to detect the shock. So for the shock detection, we know type smoothness criteria was used. So smoothness criteria, smoothness parameter 5i is calculated based on the pressure values at the current as well as the boundary points. So once this smoothness parameter is greater than some threshold value, that particular region is identified as a shock region. Otherwise, it will be identified as a smooth region. So from this figure, like the section A describes the pressure variation. So there, 3 red color points are the actual shock points, and blue color points beside these red color points, along with red color points, constitute as a shock region. So this particular region will be treated with the lower order filtering, while the other smooth flow region is treated with higher order filtering. But the interface regions, like it will be, so instead of going from 2nd order to 10th order directly, the filtering order will be gradually ramp up from F2 to F10 to avoid the numerical instabilities. So as a validation cases for this, one-dimensional shock tube case is considered. So from the density variation at a non-dimensional time of 0.15, so compact scheme with the conventional filter, despite capturing the shock very well, so it has induced any undulations or fluctuations near the discontinuities. So upon the implementation of adaptive filter with the compact scheme, it is vanished almost all the fluctuations near the discontinuities, and but the shocks made a little, but that is okay. That is with a reasonable accuracy. And the second case is 2-dimensional inviscid shock reflection at Mach 3 and a deflection angle of 0.5. So this is so the shock is generated on the top boundary using jump conditions. So it will be deflected back towards the bottom surface, and from which it reflects back. And from the pressure variation at Y 0.17, we could see that the shock has been captured pretty well, and it has eliminated most of the fluctuations, high frequency fluctuations. So with this, like we have just before going to the DES, we just want to get the mean assessment of the flow field. That's why we conducted RANS simulations with. So the flow parameters we have taken from the Dusage et al. Study, which is an experimental study. And yeah, this is the computational domain. And this particular inlet is fed with the mean inlet turbulent profiles using some standard wall laws like Spalding wall law and Van Dries coordinate system. And shock is generated on the top boundary using jump conditions. And we have used compact 4th order and 10th order filtering in smooth flow regions and 2nd order filtering in shock regions. And then you go to 4th order for time integration. And from the RANS results, it is quite evident that it has captured all the important flow features like separation shock, separation bubble, expansion band, reattachment shock pretty well. And from the time average studies, we found that at least 4 milliseconds of computational time is required to get the steady shock structure. From the grid independent study, 601 cross 151 grid is found to be optimum with an interaction length of 4.67 delta, which is 11% more than the experimental results, where it is mentioned as 4.2 delta. And we found that it didn't show any kind of unsteadiness. It didn't capture any kind of unsteadiness. So we further extended this to DES in order to get some kind of unsteady picture. So in DES, basically it is a hybrid RANS LES approach where it works as RANS in attached boundary layer and LES in detached boundary layers as well as eddying regions. So this kind of the switching from RANS to LES happens through a length scale formulation, that is LDDES. So this LDDES confirms which length, which model to be taken. So once this LDD length scale is calculated, it will be so it will be used for calculation of mu t, and this eddy viscosity will be substituted in the production term of the kinetic energy equation. There won't be any other change other than this. So basically the governing equations are as same as the RANS equations. The only change is that we are going to change the kinetic energy term, production term of the kinetic energy equation using this length scale formulation. So this FD is a shielding function which prevents premature switching between RANS to LES. So near the wall, FD, basically shielding function is 0, which allows the model to work as a RANS. But when FD is 1 and RANS length scale is less than LES length scale, still it works as a RANS. But when FD is 1 and LES length scale is less than the RANS length scale, it works as a LES. So this is how it works. And this model further enhanced as a adaptive DES with the dynamic calculation of this coefficient CS. This dynamic calculation is pretty much similar to the Smagorensky calculation. So calculating resolved stresses using test filter quantities, it is pretty much similar to the Smagorensky model, dynamic Smagorensky model. So with this adaptive DES model acts as a RANS in attached boundary layer and acts as a dynamic Smagorensky model in detached and eddying regions. So yeah. So we applied this model for the same simulation. So we initialized the simulation, initialized the domain with the RANS solution, and we started it. So actually, we got an enlarging separation bubble. We expected it could perform some kind of oscillations, but it is showing some enlarging separation bubble. So, and then we did the same simulation with adaptive DES 2D. So in this adaptive DES simulation, we could see a clearer wiggles are observed on the outer boundary layer regions, which was not there in standard DES model. So this gave us like a small hint or small positive indication of working nature of this dynamic nature. And then like expecting like 3D domain could result in smaller separation bubble, we considered a small smart noise domain with the LZ of 0.7 delta with the resolution of delta Z plus 30. So it didn't show any kind of change in the behavior. So it is pretty much similar to the 2D adaptive DES. But the thing is that we observed a separation vortex breakdown in 3D, which was not there in 2D DES. Yeah. So now further we are going to try with the full 3D domain. So as of now, we are not having computational resources. So we are parallelizing our solver. So we'll be doing 3D simulation soon. So these are the conclusions. RANS simulation overestimated the interaction length by 11% with the experimental results, and standard DES produced enlarging separation bubble, while 2D adaptive DES produced clearer wiggles in the outer boundary layer region, and separation vortex breakdown is observed in 3D adaptive DES along with enlarging separation bubble. Thank you.
Thank you very much. Any questions?
So you developed a compact difference-based solver.
Yes.
But test cases you have tried, right? You might have tried something like advection of an invasive vortex.
Yeah, yes.
Have you tried that?
Yes, yes.
But it didn't show any results. So it's difficult to gauge if that higher order methods are working properly, no?
We have tried, sir, actually.
Okay.
Yeah, actually, here we couldn't show.
Yeah, based on what you have shown, it's not clear, because filtering part you're showing, but
Oh.
at higher order, it's working properly, it's not.
Yeah, it is working actually. We have simulated those things. I like convection vertex case.
Okay.
Yeah.
Nice presentation. I want to know, like when you say that near the wall, it behaves more like RANs. And you have this original question that you were asking whether it is upstream influence or is it from the downstream. These are all happening near the wall, right?
Okay.
And RANs is not able to pick up those things. I mean, that was how the kind of thing that developed. So at the wall, if it is going to behave more like RANs, won't it be, going back on what you're trying to do?
Like in near wall region, it works as a RANs. If it goes outer regions, it may work as LES again. Yeah.
So where do you expect this, upstream influence and all those to happen? Is it in the near wall region? Right, it should be in the near wall region.
Yeah.
So, I mean, I just want to understand because
Yeah. I
something
understand.
different. I'm not an expert here, so.
Yeah. So it's a good question.
Hi.
Yes.
When you are trying to run this delay DES method and all, finally, if I now take a time average over several cycles, you told like you need some 30 cycles or something. Did you do that? 30 cycles?
No, sir. We are yet to do.
You have to do that.
Yeah. Actually, it is initial. We are just starting, validating things. It is just starting in. We have developed the model and we are checking now.
So my question was supposed to be like, if you have done that, then
Ah.
will this match with the RANS simulation or will it be very different from it?
Oh, time average picture.
Yeah, time average picture. You don't know it yet.
No idea, sir.
Okay, but second thing, the shading frequencies, were they matching with that from experiments?
Oh, this one.
Yeah, Dosage would have given shading.
Yeah. Actually, we have tried for 2D domain only. Like we supposed to do for 3D. Like it is.
But you are seeing shading, right? You can still.
Yeah. Actually, we have taken a small span like to investigate the effect of 3D, but we have to go for a larger span actually. So just like to ensure whether it is working, that the dynamic nature is working or not, we have taken a small domain. So we don't have any sophisticated parallelization till now. Now we are working on it. So with the OpenMP parallelization, whatever we could do, we have done it.
That's all just the implementation of the.
Yeah. So now we are just trying to validate the things. Now we are parallelizing, and we are very soon we are going to take a full 3D domain and going to validate the things. Just initial step for confirming this dynamic nature or these models are working or not. We just did some simulations.
No, you're not. Check the,
No.
Shading.
Yeah.
Yeah. Thank you.
Can you hear me? For Srisha's question, I think it takes RANs very close to the wall. That depends on the grid size of the DES thing actually. So I think that may the subsonic part of the boundary layer may be higher to have a upstream influence. It is based on grid sizing that the RANs region is very close to the wall. So the subsonic part of the boundary layer might be higher than that. I speculate that.
Thank you very much. Just thank our speaker again. Yeah, next presentation is by Ramachandra Kannan. It's on the study of unsteadiness due to 3D shock boundary layer interaction in flow over a square face protuberance.
Good morning, everyone. So, I'm Ramachandra, MS Research Scholar in the Department of Aerospace Engineering, working under Professor R. Sriram. And I'll be presenting my research topic about study of unsteadiness due to 3D shock boundary layer interaction and flow over a square phase protuberance. Yeah. So, as my colleague has already explained, I'll not spend much time on it. So, basically, in shock boundary layer interactions, shock impinges on the boundary layer, resulting in adverse pressure gradient, which is basically communicated through the subsonic part of the boundary layer. And it results in the upstream influence, which basically again results in the thickening of the boundary layer upstream. You could see from this configuration that there is an impinging shock and there is a large separation bubble. And this separation bubble acts as a compression corner, resulting in the compression waves over here, which coalesce to form a separation shock. So this overall flow domain is basically unsteady, and this unsteadiness has been researched for many years, over several decades actually. So this unsteadiness basically shows wide range of frequencies, starting from very low frequencies till high frequencies, which are of the time scales of the eddies in the boundary layer itself. And there are two primary mechanisms responsible for this unsteadiness that has been talked by my colleague as well, which is the upstream and downstream mechanism. Upstream mechanism, it's basically the separation shock dynamics influenced by the incoming turbulent boundary layer structures. And the downstream mechanism, the shock dynamics is affected by the inherent instability inside the separation bubble. So these are some experimental works which have been done by researchers for the past decades. So I'll be briefly discussing about this. So Brusniak and Dowling conducted experiments on blunt fin induced shock boundary layer interactions, and they observed a good correlation, a reasonable correlation between the incoming turbulent boundary layer structures and the separation bubble, which is when they high pass filtered this correlation analysis, they observed the disappearance of this peak, which is coming from the low frequencies inside from the incoming turbulent boundary layer. So Ganapathy Subramani et al. Argued that the superstructures in the turbulent boundary layer is basically responsible for the instantaneous nature of the separation shock profile. But later, Humble et al. Argued that this is only responsible for the span-wise wrinkling effect, whereas the total stream-wise oscillations of the separation shock is affected by the low frequency content in the upstream boundary layer or the downstream mechanism. And similarly, there were several researchers who talked about downstream mechanisms as well. So DuPont et al. They found a good coherence, reasonably actually very high coherence between the downstream separation bubble and the separation shock at lower frequency sites, which are of the order shown here. And later, Priponio et al. Proposed a shear layer entrainment recharge mechanism model, which is basically based on the imbalance between the entrainment from the shear layer close to the separation location and the subsequent recharge in the reattachment location. And they said that this is responsible for the overall shock dynamics. So Sovereign et al. Were probably the first group who came up with a primary mechanism responsible for closed recirculation bubble, which is primarily in 2D configurations. They said that for stronger interactions with a larger separation bubble, downstream mechanism is the dominant factor, whereas for weak interactions with smaller separation bubble or even incipient separation, upstream mechanism also comes into picture. Clements and Narayanaswamy did a review of SBLA for 2D configurations, and they finally stated that there is a research gap in understanding the 3D configurations in general. And similarly, in parallel, there were several works for 3D configurations as well, but all of them failed to give an overall picture of the 3D flow field, which basically has to be still studied for three-dimensional protuberance, three-dimensional configurations in general. So with this, we frame the objectives of the current work. We aim to study the dynamics of 3D SBLI due to a cubical protuberance in this case, by characterizing the frequency associated with different regions in both stream-wise and span-wise directions, and to develop a basic understanding of the mechanism responsible for the shock unsteadiness by carrying out correlation analysis of fluctuating wall pressure, and to quantify the unsteadiness associated with different features such as the separation shock and the shear layer through modal analysis of Leach-Leeren. Yeah. So experiments were conducted in the blowdown internal facility. So here you can see the contoured nozzle followed with the test section of dimensions of cross section 100 cross 113 mm. And the protuberance front face was placed at a distance of 170 mm from the nozzle exit, where the boundary layer thickness was measured to be 7 mm. And this is the cubical protuberance which is considered, which is of 15 mm height. So we chose this to be like twice higher than the boundary layer thickness, so that it is sufficiently higher. So the stagnation pressure of 6 bar is maintained, and the free stream Mach number is 2.87. So we have used time-resolved Schlieren imaging and unsteady surface pressure measurements. Schlieren imaging was done using a photon high-speed camera with a frame rate of 30,000 frames per second. And fluid fast response sensors were used for surface pressure measurements. The pressure measurements were done at 500 kilosamples per second and were filtered at 17 kilohertz, since we are interested in the lower frequency range than this. 8,000 snapshots were used for the modal analysis of Schlieren snapshots, and the dynamic mode decomposition procedure that will be the results of which we'll be discussing is the procedure has been proposed by Kutz et al. Has been used. Yeah. So this is basically the oil flow visualization and the surface static pressure measurements done by my colleague Bharadwaj. So I would like to highlight a few features over here. So in general, for two-dimensional configurations, like FFS, we'll observe a straight separation location. Here we have a curved separation location, which is actually followed by the curved shock ahead of this. And we could see that the streamlines separating from this location basically comes to the protrusion location, and then it recirculates through this. And we observe that it is going till the mean separation location and then turning outwards. So from the static pressure measurements, a significant main feature that differentiates from 2D configurations is the presence of low pressure region over here. So if you track the central line, we have the free stream region and then rising pressure close to the separation location, followed by a plateau region, and then the low pressure region and high pressure region close to the protuberance. So this low pressure region is the main distinguishing factor compared to the 2D configurations, that this low pressure region is basically the result of horseshoe vertex, which will be present over here, spiraling towards the span. So yeah, this is basically the flow configuration, and this is from the RANS computational results by my colleague. So basically, we have strategies with the fluctuating wall pressure sensors in such a way that each distinct location corresponds to a distinct pressure region over here. So if you could see free stream sensor, this sensor corresponds to the free stream region, and then followed by mean shock and so on. And we also did measurements in different span-based locations. Here I have given the results of 13 mm and 22.5 mm. Here we have a sensor placed under the mean shock. Yeah. So this is the Schlieren results. Here we have the unprocessed images, and here are the processed images. This is basically done by varying the brightness, contrast, etc. So this shock put analysis is basically the procedure mentioned by Professor Strieger on the first day has been used over here. So basically we have a scan line which is at a distance of 0.9 delta x from the base wall. So this scan line scans for the pixel intensities, and sudden drop in intensity corresponds to the shock put location. This has been done for all the 8,000 snapshots, and the time series has been plotted over here. So we could observe a dominant frequency of with Strouhal number of around 10⁻², which corresponds to about 870 hertz or so. So this corresponds to the low frequency unsteadiness of the separation shock at the center line. Yeah. So we come to the fluctuating wall pressure results. So here in this plot I have plotted the different pressure spectrum at the different distinct pressure locations as I have shown you earlier. So we observe that the mean shock spectrum is similar to the scanline analysis of Schlieren with a dominant Strouhal number of 10⁻², which is also followed by the low pressure region. The high pressure region has some high frequency content, whereas the free stream spectrum is almost flat, which indicates that the frequency which we are interested in doesn't contain any dominant structures from the incoming boundary layer. So basically, it's flat. So incoming boundary layer has frequency more than this. And there is this plateau pressure region which shows frequencies higher than 10⁻². And there is a local plateau region over here, if we could clearly observe. So this is close to 10⁻². This was earlier reported in the two-dimensional configuration results by Murugan and Govardhan for the FFS case, and also Erangel and Doling for compression ramp case. Yeah. So this is the plot for the 13 mm span-wise line. And we observe that the plateau pressure and low pressure shows some lower frequencies when compared to that of the central line. So this is the spectral results for the mean shock location along different span-wise locations. Basically, Z by H equal to 0 corresponds to the central line, 0.87 corresponds to 13 mm line, and this corresponds to 22.5 mm line. So what we observe is there is the common frequency of the total shock that we have from the spectrum is seen to be around 650 hertz, Whereas some additional high frequencies are introduced at the center line, which is close to 900 Hertz, which also agrees well with this Schlieren results. So we carried out some cross correlation analysis between different regions along the center line. Basically, FS means free stream, MS mean shock, HP high pressure, and PP plateau pressure. So this cross correlation analysis has been done in this manner. Basically, a positive time lag between regions 1 and 2 tells us that the event at 2 follows that of 1. This is the convention that we have used. Basically, we have taken an upstream location and a downstream location. If 2 follows 1, that means downstream follows upstream. So this is the basic convention that we have used for the analysis. And we see that free stream region has very less correlation with the other regions. The values are lesser than 0.06, which basically tells us that this is a strong interaction and upstream mechanism is less dominant over here. And mean shock and plateau pressure region has high negative correlation, so of the order of 0.5. So this negative correlation, what it means is basically when the shock moves downstream, that results in the decrease in pressure at the sensor location, which basically corresponds to a high pressure, a rise in pressure inside the separation bubble, since the bubble would contract. So and vice versa. So the negative correlation basically means that. And this is observed at a very close time lag of 10 microseconds, minus 10 microseconds. So this means that means the strong dependence of the downstream bubble in this along the center line. So this was earlier reported by a few other works, and we also observe that despite the fact that the mean shock location and high pressure location are far apart, we observe a good, reasonably good correlation of 0.2 at a time lag of 130 microseconds. And we also observe that upstream event follows the downstream event in all the cases. That is like the time logs are negative. Okay, so further we did some modal analysis of Schlieren snapshots. We have carried out dynamic mode decomposition, which is basically a spatiotemporal decomposition technique, which arranges the mode in terms of the decreasing order of the frequency content. So what we observe is we could observe some dominant frequencies over here, which is close to 10 power minus 2. All these modes highlighted the separation shock in the spatial mode. So the Stahel number, which I plotted here, is close to 10 power minus 2 as observed from the other results. And we also observed to and fro motion of the shock instead of a flapping motion. This has been identified from the shear layer structures, which is originating from the separation location. So to look into a closer picture, we also carried out the same analysis using a cropped snapshot of 196 cross 60 pixels. And we could observe some shear layer structures which are getting finer and subsequently shading towards the reattachment location. So these shear layer structures always corresponded to a higher frequency side, which is greater than Stahel number of 10 power minus 2. So these additional results I've not mentioned in the paper. So I'll just briefly state it because these were interesting for us. So basically what we did is we carried out cross correlation analysis between the mean shock at different span-wise locations. M0 corresponds to the center line, M13 to the 13 mm line, and M22.5, 22.5 mm line. So what we observed is a positive correlation was observed between all the three configurations, which basically means that on average the shock moves together. It is not like the span moves first, and on average the shock moves together. So also the correlation to M0 decreases as we move towards the sides. For example, if you could note, M13 M0, M13 M0 is basically higher than M22.5 M0. The correlation basically decreases as we move towards the sides. And we also had an interesting observation that M22.5 M13 has a very high correlation with almost zero time lag. We could see some correlations greater than 0.7. So this led us, along with the spectrum of the mean shock location, basically led us to think that along these sides, as we move towards the span, the shock moves almost together with a lower frequency of about 650 Hertz, whereas some additional high frequencies of 900 Hertz comes at the center line. And also with some insights from oil flow measurements, we also did some correlation between the center line high pressure and the different mean shock location towards the span. So this led us to a very interesting result that the correlation basically increases from 0.18 to 0.29 as we move towards the sides. So as I've already shown the oil flow visualization, the streamline comes from the near the protuberance to the mean shock location and then turns outwards. This basically led us to do this correlation analysis basically. So to conclude, the unsteadiness associated with 3D SBLI of flow past square face protuberance has been studied using Schlieren and surface pressure measurements. We observed dominant Stall number of 10⁻², in all the cases, the DMD analysis, the scan line analysis of Schlieren, and fluctuating pressure measurements. The DMD also identifies high frequency modes representing the shedding of the separated shear layer. And we observed that there is this common low frequency of the shock in overall, which is around 650 Hz, with some additional high frequencies at the center. The cross correlation results clearly identify the independence of the shock and bubble with the filtered free stream signals. And we also observed that the shock put and the plateau region are strongly correlated along the center line, which is similar to the 2D observations which were done earlier. Thank you.
Thank you very much. Any questions?
Right. So you said that in the center line there is 900 Hertz frequency.
Yeah.
Which is additional to the 650
Yes,
Hertz,
yes.
which is seen everywhere now.
Yeah.
What is that 900 due to? You would have seen it in the DMD, right?
This 900 Hz, sir. The DMD results basically predicted that frequency only, but it is not. DMD is based on Schlieren. We cannot capture the span-wise things, right? So we couldn't compare that. So it is like span-wise integrated, line of sight integrated information.
Oh, you didn't do focusing Schlieren.
Okay. No, we didn't.
Fine. So if you're doing average thing, how did you get the 650?
650 is based on the spectrums. Spectrum
from
of pressure,
simulation.
fluctuating pressure.
From a simulation. You're going
No, it is based on. It's just the dominant frequency seen in the fluctuating wall pressure spectrum.
You measured pressure on the span
Yeah,
side
yeah,
also.
exactly. Yes.
Okay. So from that, you are telling that there is a frequency there.
Yeah.
But you cannot tell what it is due to right now.
Yeah, exactly. We are further investigating on it. We are taking some more span-wise measurements to arrive at an overall conclusion.
Okay, but it is like all these experiments are done in a blow-down wind tunnel?
Yeah.
Okay. Okay, that's all. Thanks.
So when you do these cross correlations between different, are all the measurements taken in the same run or they are
same run? Sir.
So these sensors that you correlate, they are for one
run.
Because,
One run.
do you have so many culites that you populate them?
Actually, like we did all the experiments using 3 culites only. So that's why you always see 3 configurations and.
Okay, only those 3 you correlate.
Correlate.
Okay. Yeah.
Any other questions? I have one. From your DMD analysis, you said that the shock, you can identify the movement of the shock.
Yeah.
What's the width across which it moves? Because that might also inform other studies, in case you want to resolve.
You mean the width across with the shock moves? Yes. That we have identified the shock put with, we have identified from the Schlieren snapshot itself. We have the final total excursion of the shock, right? So that is depend. Here, I think it is of the order of plus or minus delta x, which is the 7 mm, plus or minus 7 mm.
Okay, thank you.
Thank
you. Okay, thank you very much. Thank you, speaker again. Next presentation in the session is by Nilavasan. It's on the effect of ramp plane vortex generators on a flare-induced shock boundary layer interaction.
Good afternoon, everyone. My name is Nilavarasan, and I'm here to present my research on separation control of over an axisymmetric flared body using microvortex generators. I'm going to present a small excerpt from that. In this presentation, we'll be discussing the effect of particularly ramp vane vortex generators on a flare-induced shock-bound layer interaction. So generally, shock-bound layer interactions are a detrimental phenomena in supersonic and hypersonic flows, and especially in this presentation, we'll be discussing more on the shock-bound layer interaction phenomena that is happening over launch vehicles and missiles. In case of these kind of vehicles, axisymmetric vehicles, shockwave boundary layer interactions will have an effect of buffeting, which happens because of the separation bubble oscillations, which in turn leads to an oscillation of the separation and reattachment shock. So the buffeting phenomena can be catastrophic, especially in the atmospheric flight phase, where the vehicle experiences transonic and where the vehicle undergoes transonic or low supersonic Mach numbers and also undergoes very high dynamic pressure conditions. So in such cases, especially in this particular presentation, we are going to be discussing about the shockwave boundary layer interaction that is induced by interstage flares, which is nothing but an axisymmetric compression corner, and the flow configuration is very, very similar to that of a planar compression corner. You'll have a AD type 6 shock interaction that is happening at the triple point, and you'll have a separation shock and a reattachment shock, the bifurcating shocks from the main shock. And this particular flow condition is very, very similar to what that is being observed in planar configuration. The only difference is that in an axisymmetric configuration, you'll have a three-dimensional relieving effect, and the shock inherently is slightly weaker than the planar oblique shock interactions. So coming to the configuration, we have actually performed both experimental and numerical results. The experiments were carried out in NAL's 1-foot tunnel. And the test Mach number was Mach 2, and with a free stream velocity of 523 meter per second. The Reynolds number was 25.257 into 10 power 6, which is quite, and if you take the model is a cone cylinder flare configuration with the forebody before the flare. If you take it, the total length of the model was 100 plus 280. The cylinder length is 280 and the cone length is 100. Which gives you a total length of 380 mm, which is quite sufficient to get a natural transition. But since we are conducting a numerical simulation, which assumes that the flow is turbulent from the beginning, we have introduced a forced transition. That is why we have put a boundary layer trip at the beginning of the model, and we have introduced a forced transition setup. As far as the stagnation pressure is concerned, the stagnation pressure was 30 psi, and the stagnation temperature was room temperature 298 Kelvin. So if you look at the free stream values, it will be around 3.4 psi, the stagnation pressure, and the stagnation temperature was around 162 Kelvin. The flare configuration, we are having a 24-degree flare, which is quite enough to get a separation that will be enough to study the phenomena very accurately. And we have observed a boundary layer thickness of 5 mm at the juncture without the flare. We do a simulation of a cone cylinder configuration. We have observed a boundary layer of 5 mm at the juncture, at the cylinder flare juncture. And at the location of the insert, at the location of the VG locations, we have observed a boundary layer thickness of 4.2 mm. So with that information, if you go, we have in this presentation, we'll be discussing about the ramp vane configuration, and the device height of the ramp vanes were 2.1 mm, which is 50% of the local boundary layer thickness. And the devices were placed 50 mm ahead of the compression corner. So that amounts to 10 delta. That is the 10 times the boundary layer thickness that was observed at the corner. So the inter-device spacing between the devices were 7.5 H, which allowed us to place around 8 devices along the entire circumference of the model. And this is the ramp vane general geometric configuration, which is a combination of both ramp type vortex generators and vane type vortex generators. And it has an incidence of 24 degree with respect to the flow direction. So we have for the experimental setup, we have used 10 Qlite transducers that were placed in between two adjacent devices. You can see that along the divergent region, we have placed 10 Qlites. 6 of them were placed on the cylinder surface and 4 of them were placed on the flare surface. And we have taken the measurements at 50 kilohertz with a low pass filter of 20 kilohertz. And we have used a 7-point calibration setup. And we have done the check calibration every day during the experiments to confirm that the calibration constants have not been deviated. The standard Z-type clearance setup was used. And we have initially conducted both using a vertical knife edge and a horizontal knife edge, but we prefer to go with the horizontal knife edge because the boundary layer was much better. Boundary layer was much more clearly distinguishable in the horizontal knife edge configuration. The Sclerin visualization were not time resolved. They were only taken at 60 frames per second. We had this limitation, and we were only able to take 50 frames over a time period of 0.83 seconds, and with an exposure of 125 microseconds. So we used a green lamp with a 525 to 535 nanometer wavelength, and we have used a Motion Pro X3 camera to capture the images. So coming to the solver setup, we had a star CCM solver, which is a finite volume based solver. We used a steady state simulation with a turbulence model. The one equation Spalart-Allmers turbulence model was used since it can capture adverse pressure gradients more accurately. The flux discretization was using advection upwind splitting method, and the spatial discretization was a second order upwind scheme. The air was assumed to be an ideal gas with its viscosity being computed using the Sutherland law. So when you come to the computational domain, since the model was placed at a zero angle of attack, we took advantage of that, and we only simulated 1/4 of the model due to the axisymmetric flow field. So the domain used was a cuboidal domain. Along the one of its longitudinal axis, we placed the model axis so that 1/4 of the model was inside the domain. Only 1/4 of the model was inside the domain, and this was the domain that was simulated. So coming to the meshing part, we have done a very predominantly hexahedral grid was used, whereas in some cases polyhedral cells were unavoidable, especially in very complex geometrical situations like in the region very close to the VGs. A very dense surface mesh was put in, and an even denser volumetric annular mesh was provided around the VGs, so that the very intricate flow phenomena around the VGs can be captured accurately. So we used the 50 prismatic cells over the surface. You can see that in the uncontrolled grid here that can be shown. We used 50 prismatic layers within a 5 mm distance. And when it comes very close to the VGs, the prism layers had to be retracted because the VGs had a much smaller dimension than 5 mm. But the region was well compensated by using through the annular volumetric mesh, which gave a very close mesh around the VGs also. So we validated the case, the numerical modeling with the experimental data, time average data from the QLite transducers. We were able to achieve a very good match for both the uncontrolled and the controlled cases. So coming to the results, we initially performed Sclerin. We initially talk about the Sclerin visualization. So you can see that the separation shock stands 12.5 mm ahead of the corner, and you can see that this length was taken as the interaction length. And when you install the RVs, you can see that the separation shock has been pushed behind considerably. And but the main shock angle, which was 41 degree, did not have any change. And this 41 degree value actually matched very closely with the theoretical conical shock relations also. And you can see that there are two shocks. That one is the compression shock, and the other one is the recompression shock that emerging from the RVs, and they had an angle of 6 degrees in between. You can also see that there is a very thicker reattaching boundary layer in the controlled configuration. This could be because of the counter-rotating vortices that are emerging from the VGs. So coming to the more three-dimensional visualizations, you can see that here I have marked the upstream influence with a black ISO line. And you can see there are some mild undulations. And if you go to the streamline visualization, you can see that the undulations more clearly, and you can see a much stronger undulation on the reattachment side also on the flare face. These undulations were, it has been inferred that these undulations are caused by Gottler vortices, and those calculations have also been made. That is, we have calculated the actual Gottler number, and we have also gone with the threshold Gottler number, and we have compared it, and we have confirmed that these undulations are indeed caused by Gottler vortices. When we put RVs inside, we can observe very sinusoidal variations in the upstream influence line, and you can see that there are turbulence. So there are high pressure spots that are being formed very close to the corner on the flare side, and this is because of the shortening of the separation bubble, which causes the turbulence spots being formed along the gap between two VGs. So since the separation region has shortened in between the two VGs, that is where the QLites have been placed so that we can take the measurements, take the unsteady measurements also. When you come to the streamline visualizations, you can see some conspicuous space-shaped patterns that are being developed. And you can see some very well-organized straightened patterns also. This space patterns were developed because of the vortices vortices breaking down the separation region and forming some foci type of singularities. So here you can see the separation region more clearly, where you can see for the uncontrolled case, you can see the undulations caused by the Gottler vortices. And you can see for the controlled case, you can see the spade shape patterns that are very clearly formed. And you can see the foci type of singularities that are present inside the spade lobes, which are footprints of some tornado-like vortices that are being developed. And you can see that the reattachment line has also moved very closely to the compression corner when compared to the uncontrolled case. In the velocity contour at the corner also, you can see that there is a variation caused by the Gottler vortices, and this happens to be a very perfectly sinusoidal variation with an angular wavelength of 36 degrees. And you can see here also there is a small increase in the turbulence separation bubble height along the device center line, but in all other regions the separation bubble had nearly flattened, and on the average separation bubble thickness reduced by 27%. So coming to the unsteadiness measurements from the culites, that is the experimental data, you can see that there is a strong peak of on the RMS or the standard deviation plot at the fourth culite, which was suppressed when the ramp vanes were introduced. And when we had a probability density function that was plotted for the data from the fourth culite, you can see that it deviated from the Gaussian distribution, showing the presence of intermittency in that particular region. The intermittency was further studied using the two-threshold method that was developed by Dolling and Bosniak in 1989. And we actually managed to separate or isolate the shock motions through in the form of a bimodal signal. And we calculated the intermittency for the uncontrolled signal to be around 0.663. And for the control signal, it was around 4 × 10⁻⁴. So this also once again clearly shows that the shock has been significantly pushed downstream because of the presence of RVs. So we went ahead and calculated the spectral and did the spectral analysis for the signals from K4, and we can see that the dominant frequency for the uncontrolled case was around 0.5 to 0.9 kilohertz, and this has shifted considerably to 1.1 to 1.6 kilohertz in the presence of RVs. And when we normalized the frequency in terms of the Strohal number, we can see that the range was very much similar for both the uncontrolled case and the controlled case. The Strohal number was pretty much close to 0.013 to 0.022. So this showed that the Strohal number remained constant while the frequency alone has been shifted. So the frequency alone has moved to higher frequency. So the changes in this flow domain has been predominantly caused because of the counter-rotating vortices that are developed by the vortex generators. And the vortex generators develop these counter-rotating vortices by producing a span-wise pressure differential. You can see the vortices being formed because of the backward pressing step kind of flow that is happening here. That is from the high pressure side region. The flow is happening along the span-wise direction to the low pressure side. And this rolling over motion has causes the formation of a recirculation zone here, which was aligned along the streamwise direction through these glancing shocks. And these counter-rotating vortices are in turn responsible for the changes that were observed in the interaction region. So the vortices can be clearly visualized in the vorticity plot that is shown here. And if you take the relative velocity plot, that is the difference between the uncontrolled velocity field and the controlled velocity field, you can see where the momentum deficit region lies and where the momentum surplus region lies. So the momentum deficit region was found along the device centerline region, while the momentum deficit region could be found along the device gap region. That is why you can see that the shock has been pushed significantly downstream along the momentum surplus region, that is the device gap region, and there are spade shape patterns or some slight early onset of separation along the upstream along the device centerline region. So to conclude, the counter-rotating vortices developed alternate upwash and downwash regions, which caused a significant variation in the flow field. And these vortices in turn interacted with the separation region, forming tornado-like vortices. And there was significant manipulation of the temporal behavior of the separation shock also. We have seen that the shock frequency varied from 0.5 to 0.9 kilohertz to 1.1 to 1.6 kilohertz. So this shows that we can move the shock frequency to higher bandwidths that are much more safer for the vehicle and will be away from structural resonant frequency. So with that, I would like to conclude. Thank you.
Thank you. Any questions? Hi, you did only 1/4 of the domain.
Yes, sir.
So, did you see any correlation between the pressure fluctuations in the one device compared to the next device downstream?
Pressure fluctuation. So it is a steady state simulation, sir. I have not done unsteady
Oh, you didn't
simulation.
do unsteady. Then how did you get the frequencies?
That is from the QLights, sir. That is experimental data.
Okay, in the experiment, did you see that behind the devices?
No, sir.
They are all exactly in phase?
Exactly in phase, yes.
Even when it is, the experiment is done on full domain, right?
Full domain, yes, sir. Yeah.
In the full circle also, there is
Yes.
no off frequency like phase.
We have taken along only one line, sir. The QLights are positioned along only one line. You can see here.
No, only one line.
Only one line.
Device. Not on all the devices.
Not on all the devices. Yes, sir. That should be transverse flow disturbances also. Yes. This has been taken only along the device gap region. If you take along the device center line, the plot will be entirely different.
You did not do that. Right?
Yeah, I did not do that, sir.
Thank you.
I have a question. So what is the motivation for the geometry of the vortex generators?
The geometry of the vortex generator is the ramp vane configuration. So initially you'll have the common geometries that are investigated are either ramps or vanes. So the ramps will be some triangular type of ramps that are being used, and vanes are normally rectangular vanes that are being placed. So the ramps generally are regarded as low performance devices. Their performance is not up to separation control performance. And vanes, when you take them, their performance is good, but they are structurally fragile. So we need a combination of those things. So the device has been designed on that motivation. So this will provide both the structural rigidity and the performance control. These are taken from standard literature that has been found.
Just one last question is, since you have, let's say, some numerical, would you be able to figure out what is say a reduction in drag or any change in drag, vehicle drag because of the presence of the vortex generator?
Vehicle drag, yes, the presence of vortex generators generally increase the drag actually, because you are seeing increase in static pressure. If you see this high pressure spots here, there is a separation reduction, so there is an increase in pressure also, which is accompanied by the increase in static pressure. So definitely there is going to be an increase in drag. I cannot quantify it because the dimensions of the flare was according to the blockage of the tunnel. So this is not numerical work. Yes, I can.
Okay. Thank you very much. Right, so we have the last presentation of this section, and this is the speaker is joining us in online mode. We presented by DB Singh. The work is on comparative assessment of aerospike and aerodisc in alleviation of transonic shockwave boundary layer interaction on a launch vehicle model.
Yeah, so hello everyone. Shall I just let I share my presentation?
Could you just switch the slides to make sure that we can see the change? Yes, yeah, it works.
Yeah, so hello everyone. My work is on comparative assessment of aerospike and aerodisc in elevation of transonic shockwave boundary layer interaction on launch vehicle configuration. So I'm speaking on the introduction, literature review, objective motivation, and we have done this is the experimental work. So I will talk about the test facility and the results and conclusion. So as you know, as two of my previous speaker speaking about the buffet, right? So if you see all these vehicles, when they gone to the initial design phase, most of them encounters the transonic buffet problem. And especially if you see the vehicle like Titan 4B, which encountered the failure, and it was suggested that primarily it may be due to transonic buffet. And you are seeing the Aries configuration where it was reported that vehicle encountered sudden jump in pressure during transonic flow regime. Similar observations are made in the Vega vehicle. And if you see this side on my left, we have a LVM3 configuration, so which also gone through the some configuration change based on this phenomena. So to literature review, if you see the transonic buffet problem in the launch vehicle, it is well reported from 1961 onwards, where first time Charles F. Coe indicated that high steady and unsteady pressure fluctuation encountered in Centura and Able 5 vehicle during transonic regime. Subsequently, they have presented their work on unsteady pressure fluctuation on hammerhead vehicle configuration. In 1963, looking these previous two papers, Chevalier and Robusten, they identified the alternating flow separation and attachment at transonic speed. And this paper become like some criteria for the launch vehicle configuration. We have a report on the NASA where we are fixing the different geometrical parameters which are free from the buffet. We also have a paper on the Erickson saying how this unsteady flow separation can endanger the structural integrity of the vehicle. And then we have a paper on this transonic buffet, which is very common in the airfoil kind of structure by Lee and all. So if you see the throughout the time span, you will find the paper on the different launch vehicle which encountered the transonic buffet phenomena in their initial configuration stage. And we started some work on the generic launch vehicle configuration. And recently we published our work in Journal of Spacecraft and Rocket. And if you see here, interestingly, in 2018, Mr. Panda, he again reconfirmed the work done by the Coe and Newt in 1962, and by putting the large number of collides. So if you see the alternating flow phenomena and presence of large pressure fluctuation during ascent phase of the trajectory is well reported. However, the mechanism to control shock oscillation using passive or active device is not reported well. So research gap, if you see, you won't find a systematic study of the effect of the nose angle, which is the main cause for the transonic buffet. And then systematic study on the shock wave boundary layer interaction. In the transonic flow regime, you will find a good number of references in the supersonic and hypersonic regime. So with this research gap, the motivation of this study is to derive from our Indian space vehicles. Like earlier I said, the GSLV and LVM configuration. See, this LVM configuration initially when it was the cone cylinder junction, later it got converted to the Ojai. So in this payload region, we have found this square wave pattern kind of the pressure fluctuation. And this kind of pressure fluctuation, as it reported in the literature, is primarily cause of the transonic buffet, as it's also indicated by the Chevalier and Robusten. And they noted out this like alternating flow separation and attachment phenomena. Similar phenomena observed in the Ares flight vehicle. So what they observe, vehicle encounter sudden jump in the pressure. So it's like the transonic shock oscillates, and you are finding the subsonic and supersonic zone in the payload region. So objective of the study is to just have a geometrical change of the nose and see what the kind of transonic flow phenomena change is happening in the payload region. So if you see here, this is the 25-degree nose configuration, and there you are finding this transonic shock, which is oscillating in the payload region. So when this shock is oscillating in the payload region, it is causing the structural vibration, and which may cause the damage in the payload or the structural integrity of the vehicle. So the prime objective of this study is to study what is the effect of the nose cones on the payload region flow features. So mechanism of the shock oscillation as it was given by the previous two author. So here, if you see that work by Kessler in 1964, what they suggest, if incoming flow is the supersonic and you have a downstream subsonic flow, then chances are there that this shock oscillates in the vicinity. And this oscillating shock caused the square wave pattern in the time pressure history, which will give you the alternating flow phenomena kind of the scenario. So just I will speak about the model configuration. So what model we have taken for the study? It's a just 20-degree bottle, 1D of the payload region, and it consists of the 25-degree, 20-degree, and 15-degree half-angle cone. So it's a standard cone cylinder bottle configuration. And for the control aspect of this, we have taken the aero spike and aero disc, which is connected on the nose. So basically, this is an experimental study, which we have carried out in the CSIR NL 0.6 meter tunnel. And this tunnel having the test duration of 6 seconds. And on my left, if you see the free stream mark versus CPRMS. So basically what we did, it's like a plot of the CPRMS, free stream CPRMS across all the tunnel worldwide. So if you see, our tunnel is quite tunnel. So it's well suited for the unsteady pressure measurement. So these black dots, what you see. So we falls within 0.015 CPRMS in terms of the unsteady tunnel fluctuation. And this is the experimental model mounted on the tunnel pod. And on the top generator, we have 8 collides. And on the nose, we are having 1 collide. So primarily here in this study, I'm just presenting the work of the 8 collides, what we mounted on the top surface. We also conducted the force measurement where we have used the 6-component strain gauge balance and we measured the aerodynamic coefficients. So if I present the force measurement, so what you are seeing in the plot, basically CN, CPM, and CAT and XCP. So if you see for 15-degree and 20-degree, we have a linear aerodynamic characteristic. Whereas the minute you will go for the 25-degree nose configuration, you are finding the sudden jump in the pitching moment. So this non-linearity caused the jump in your center of pressure, XCP. And similarly, this minor non-linearity is also observed in the 20-degree. So if I talk about the unsteady pressure measurement, what we did in the tunnel. So if you see on the heat shield region, we are having 8 collides. And this particular test, what I am presenting here, it's at the angle of attack 4 degree. So 25-degree nose configuration at Mach 0.94. You see there is the square wave kind of jump in the K1, K2, and K3. That clearly indicates that the shock, which is the lambda shock, is oscillating in this zone, causing the large pressure fluctuation on the heat shield. So this just I'm showing the spectrum of the all 8 collides and for all 3 nose configuration. So ideally, if you see for 15-degree, you don't find any low frequency jumps. But if you see for 20-degree and 25-degree configuration, which are indicated by green line and the red line, you will see where this cone cylinder junction is there. So from there downstream, K1, K2, K3, I just representing in terms of X by D. So X by D 0 indicates the cone cylinder junction. And downstream, you are finding the each collide. So it's like point X by D 0.1, you are having the first collide, and then X by D 0.8, you are having the 8th collide. So if you see the FFT or the frequency signature, it is a clearly indicative that 20-degree nose configuration as well as 25-degree nose configuration versus the alternating flow. So this alternating flow may cause the buffet scenario in this particular configuration. So what we did to mitigate this, we started having a passive flow control device in the form of aero spike and aero disc. So if you see this 25-degree nose configuration, we have placed the aero spike, forward facing aero spike, as well as aero disc. And these two devices are controlling well the transonic shock oscillation. So if you see that your aerodynamic characteristics are linear, you are not finding any jump in the pitching moment. And you have a aero disc is giving a lower drag compared than aero spike. Probable reason is that you may have a low pressure, high low pressure zone, larger low pressure zone in case of aero disc. So we also confirm these findings by doing the Mach sweep runs. So what happens if you fix the angle of attack and do the Mach variation continuously? Because in our tunnel we can do that. So if you see that your x-axis represent the Mach variation and your y-axis represent the pitching moment. So if you do the Mach sweep well below your critical angle of attack, you see that you are not finding any jump in the pitching moment. But if you go near to the critical angle and you do the Mach sweep test, you are finding there is a large jump in the pitching moment when you are talking about the basic, which got rectified when you are having the aero spike or aero disc configuration. We have also conducted some IL flow run. So you can see this, probably it is happening because of these two large counter rotating vertices are sitting on the heat shield region. So basically these counter rotating vertices interacts with the incoming flow and creates this jump in the pitching moment, which is not seen when you are using the control device. So these are this cytograph images. So if you see in the basic configuration, as I said, you are finding the shock at the cone cylinder junction, and this shock is moving almost like a quarter of heat shield length, causing these unsteady pressure fluctuation, which are not there in case of control device. And this control device we optimized with our experimental study, which I'm not presenting here. I'm just presenting only the optimized device configuration. If you see the time pressure history of the Coolite data, so your basic possesses the square wave pattern in the K1, K2 location. Whereas if you see with the aero spike and aero disc, you are finding quite a random signature. You are not finding any higher unsteadiness. These are the FFT plot for the complete, it shows the complete picture where you are having the basic configuration, which is represented by red, and you have a black and green. Black is the aero spike, whereas the black is the aero spike and green is the aero disc. So if you see, there is a large reduction in the low frequency content when you are using the aero spike and aero disc. So with this, I want to also plot the cumulative CPRMS. So cumulative CPRMS basically tells you that at what frequency level, how much is the reduction in the frequency. So if you see, just because generally for Buffett considers for this wind tunnel model, then below the 1 kilohertz. So if you see till 1 kilohertz, there is a large reduction in the unsteadiness by using aero spike and aero disc. Whereas this, if you see the basic configuration, your cumulative CPRMS is almost 0.2, which almost corresponds to around 175 dB. So there is a large reduction in the pressure fluctuation by means of using aero spike and aero disc. So with this, I will conclude my talk. So what we did, basically, we have done the aerodynamic characterization for 15 degree, 20 and 25 degree nose cone geometry. And we found there, because of the shock wave boundary layer interaction, there is a large pressure fluctuation in the payload region, which alleviated by using aero spike and aero disc. So significant reduction on the low frequency fluctuation were achieved by using passive device. Thank you.
Thank you very much. Any questions from the audience? No? Okay. I have one question. So
yeah, please.
It appears from your results
both the aerospike and the aerodisc seem to work well across the range of Mach numbers and angles of attack that you investigated. Is there any downside to this configuration? Can this be considered as a good addition onto?
See, we have tested only for the transonic Mach number. So still we cannot comment on the supersonic regime, what is going to happen. So if really we are interested to use these devices, passive devices for the real launch configuration, we have to characterize for other Mach numbers. Of course, these aerospike and aerodisc are well tested for the hypersonic regime. So where they are using these devices for the aero heating application.
Okay.
Yeah.
Thank you. Yes, please.
I have a question.
Yeah, please.
When you were changing the Mach number during the flow, what was the rate at which you could vary in your tunnel?
See, if you see in our case, these Mach rates are changed based on the flap position. Basically, we are changing the geometrical area. So we have a different choice, like you can change your flaps speed. But looking at our tunnel blowdown duration, like we have a typical only 60-second blowdown duration. So generally we change dm by dt somewhere in the range of 0.01 or 0.02, which is not very close to the flight, but somewhat the range.
Is in the ballpark of flight thing. For low Mach numbers you are considering, the initial acceleration time, it will be probably close.
No, yes. Of course, it's a parabolic curve when we are changing the Mach.
Yeah. So, okay. So, but when we go to higher and higher Mach numbers, but you have not done the experiment, it looks like you're not done for as.
Yes, because our interest was only for the transonic, because if you see this phenomena, transonic buffet is the one which is very critical in the vehicle design in the initial phase.
But what happens to that extra device sitting in the front when we go to high Mach numbers? Will it cause more drag or will it break off? Those things we need to look at, right?
Yes, obviously. We have not looked at that aspect yet.
Yeah. Thank you.
Thank you very much. Any other questions? Okay, yeah, we'd like to thank you once again.
Thank you.
This was the last paper in the session, so we'll come to the end of the session as well. I would like to once again thank all the speakers for the wonderful presentation. And
Thank you, sir. Thank you for chairing the session. So here comes the forenoon session. So here ends the forenoon session. So we'll be meeting back at 2 p.m. So before that, I would like to call upon Professor Jayachandran, sir. Please come here. Hand over a small memento to our chair. Thank you, sir. So let's break for the lunch. Thank you all.
Sir, go to the dais, sir. Go to the dais and look at the camera and speak. You can see Professor Valenta on the lower two displays, sir. The two displays below the dais, you can see there. Professor Valenta?
Yes.
Yeah. So Valenta, they're checking your audio and video. Please respond to the auditorium, please. Can you hear us, Professor Valenta?
Yes. Could you kindly repeat it once more?
I'm speaking from the coordinating desk here, and the participants are waiting, and the auditorium. Please respond to them. They would like to speak to you to check the audio.
I see.
Auditorium, your voice is very feeble. Auditorium, your voice is feeble. It's not bright.
Hello. So we are in the first presentation. I would like to can you show the presentation? Just to check the video. Sorry. Hello. Can you hear me, sir? Something to myself.
Yeah, you're talking to me, yeah?
Yeah. So, recommend first presentation was experience of
Actually, yeah. So sorry, I will re-log in again. I couldn't be able to hear the voice properly. There's a break. The voice. Can I? Yeah. Sure. Hello.
Can you share the presentation?
Yeah, sure. Can you able to see the screen? Yeah.
Just change the slide rather. Slide share. Share the slide.
I still have some audio problem.
Yes. The auditorium audio needs to be brighter, sir, because it's very feeble and it's not bright.
Yeah.
Auditorium, Lokesh, if you're there in the auditorium, please the microphone. Maybe the battery level is low. Change the microphone, please. Sir, move the slides, sir. Mr. Sendil, just move your slides 1 and 2 and on the full screen if all is well.
Yeah.
Okay, no, it's okay. No, just go to the full screen mode and change the slide.
Okay. Let me see what, yeah.
Go down. Yes. Yes, correct.
Yeah.
Yeah, all right.
Yeah.
All right. Okay, so from my end, it's all right. Let's check with the auditorium.
Yeah.
If all is no. Audio is bad.
No, we can't hear you actually. From the
Audio is bad,
auditorium.
sir. மணி அது பாரு என்ன ப்ராப்ளம் பாரு மணி லோகேஷ் அங்க இருக்கறா பாரு யார் இருக்காங்க ஆடிட்டோரியம்ல So just try once removing your mask and speak, sir.
Hello,
Can you
hello.
unmute
Check
Valentine?
test. Hello.
Slightly better,
Hello.
sir.
Hello.
Yeah, this is better. Yeah.
Yeah, better, sir. Please interact, sir. I'm muting my microphone. You can interact with Mr. Sandhu.
Yeah, sure. Senthil Kumar, so you can just stop your presentation. This is fine, sir. We can see your presentation. It's very clear, and your voice is audible.
Yeah. Yes. Okay. Can I stop share? Yeah, sure.
Yeah, stop sharing. We'll let you know.
So it will start. It will start after I think 55 minutes more, right?
Yeah,
So 2
probably.
o'clock.
This is a lunch break, so another 30 minutes or 40 minutes, probably.
Okay, great. Okay, great. Thanks. See you then.
Yeah, please. Professor Valenda, can you hear me? Can you mute Senthil Kumar, sir? Professor Valenda, can you hear me now? Hello?
Okay, I can hear you.
Yeah, we can hear you, sir.
Yes.
Can you share your presentation?
No, I don't see my presentation. No.
Can you switch on the video? Your video is not visible to us. Yeah. We can see you, sir. We can see you. Sir, can you share your presentation?
No. I don't see my presentation now.
Yeah. Take your time, sir. If it is a PDF document, just open it.
Yes. I think you should have it.
Yeah. Just search in the downside, sir. It would the down portion. Can you see the participants link? Can you see below that? You can see the participants. Just click on the screen. Just click on the screen and you'll see green button, share.
Sir, at the auditorium, please. So this is Kannan. Can we ask Professor Valenta to send us the slides, and from here we can manipulate as and when?
Yeah, sure.
That should also be easier.
Yeah. Professor Valenta, can you share your slides to us? Can you send through email? And we will change the slides here. Is that okay with you?
So shall I send my slide? No.
You can send your presentation to through WMail or SIS mail. Okay, sir. We'll get back to you, sir. Just send the mail. We'll get back to you once again. In the meantime, we'll check with the other presenters. Is that okay? Can you hear me, sir?
Yes, I can hear you. So
Please send us your presentation. We'll get back to you. Take your time, sir. No issues.
But how should I send my presentation? Tell me.
Through email. We are communicated to you through email, right? Just attach the copy.
Because you know but I know that you
can anyone from the auditorium share the email ID on the chat so that Professor Valenta can take that email ID and send it directly to them. Mr. Valenta, you should also slightly tilt down your camera if possible. You're not able to see your face. Professor Valenta, just correct, very good. Now it looks nice now. Yeah, perfect, Professor Valenta. That's perfect.
Okay.
Thank you so much.
Okay. But I would like to tell you that just before
Valenta, I am from the control room. Can I send you my email ID?
by email
chat box.
I've just sent you.
Let me tell you one thing.
I just sent you my email ID and see if possible you can. Yeah, there's two email IDs now. SIS-2020@wmail.iatm.ac.in. You can send there. Click on the chat icon there.
But let me tell you one thing. Just before you started checking the previous paper, I saw on the screen the first page of my presentation. So I think you do have it.
Okay.
Please check it.
Yeah, we'll check that, sir. We'll check that.
Just before you started checking this.
Okay.
Yeah, Valenta, Professor Valenta, hello.
Yes.
Yeah,
Yes.
we have the PPT. It seems just wait for 2 minutes. We'll try to share it from here itself.
Maybe.
Hello.
Hello.
Hello, sir. Professor Valenda,
Yes.
we are right now we are trying to share the slides.
Okay.
Hello, can you see it, sir?
Yes. Yes. That's
Yeah.
it.
Right. So we can control that from here. You just tell us next slide. We will change the slide from here. Is that okay, sir?
Could you repeat it once more? So,
Yeah, we will change the slides here. You just need to say next slide.
okay. Okay.
Okay. Okay, sir.
Thank you. Thank you. So,
We'll your presentation will be in roughly 1 hour. We'll let you know, sir. Please be online.
yes. Okay.
Thank you, sir. Thank you. We'll see.
Thank
See you soon.
Thanks a lot.
Sir, can you hear me? Can you unmute Rajshekhar?
Yes, sir.
Hello? Yeah. So yours is the third presentation, I guess. No. 2:40 is the timing. Can you
Yes,
share
sir.
your presentation, sir?
Yes, sir. I have to share a video file or PPT, sir.
PPT.
Okay.
Yeah, can you go to the slideshow and change the slides?
Yeah.
Yeah, it's changing. Yeah, that's the third slide. Fourth, okay. Now it's also okay. It's very clear.
Yes.
Now, do you want to play any videos or animation? Want to try that?
No, sir. Actually, I taken video of my presentation.
Okay.
So some online presentation they require video, so I taken video also. So if you want to play video, I play, or else I have to present. That is also okay.
Yeah, the presentation is fine.
Okay, sir. Then it's okay. No video, extra additional video.
Okay. So we'll let you know, sir.
Yes, sir. I'm waiting.
Third person. Yeah. Thank you, sir. Thank you.
Thank you,
Bye.
sir.
So it's by Manish Suresh Rao and Gautam Hegde. So warm welcome to all the delegates. Here we start the afternoon session in day 3 of 24th International Shock Interaction Symposium, SIS-2022. SIS-2022. So, Professor Sarit P. Satyan from Applied Mechanics Department of IIT Madras will be chairing this session.
Hello, Dr. Sindhil Kumar. So the next presentation will be by Dr. Sindhil Kumar Subramaniam and Konstantinos Kondis. The title of the presentation is Experimental Study of Blast Wave Patterns on Periodic Span-Wise Grooved Surfaces. So you can take 15 minutes to complete your presentation and the remaining 5 minutes for discussions. Okay, thanks.
Yeah. Thank you. I'll share my presentation. Are you able to see this here?
Yes.
Yeah. My topic is experimental study of blast wave patterns on periodic span-wise grooved surfaces. Okay. Understanding shock wave interaction with solid boundaries is important in many applications like health, safety, and transportation. Some common examples are like shock waves through high-speed trains passing under the tunnels and internal combustion engines, an explosion on land or mines where the shock wave interact with the solid surfaces. In this one particular interest is like shock wave attenuation through surface modification. The present research compares different standoff distance of periodic span-wise rectangular groove shape and study their interaction with the incident shock waves. So this is the experimental setup of the study. So we have a shock tube, a small open-end shock tube of 22 millimeter internal diameter, and it's the shock wave is produced by nonal detonating tubing, and we have the groove plate at the exit of the shock tube. The shock tube can take the pointer here. It can move traverse in this direction, so it can provide a stand-up distance. And we have 3 plates flush mounted at different places, and these are connected to like National Instrument data acquisition system, and then the signals it's used to trigger the Shimazu high-speed camera. For this study, we are recorded like a 500,000 frame per second or and 250,000 frame per second. Okay, also we did some acoustic measurement. We made a custom built anechoic chamber and using sonic foam wedges. So we installed wedges on a wooden wall and created a big box. And we use class 1 sound meter from Castle Group. And it can able to do octave band analysis, and it can measure up to the human hearing frequency up to 20 kilohertz frequency range with the interval time of 20 milliseconds. And it has been kept at a distance of 50 D, where D is a diameter of the shock tube. So these are the dimensions of the groove shapes we tested in the study. It's all in millimeters. We tested different shapes, but for this conference, I included only the rectangular shape, a wide rectangular shape. And the location of pressure stands is shown here is also in millimeters. So, okay, we'll start with the Schiller visualization. So here, I provided a wide angle picture of the Schiller visualization. So there are 2 set of pictures. One is for 0 standoff distance and another one is for 1 standoff distance. again, in the experiment, we tested for 0.2 d standard distance and 0.5 standard distance. But due to like our space availability included only these two results. Okay, there are some flow features we can able to see from this. Wait a minute, I try to. Okay, so there are some flow features here. The distinct difference between these two. The one is first the strength of a reflected shock increases for higher standard distance. The reflected shock in the sense like we can see the RI here. So this is a reflected shock. From the visualization, you can see here the strength is obviously increased by seeing in the visualization. So that is the first observation. The second is a formation of max stem. The reflected shock wave and incident shock wave merge at this position and create a max stem kind of structure at a 0D standard distance. But in case of 1D standard distance, since it is spherical, it's kind of reflected like a regular reflection. And the third one is the interaction of vortex loop. Vortex loops is like a circular compressible vortex, which is emanating from the shock tube exit because of the diffraction from the shock tube exit. You can see the dark shadow here, that is a vortex loop. Actually, we shown the sideway picture of the vortex loop. Actually, it's a circular one. This is also moving behind the shock wave, but at a different velocity, at a slower velocity than the shock wave. At 0D standard distance, the vortex loop is interacted with the surface, the groove surface, and because of the friction, you can see it's disintegrated, and within like some 150 microseconds, it's almost disintegrated completely. So the effect of vortex loop is absent and further downstream in 0D, but at 1D standard distance, the vortex loop is free from any disturbance from the groove and just travel through. And the next one is a vortex shedding at the groove tip occurs at lower standard distance. So which means there are small vortex happening at the groove tips. Actually, in the next slide, I will show a zoom in picture of this so we can see it more clearly. But now just here to emphasize on the difference between this 0D and 1D, and the same vortex, tip vortex is absent at 1D standard distance. So the next one, a slightly more zoom in picture of 0D standard distance. So the total time span is starting from like 4 microseconds to 56 microseconds. So in this slide, we are seeing up to 56 microseconds. In the later slide, we will see like what will happen after 50 microseconds. So the first 50 microsecond is like we can see a lot of shock wave interaction happen within the groove surface. So at 8 microsecond and 12 microsecond, we can see it's diffracted at this place, and this diffraction weakens the shock wave here. And at 16 microsecond, the shock wave almost split into reflected shock wave and the transmitted shock wave, and the weakened shock wave incident I1 is still going into the bottom surface and hitting back and reflecting back. At the same time, because of the diffraction here happened at 12 microsecond, we can see there are vortices, the tip vortices started forming, and exactly at 28 microsecond, we can see the tip vortices is like interacting with the reflected shock wave. And between 32 to 56 microseconds, we can see there are multiple shock interaction, like a shock interaction, shock wall interaction, and shock vortex interaction happening here. So it's a kind of like a lot of shock waves interact, and then it emerges into a secondary shock wave from the groove surface. So this goes a primary shock wave and the secondary shock wave because of the interaction inside the groove surface. So if you see the same thing at 1D distance, the angle of the shock entering into the groove surface is completely different. In the previous case, the shock wave entered with respect to groove bottom at 90 degrees, but here it's more at an angle less than 90 degrees. So obviously it produces less diffraction, and because of reduced strength in the diffraction, the vortex formation is also limited. You can see the picture here again. It's up to 88 microsecond. So you can see the shock wave entering into the grooves. You can see the small vortex formation because of limited diffraction, and also we can see how the shock wave get deflected, and it's going away from the free surface. So further we are seeing a visualization from 100 microsecond to 400 microseconds. So the first 100 microsecond, we say there are a lot of shock wave internal reflection, but after 100 seconds, we can see the evolution of vortex, the tip vortex. We can see the tip vortex started at 140, and then it started to develop into a matured vortex, and there is a slipstream behind the vortex. Surprisingly, around like 250 microsecond, the slipstream detached from the wall, and you can see a formation of a secondary tip vortices. There are several theories. The one possibility is one author suggested that there will be a counterclockwise rotation of the secondary vortices that could have created instability in the free stream, which causes to separate. But in this visualization, we could not able to see whether it's the rotation of this secondary vortices. So there is one more possibility that there is a huge the flow come inside and then it trying to go like an upwash of flow. This upwash could have created a pressure differential, and that would have separated the slipstream from the tip. And it's separated and it swings and curl inside the grooves, and there are after the secondary vortices, you can see still more. There are so many tertiary vortices, and there are plenty of vortices which is following. This is possibly due to the slipstream become a transition into turbulence, would have created these small vortices, and finally all these vortices curl into a bigger spiral kind of structure inside the grooves, approximately at 400 microsecond. This is the flow picture at 0D standard distance. But at 1D, as I said before, the shock wave entering at an angle, and it reaches the bottom surfaces almost like a parallel to the bottom surface. So because of that, the diffraction strength is low and the vortex production is low. So there is a small vortices happening in the corner, but also we can see there are even more small strength vortices happening on the other side of the grooves. That because when the shock wave enter into the groove and then reflect back, and it's go like this. So it reflect back, goes like this. So it's diffracted in the other corners as well. So we can see several tip vortices at 1D. So we call it multiple diffraction. So vortex at both corners of the groove wall, and reduction in vortex strength and movement as well. So finally, now we are seeing what happened after the 400 microseconds to up to like around 800 microseconds. So all the vortices matured, and then it's a kind of curl into a bigger spiral here. And after some 600 microseconds, there is no enough momentum. And I think the pressure get equalized between these two, and the vortex spiral vanishes. After 800 microseconds, there is not much thing happening inside the grooves. In case of 1D standard distance, you can see the formation of vortices on all the corners. And in fact, there are vortices on the top of the grooves because of the multiple diffractions. mainly because of the angle of the shock wave entering into the grooves. So now we'll go to the pressure measurement. So before going into the pressure measurement of grooves, first I want to show how the pressure look like for a shock wave from a normal shock tube. This is the flat plate at 0D distance. So we can see initial shock wave. There's a peak is the initial shock wave, and then there's a compression wave, and this is the vortex loop. The vortex loop is like a kind of suction pressure because it's rotating and creating a kind of suction. These colloids are at a different length from the exit of the shock tube. So when the length increases, you can see the distance between the shock wave and the vortex loops increases, and the gap between the shock wave and the vortex loop is filled with the compression waves. The same thing happened here. There is one more thing we need to notice is like the vortex loop. The magnitude of the vortex loop is almost constant in as the distance increases, but the strength of the shock waves decreases because the strength of the shock waves depends on it's expanding into the free space. So obviously it's the strength is getting decreased until the pressure equalizes with the surrounding atmosphere pressure. So the strength of the shock wave is decreased, but the vortex loops, it's since it's a flat plate, there is not much interaction happening with the vortex loop, so it's continued gaining its momentum and continue with the same magnitude of pressure until some distance, like some 10 centimeters. So this is a typical pressure history of blast wave over flat plate. And finally, the combustion products that comes after 800 microseconds. So we no need of this one. These are the pressure history for on this rectangular groove shapes. Seen in the previous slide, we can see a reduction in the peak of the shock waves as the distance increases. So the D is for 1D and the A is for 0D. You can see the peak is decreased. But also, if you see the vortex loops also decreased to one. The vortex loop is decreased at the different standard distance. Also, the vortex loops is decreased at the different colloids. That because of the interaction between the vortex loop to the groove structure. And also we can notice a double, the single peak pressure become double because of incident shock and reflected shock. And the vortex loop is having a maximum magnitude at a 0.2 D distance. And this is because when there is a small gap between the vortex loop to the groove structure, and that gap produces a kind of pathway for the air to flow, and the air gets sucked inside, and because of that it has a higher magnitude. And also we notice the strength of each of the double peaks varies for different standard distance. We can see from this figure the strength is also changing. So by doing this, it's changing this. We are changing the strength of the shock wave using the grooves. And finally, the acoustic measurement. Here we presented from 31 hertz to 20 kilohertz. These 31 hertz are like inaudible range for humans almost. And the peak noise is lowest at there's a low frequency, but it's lasts for a longer duration for up to like 2.5 seconds. But if you come to the other end of the frequency spectrum, it's lasts for only milliseconds, but it reaches up to 100 decibel. Where a peak sound pressure is measured at 118 decibel for a frequency of 1 kilohertz. So here it's reached the peak. The standard distance almost have not much effect on the peak pressure. very little effect, so it's not much appreciable effect. And obviously the settling time is inversely related to the increasing frequency, as we see from these figures. And the slope is more gradual and curved at a lower frequency, and the flow and the slope is more steep and linear at a higher frequency. These are the observations. So finally, the conclusion is we have made some observation like pressure, acoustic, and flow development patterns over rectangular groove surfaces at different standard distance at a Mach 1.35. We observed there are multiple internal reflection within the first 100 microseconds, and between 100 to 400 microseconds, we witness evolution of tip vortex. There is one more thing to forget, like it's since the Mach number is 1.35, so we have a subsonic flow which is like a tip vortices at the groove surface. Probably if the Mach number is above 2, we will have a supersonic flow features at the tip vortex. The shear layer curl clockwise aligning the trajectory of the primary vortex, and the main vortex and tail vortices form a vortex spiral that completely fills in the groove walls. And at 1D distance, we have the diffraction occurs at both sides of the groove wall, causing a vortex to develop in the direction of the flow, and in different places of the grooves. So the direction of the flow and the opposite direction of the flow. And the strength and displacement of the vortex at 1D standard distance are obviously smaller than the lower standard distances. And in the pressure measurement, we observe a double peak pressure, which indicates the presence of a reflected secondary shock waves. It's one of the reasons for the shock wave attenuation using grooves. And in the acoustic measurement, we saw like an increase in standard distance had a noticeable effect at the lower end of this frequency spectrum, but not at the peak noise. So, okay, that's it. That's my presentation. Thank you.
Okay, thank you, Dr. Sendil Kumar. So now it's time for questions.
A nice presentation. I have a couple of questions. The first one is regarding the vertex strength you are mentioning from the Slern images. I'm wondering, how did you estimate the vertex strength from Slern images?
This is just an observation for by looking at the darkness. I mean, the more the dark, more the strength kind of observation, but the more observation can be made in the pressure measurement.
And another,
just by seeing the dark. Yeah.
Usually the strength is estimated from the quantitative techniques like PAV. And a follow-up, you used an anechoic for the sound measurement.
Yeah. Before going that, before going that, I just would like to mention that we planned for a PAV for this one, but the shock waves are not much visible in the PAV. Only the vortex actually can be seen. So we have a plan still for the vortex disintegration to have a PAV measurement. Yeah.
So the next question.
The next question, please.
So you use an anechoic chamber, am I correct?
Yeah.
For sound measurement.
Yeah.
I'm wondering, usually the anechoic chambers cannot avoid the shock reflection. But how did you estimate the sound pressure levels?
It's only the, we are measuring the acoustic signature, isn't it? Like, we are not measuring the shock wave strength. So how the
No, what I mean that is your measurement will be contaminated by the reflection of shocks from the anechoic chamber walls itself.
I have not thought about it, because my guess is that the foams should not reflect the shock waves. That's what the expectation is.
It won't reflect sound waves, but the shock waves will be reflected.
I'm sorry about it. I will think about it. I'm not sure.
Any other question?
I have two questions.
Yeah.
One, I don't understand what is new in this study. All the features that you have shown us something that's already known, right?
Yeah, it's a. There are few things which is not in the literature is about the separation of this slipstream, which I haven't found in any literature so far. So that need to do some. We need to do more study to know why the slipstream it swings its tail upwards and then it's curl back, which I think it's kind of interesting in the study.
But that is again discussed in various configuration of nozzles and other things. Not precisely this kind of wall structure that you have, but in other structures, how is that slipstream going to be different from what you see here?
I'm sorry, I don't understand the question. Like the nozzle. I mean,
No, there are other structures with protrusions like this, which creates slipstreams. And this seems to be similar to that. So from the fundamental point of view, I don't see any difference.
What I from the lecturers survey, what I know is like the slipstream is to attach for a long period of time from the. But because of the groove shape is smaller, so I think it's get separated. That's what my understanding is.
Okay. The second question I have is this dimension that you show for the structures. How did you arrive at this dimension? 7.
Yeah.
Anything
Actually, it's we are carrying out. Sorry. Yeah, we are carrying out.
Sorry, proceed. Yeah.
Sorry. Yeah, it's been already. We are studying for yeah, we are taking a source from previous experiments, previous numerical studies. So there is not a specific importance to this dimension.
It has nothing to do with any characteristic length scale of the problem.
No, no.
So it's randomly.
It's not random. Like we are continuing a study from previous numerical studies.
Okay, so the previous study had some random dimension then.
Yeah.
Okay.
Okay. So, Dr. Sindhil, I have one question just before we conclude. Yeah. How big is your this chamber? What is the size of the chamber?
The anechoic chamber?
Yeah, yes.
It's you can say like a 3 or 4 meter cube. It's a small one. Like a person can stand inside because we created like a custom build only for the study. Okay. It's not a professional one. Yeah.
Yeah. Yeah, because looking at your Schlieren pictures, no, I see some reflected shocks, which is not.
Sorry about the Schlieren was conducted not in the chamber. Oh. There's a separate study. So.
Okay. Yeah. Okay. Right. So this you did all these experiments only at a particular Mach number, right? 1.35.
Yeah. So 1.35. Yeah.
So did you try with any other numbers? Any other speed?
Actually, we are trying with the different shapes, so we are keeping the Mach number constant.
Okay, so but this was restricted because of your shock tube limitations or anything, some other reason?
No, it's not limited. We can go up to 1.7 based on the nodal tube length. That's the only limitation.
Okay. Okay. Good work. Thank you, Dr. Sindhil. So let us congratulate you. Thank you very much. Thank you.
Thank you.
Sorry, I had to leave for an emergency. So the next talk is from Professor Valenta. Is he online? Professor Valenta?
Is there online? Professor Valenta?
Yes.
All right.
Yes. Professor Valenta, good morning. This is Rajesh. Are you able to hear me?
Yes, I can hear you.
Yeah,
Yes.
yeah. So the next talk is from Professor Valenta, and the co-author of this work is Slovica. So he's going to talk about the detonation dampers for decks transporting gaseous fuels. Professor Valenta, you can start.
Yes. Thank you. So I will be talking about detonation dampers for duct transporting gaseous fuels, which the transport of gaseous fuels is nowadays quite important problem in modern societies. And may I have the next slide, please. The next slide, please. This transport is safe if pressure inside the pipe is higher than atmospheric pressure. Otherwise, atmospheric air may leak into the pipe because there always may be some places where with small holes. And this may lead to burning and detonation inside the pipe. This is very dangerous because this may lead to burning and detonation. And detonation must be extinguished if it happens. Standard device for the extinguishing detonation is a matrix of narrow channels extinguishing flames by cooling hot gas through contact with cold walls. Such matrix is placed across the transporting channel. Burning gas may also be cooled in expansion waves in place where channel where damper channel increases. And I'm going to next slide, please. I'm going to compare two damper channels, one classic with constant cross-section, and the other one with varying cross-section, like in this picture. Next slide, please. The results I'm going to present were obtained with direct simulation Monte Carlo technique. The assumptions made are as follows. Gas consists of hard sphere molecules. Part of these molecules carry some internal energy, which may be transferred into kinetic energy of molecular motion during collisions with other molecules. Maxwell's model of molecular interactions with walls has been used. Molecules reflect from walls either diffusely, that means with
with maximum possible exchange of energy, or specularly, that means with no energy transfer. Microscopic character of gas wall interactions depends on accommodation coefficient alpha equal md over n, where md is number of molecules reflected diffusely, and n is total number of reflected molecules. Next slide, please. Molecules exchange energy and tangential momentum with walls through diffuse and reflections only. Therefore, the factor important for the flow is the ratio of number of molecules reflected diffusely to total number of molecules in considered area. In wide channels, this ratio is smaller than in narrow ones. Since calculations, DSMC calculations must be performed for narrow channels, because otherwise, if we try to calculate channel of sufficiently large dimensions, then the calculations would take enormous amount of time. So, but artificial decrease of number of molecules reflected diffusely, which means decrease of the accommodation coefficient as, makes it possible to obtain in a narrow channel the flow pattern similar to that in wide channel. This is the method which I was using in my simulations. In the important investigation, the simulated channel width was equal to 70 mean free paths. That means about 5 micrometers at the assumed value of alpha accommodation coefficient equal 0.01. This produced flow picture corresponding to real channel width about 0.5 millimeter, which is the value commonly used for in real detonation dampers. Note that accommodation coefficient at worst of real channels is close to alpha equal 1. Next slide, please. Now here, I think I don't have to to describe the idea of making these simulations. So I would like to ask for the next slide, please. Next slide, please. But now I'm going, since detonation may occur both during the flow through the detonation damper and if there is no flow at all too. So I first calculated flow parameters during the stationary flow across the damper tunnel. Here you can see the diagrams of velocity, pressure, density, and flow rate in the channel. In the channels I presented you at the beginning. Look at the diagram of pressure. We can see that channel 2, that means channel with varying cross section, has the pressure drop along across this channel is about twice as large as along the straight channel. So it's certainly some loss if we have to use such damper channels. But I think I will show you that it is certainly worthwhile. Next slide, please. Here, I'm in these two pictures. I'm showing you the detonation inside inside my damper channels in channel 1. That means without variation of section. You can see that these curves correspond to temperature distribution inside in gas, showing how detonation wave proceeds along the channel. You can see that the intensity of that means pressure jump, temperature jump across the detonation wave decreases only very weak along the channel. So such channel is practically unable to extinguish the detonation. Now, next slide, please. Next slide. Here, I'm showing you the similar picture for channel number 2 with variation of cross section, and you can see that intensity of please one slide back. If you Okay, thank you. Here you can see that the intensity of detonation certainly is getting much weaker toward the end of the channel, and close to the end of it, detonation actually splits into relatively weak shock wave, and then you can see and some mass of hot gas following the way the shock at certain distance. So the situation seems to be much better, but unfortunately, this weak shock wave increases its intensity with time. Why is it so? Here in this page, in this picture, I'm showing you the diagrams of percentage of flammable component correspond. The curves correspond to the curves here in this left picture. You can see that something happens here at the end of the channel. That means the flame suddenly appears here. So, and this explains why the shock wave increases its intensity. Next slide, please. Here, the picture is quite similar to the previous one, but the shock wave at the end is weaker than before, and its intensity does not increase. So we no flame can be seen here in this picture where so I think we may expect that this channel will extinguish the detonation wave. So I think this is so may I have the next slide, please? Next slide. So these are the conclusions which may be drawn. First, the proposed method of this DSMC simulation of flow in channels of detonation damper was found to work also for channels of technologically acceptable dimensions, relatively wide. Presence of abrupt changes of cross-section in channels of detonation damper increases efficiency of damping. In channels of technologically acceptable dimensions, its influence is stronger than influence of cooling by the walls. which it could be seen there. And in wide channels, the increase of flow resistance due to presence of changes of cross-section is significant. However, taking into account the increased efficiency of damping, the net gain seems worthwhile. That's it. That's all what I wanted to present you. Thank you very much.
Yeah. Thank you, Professor Valanta. From the audience. There are no questions. Let's thank the speaker again. Professor Valanta, you can close the PPT. Okay, let's go to next paper. Next paper is by Jayapal Rajashekar, Teho Kim and HD Kim from Andong National University. It is on the computational analysis of explosion at air, water, and interface.
Yes, sir.
Yeah,
Thank you.
Jayapal,
Yes, sir, I'm here.
Yeah, please.
Yes, sir. Thanks for introduction. Good afternoon, everyone gathered here. I am Jayapal Rajashekar from Andong National University. I'm working under Professor Hidung Kim, and my topic is computation and analysis of explosion at air, water, and interface. And my overview is introduction, literature review, research motivation, numerical methodology, CFD and analytical results and discussion, and conclusion. And my introduction is, if an explosion happens in water, it approaches two kinds of boundary. The first boundary is free surface, and the second boundary is structure. So if it approaches the free surface, once the shock wave reaches the interface region, that is air-water interface, it tries to transmit, but due to acoustic impedance difference between air and water, the shock wave not able to go in that magnitude. So it reflects back, but this reflection is in the form of expansion wave, results in cavitation, and this cavitation reloading has same magnitude as that of initial loading, and it has significant influence in the free surface. Whereas if we take the next case, that is next boundary, that is structure. In the structure case, once the shock wave hits the structure, it reflects back and transmit considerably. If the shock wave is considerable, it results in damage to the structure, and cavitation also reloads here and reflects back. So within the same medium for the explosion, same explosion, depends upon the boundary, the results were different. So it's a next case, that is explosion in air. For explosion in air, once the explosion happens, it approaches the air-water interface, and as I said before, the acoustic impedance difference between air and water is so high. So this water surface almost acts like a solid, not like exact solid. So the transmission is less and reflection is more compared to the top previous case. And the shock wave propagation in air is slower as compared to that of water. That is due to nature of air and water. So I referred some literature review about this study. I referred the explosion at water surface by Benixlo, and I mainly calculated analytical calculation using RH coal underwater explosion, and referred many other papers. I found that most of the researchers were interested in explosion in air and water. Until date, very few works has been done in the interface explosion. So my interest goes towards interface explosion and try to compare it with air and water. So interface explosion research involves complex physical processes such as explosion, cavitation, fluid interaction, and shockwave propagation. And my interest is to find fluid interaction and shockwave phenomena near the water-air interface. And the application vary from the depends upon the strength of the shockwave. Like if the higher the strength, like explosion or military applications were there. So underwater explosion, missile design, or military and naval applications were related to that. And to mitigate the shock wave, it is applicable in mining industry. And for medical industry, it is related to kidney stone removal or even cataract surgery nowadays as the application related to this study. So depends upon the magnitude, the applications were different. And my objective is to understand the shockwave propagation characteristic near the water-air interface and to investigate the attenuation of shockwave in different medium of explosion and to understand the fluid interaction near interface. So this is my computation domain. And my computation domain is 12 meter by 10 meter I have taken. And in this, I tried to solve 3 cases. First case is explosion in water, and second case is explosion in air, and third case is explosion at the interface. And I modeled this computational domain using air as ideal gas equation of state and water as polynomial EOS, and explosion as Jones, Wilkins, and JWL EOS. And I use the charges TNT. And for validation purpose, I used the analytical results from underwater explosion because very few researches were done in this case. I want to compare 1 kg of TNT explosion analytical results with my CFD. So I didn't get much papers. So I calculated for 1 kg of TNT, how much the pressure or shockwave propagation is there from RH Cole's underwater explosion. And this is my result at the pressure contour of shockwave propagation at a time of 1 millisecond and the shockwave propagation in water at 2 milliseconds. And I try to compare at a distance of 2 meters from the charge. I try to compare my CFD and theoretical results, and the peak was reasonably matched and other regions also reasonably matched. And at figure 6, I try to compare peak pressure of all the points, like from 0.5 to 4 meters. I try to calculate the peak pressure in CFD and theoretical calculation. It almost matches reasonably well. So I try to proceed with my simulations. And this is my first case, that is explosion in air. In this case, the explosion happened at the distance of 1 meter below the interface. Once the explosion happened, the shock wave approaches equidistant in all direction. So it reaches the air-water interface. Here, the shock wave tries to goes outside of the interface, but as I said before, due to acoustic impedance different, the shock wave not able to go outside in that same magnitude and reflects back as expansion wave. This sudden reflection of expansion wave results in sudden negative pressure, results in cavitation. Also, the transmitted shock is weaker in strength and moves at a slower pace. And I quantitatively try to show that result. So I created a monitoring point near the interface region, 3 monitoring points near the region. Here we are able to see the pressure and time graph of explosion in water case. So here we see the explosion. This is incident shock, and this is incident shock. Here we see it goes in the magnitude of 100 MPa and goes at the other point at 80 and 65 successively. Once it reaches the interface region, suddenly from nearly 65 to 70 MPa, it goes towards the negative. So the sudden transformation was due to the presence of interface, and the sudden transfer from positive to negative phase is said to be, I mentioned before, as cavitation, and we are able to quantitatively verify that. And this, I try to show the transmitted shock wave also. For that, I just try to draw a wave diagram of this. The explosion happened at a distance of 4 meters. So incident shock goes in the water medium, that is not a problem. So another side, it goes towards the air region. This I consider the center as dotted line as water-air interface. And once the shock hits here, the water reflects as expansion wave, we are able to see here. And the transmitted shock wave gets weaker and propagates the smaller distance, that is around some 0.25 meter for the total time of 2.5 ms. So that is the thing, it happens. So transmitted shock get weaker due to the presence of interface there. And this is my second case, that is air explosion. So the same explosion, only the medium is different. So the explosion happened above 1 meter above the interface. So in that case, the incident shock is, as I said before, there is no problem. It goes there. And another part of the incident shock move towards the air-water interface. It is facing the interface. As I said before, the acoustic impedance difference between air and water is different. And water almost acts like a solid body. So the reflection of shock wave is considerable here. And transmission also, even though the transmission of shock is very minimal due to nature of water, the shock propagation is higher there, and magnitude is comparably higher in water region. So to quantitatively measure that, I created a monitoring point in air side and water side. Air side, 3 points I created a monitoring point above the interface, and below the interface also created 3 monitoring points at a distance of 0.5 meter from the interface region. And this is an incident shock. So once the explosion happened, the incident shock moves from here to here. And incident shock has a magnitude around 9. So once the incident shock goes near the interface and touches the interface, it tries to reflect and transmit. This is a reflected shock wave, but this time the reflected wave is a compression wave. Last time, due to the water medium, the reflected wave is expansion wave. Here the reflected medium is compression wave, and as a reloading of similar to that of incident shock wave. Whereas in the other side of the same case, where in the water side, the shock wave, once it touches the interface, it experiences, all monitoring points experience a precursor shock, as well as the shock wave is compressive wave as expected. And this is a wave diagram for this case. So the explosion is happen at 0.6 meter, and the shock wave hits the interface region. The transmission and reflection is almost similar compared to the previous case. And this is the third case. This is explosion at interface at time. The explosion happened at the interface. So for visualization purpose, I try to patch 2 diagrams in the same patch so that we are able to see at the same time of 1 millisecond the shock wave propagation in air and water. We are able to see the visualization purpose. I did this. So once the explosion happened at the center, the shock wave proceeds in the air as well as water. Here the reflected wave from interface also propagates in the air region. So these are all the monitoring points in the air region as well as water region. So in air region, the shock reaches the maximum pressure and attenuates in all 4 points. Whereas inside the water, there is some small fluctuations were there. This is not said to be cavitation. There is some fluctuation in water because the explosion happened at the interface. That is what I'm able to understand. And as far as wave diagram is concerned, explosion happened here, and at the explosion happened here, and the incident shock moves in both the direction in this case. And at incident shock moves gradually in water medium, whereas in the air medium, the incident shock initially propagates at a higher speed, and after that it attenuates faster in air compared to that of water. So that is the thing we are able to see. And I just try to compare all my results. So acoustic impedance is a major role here. So I try to calculate with the Euler number because I want to predict all 4 cases in the same graph. So I use Euler number for the purpose. And from this graph, we are able to understand that air explosion attenuates faster and the magnitude is very low. Whereas in the interface, air side of interface explosion, the magnitude is little higher. This may be due to interface reflection of shock wave at the interface region. And water explosion has a higher magnitude, and this also attenuates at the similar pattern. Whereas water side of interface explosion also faces the attenuates in the same pattern, but at a lower magnitude due to the effect of interface, air-water interface. And my conclusion is, in water explosion, the shock wave reaches the interface and reflects in water as expansion wave that results in cavitation. Whereas in the air explosion, the shock wave near the interface reflects and transmits as compression wave. The strength of incident and reflected shock is of equal magnitude. Whereas in interface explosion, the shock wave propagates in both in air and water. It propagates and attenuates faster in air compared to that of water. And in shock wave in air side of interface explosion is strong, significantly stronger than air explosion due to the reflection of shock wave in water air interface during explosion. And the water air interface and cavitation plays a major role in the characteristics of shock wave propagation in air, water, and interface explosion. Further, I am extending my study towards fluid structure interaction. Thank you, sir. Thanks for your attention.
Thank you, Jaipal.
Yes, sir.
Questions from audience?
Yes.
Okay. 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 Thank you, sir. Yeah. Can I ask a question?
Uh, uh, can you please wait?
Okay. Okay. Yeah.
Jaypal, are you able to hear us?
Yes, sir.
Yeah, there's a question from audience here.
Yes, sir.
Yeah. Can you go to the first slide?
Yes.
No. Yeah. No, next slide. Next one.
Okay.
So on the right side, you have put image.
Yes.
Does the shock wave, that means is it behaving like an electromagnetic wave? There will be a
No, sir. Actually, if a shock wave comes in this angle, it may refract, sir. But for my case or my experiment, this diagram won't suit exactly. If it comes in this angle, it may get refracted and transmit into the water. But as far as explosion is concerned, it comes straight and goes straight. Only transmission is there. No refraction is there, sir.
Yeah, because to have a refraction, there are a lot of
Yes,
physics
sir.
to be factored. Yeah.
Yes, sir. Understand.
Doubt that there will be a refraction. Okay.
Yes, sir. Yes.
Thank you.
Thank you, sir.
Yes, sir.
So any questions from the online audience? Someone was asking a question. No? Can you show me the Zoom window?
Yeah. Excuse me. Can
Yes,
I
sir.
speak?
Yeah, please,
Can I-
please. Please.
Okay. Yeah. Yeah. Thank you, sir. Yeah, for your the wonderful report. Yeah. And my question is, your result is only from the numerical simulation,
Yes,
or
sir.
from numerical simulation? Yeah.
Yes, sir.
Okay. Can you have you done some experiment or compare to other scholars' experiment? Yeah.
Here I used a charge of TNT for explosion. The TNT I used is 1 kg of TNT, sir. But most of the experiment were did in grams. For example, this first paper, explosion at water surface, was did at 5 gram of 5 gram of TNT, sir. So I'm not able to get papers for 1 kg, nearly 1 kg of TNT explosion experimental papers. So I try to study and compare these kind of results for smaller magnitude cases. Because explosion has some limitations also. So for experiment, we can't explode 1 kg of TNT. So this is computation. We are able to do that. There is no limits for computation. So we try even 1 kg, 10 kg, 100 kg also we are able to try. But for experiment, there is some limitation. So most of the experiments were related in grams of TNT. Like the charge they used at the center is 5 gram, 10 gram. Maximum is 50 gram or 25 gram, in that range only. Maybe some American military report, or in that cases, like from military bases, we get a report manual in kgs of TNT explosion.
Which report? Which one? And you the American? Which one?
Analytical, I tried using underwater explosion by R.H.
This book. Okay. Okay.
Yes, sir.
And,
From that book, I using the formulas, I tried to calculate and compare my results.
Okay. Go to your result. The final. The last slide. The last slide.
Last slide. Okay.
Last slide. Okay. The conclusion. Okay.
Sorry.
Conclusion. And the conclusion about you resulting in the first one, and resulting a cavitation. Okay. Have you get some bubble? Yeah. The bubble. Yeah. The bubble. I think if you put the charge in the water, I'm sure there's some bubble in it. Yeah.
Yes, sir. Yes, sir.
Bubble.
You are asking about. Yes, sir. I understand. You are asking in general if explosion or any kind of disturbance happen in water, bubbles generated from there. But we are this is due to cavitation, bulk cavitation due to difference in interface, but that small bubbles due to disturbance not able to predict using commercial software, sir. And software limitations for that.
And I think if you put the charger more deeper in the water,
yes,
the result different. The result different.
Oh, okay, sir. Sure,
Yeah,
I try future cases as per your suggestion. I try, sir.
And if there's some, if we can see some bubble, maybe there's also maybe we can see the collapse of the bubble. If the collapse bubble happen, maybe there's some jet. Yeah. So the jet will result in the most serious damage. Yeah.
Okay.
Okay.
Yes, sir. Thanks for suggestion.
Okay, I come from China, Beijing Institute of Technology. I come from China. Maybe we can contact you. Where are you? Your email address?
Yes, sir. I will share my email address. I'm from South Korea, working in South Korea, Andong National University. I will share my details, sir, to the conference team.
Email. Where's the email address? Where?
I didn't mention here.
Okay.
I will share my email address, sir. Definitely.
Okay. Tomorrow morning, the first one is my report. Okay. Maybe you can see you can get my email. Yeah. Okay.
Yes, sir. Yes, sir. I will email you.
Yeah.
Okay.
Thank you, Dr. Sun. Yeah, we'll meet you tomorrow. Yeah.
Yes, thank you. Thank you. Yeah.
Thank you. Any other questions?
I have a question. Like I have a couple of questions. First thing is, what model have you used?
What
model have you used to model all the underwater explosion?
Yeah, I modeled air using ideal gas equation of state and water using polynomial equation of state, and explosive using JWL, and the total simulation I used commercial software Autodyne.
Okay.
ANSYS Autodyne.
Like how many phases are you solving, or is it a single phase and with an interface, or what is the model?
Yeah, 2D interface, 2D planar.
Okay, how many equations are you okay, which how many phases?
Phases in the sense air, water, in that way, or you are asking about like in fluent, you are asking the model like a turbulent model, what kind of turbulent model it is?
No, that's not the question. The question is, in your model, how many phases are there?
Yeah, see, as you see, 2 phases, air and water with interface. 2D. This is 2D simulations.
Okay, fine. So since you told 1 kg of TNT, what is the volume it is occupying?
Because it is a 2D, I converted it as a sphere by 4/3 pi r cube, and I take it as surface area, means cross section. 4 pi r squared. Yeah.
What is it? I mean, how much have you taken? What is the radius or dia of your?
I think 0.0269, something in that way, in meters. 0.0269.
Okay.
I'm not sure. It is in that range.
Okay.
Very small.
Understood. Now, the thing is, what boundary condition have you used?
Here I used transmitting boundary to avoid reflections from shock.
Okay, fine. Yeah, okay. Since it was not mentioned, I just wanted to ask that.
Yeah.
The results where you have shown for the explosion at the interface. The other one. Blast wave. Contour plot.
Slide 15.
Oh, sorry. Okay.
Yeah, here. So once this is now I understand this is the blast wave that you have represented.
Yeah.
So my doubt here is when it is blasting at the interface, the speed of sound of air and water is different. In water, it's why am I not seeing that difference in the rate at which it is propagating in the two mediums?
Yeah, if I present only the water contour, means water side contour, if I this contour I tried to present using patches, means the top side is air and the bottom side I neglected, and bottom side as air, That is the difference in label you are able to see. The top you are able to see in the air side, that is around 15 bar, that is 1.5 e power 6, whereas in the water side you are able to see 4.1 e power 7. So that is around 410. So that is the reason I try to patch that.
Oh, it's patched.
So without patch, if I show what the water case, you are able to see only the water case and not able to see the air side explosion shock wave.
No, in XT diagram it is clear, no?
Yes, sir. With the XT is clear.
Thank you.
Thanks, Avi.
And I have another question that if you use non-ideal explosive such as aluminized explosive, maybe the result is different. Yeah.
Yes, sir. Yes, sir. Thanks for your suggestion, sir.
Okay, maybe in the future you can use aluminized explosive. Yeah.
Yes.
Any questions from audience? Okay, if there are no more questions, let's thank the speaker again. Thank you, Jaypal.
Thank you, sir. Thank you.
We'll go to the next talk. It's an offline talk from Manish, Suresh Raut, Harish, Rashid Verma, S. Gopalakrishnan, and Jagadish. The speaker is going to be Manish, no? The title of the talk is Blast Wave Mitigation in Novel Bio-Inspired Inhomogeneous Structures.
Hello all, myself Manish Raut. I am a PhD student in the Department of Aerospace Engineering at ISC. My PhD supervisor is Professor S. Gopalakrishnan, and I will be presenting our work about blast wave mitigation in novel bio-inspired inhomogeneous structures. So for this work, we collaborated with Professor Gopalan Jagdish and his student Harshit Verma, and also Mithal Patel is also our co-author. So blast wave is an increased pressure front, which is caused due to sudden explosion or very large local energy deposition. Marine and aerospace structures, mainly in defense, needs to be designed to mitigate fire shock generated due to blast loads. Early attenuation of blast wave severity reduction of the damage, structural resistance of the structural resistance to the extreme loadings are the main objectives which are looked for when we do this R&D in this area. So, earlier work on this topic was started with development of sandwich plates with sufficiently strong cores, where it was found that they behave better than monolithic plates that have same material and weight. Later, like some core materials impregnated with some fluid, glass beads, and tough volcanic rock were investigated for these kind of applications. Also, granular media that is made of alternative ensembles of beads with high and low elastic moduli of different masses were considered, where it was found that they trap energy and shock, they disintegrate the shocks. Later, recently, novel materials like metamaterials, which are and the resonance structures, which are basically which shows properties which are not conventional, which cannot be found in nature. Basically, the band gaps and all exist in this kind of structure. So these structures were also explored for blast mitigation problems. External measures like using obstacles based on geometry that can trap shock waves and spraying of water droplets in a confined geometry were also investigated for this effect. Like this spraying of water droplets can be seen in the scenario when a space vehicle is being launched from a launch pad. The water droplets and water is sprayed over there. Alongside this research in the conventional domain, people ventured into the bio-inspired research as well. So, inspired from nature, various bio-inspired structures were investigated. First of them is the nacre. So,
Niagara is basically they call mother of pearl, where when they looked into it at macron level, they found that the structure, the way material is arranged, is a brick by brick arrangement like this. So they investigated this kind of structure. Next comes the Bulligand inspired bionic structure, which is basically a layer wise, this kind of arrangement of structure. This is found in sea animals like mantis shrimp, where like that mantis shrimp hits very hard with his club. That club structure, the material in the club structure is like that Bulligand structure. So these kind of structures have been also explored for shock mitigation and blast mitigation problems. Another another creature which is like very interesting is the woodpecker. Woodpecker remains unharmed without any TBI, despite any facing the G forces above 1000 G repeatedly a few thousand times daily. It is not like even one time. It faces it daily 1000 times. So biologists have found out that the outer layer of there are three layers of the beak has three layers, out of which the outer layer of the beak has adaptive wavy sutures between the keratin scales, which are not found in that level as can be seen in this figure in other birds. So these wavy suture interface are also found in other applications in nature where there is need to handle compressive stresses and some impact loads. So based on this study or observations from the observations, the authors of the paper, we recently did some studies considering this as inspired from this. We consider some waveguides with this kind of profile and carried out longitudinal and flexural wave propagation. So for those studies, we considered some waveguides of this kind, where the geometry is described, geometry is characterized using these equations. So from those study, we found out that some configurations, if you consider like this, we call it 1C 5X 1C, where the material arranged in this way. You can see from these plots that the magenta color plot has lower amplitudes and the delay in propagation compared to the black one, which is a fully straight. So based on these studies, we decided to take the specimen for use in a real world scenario. Similar studies was done for a flexural case as well. So now to go into, now to consider them in real world application, we cannot simply consider an elastomer because an elastomer will buckle at low critical compressive loads due to like their low instantaneous and long-term relaxation modulus. It can also become unstable in creep phenomena as well. So though the buckling is reversible, because in metal once buckles it is gone, but in elastomer it can be reversed. But this phenomenon, but still we have to make it stiff. In nature also, in woodpecker, the suture structures are surrounded by high mineral content, hard materials. So we need to arrest the buckling phenomenon. So instead of taking it just a sole elastomer, we stiffen it using two aluminum plates, which are just kind of sandwiching the elastomer. So the rubber. So there are two things. One thing is we are modeled in FEA. We got results in FEA, and also we did experiments. So to model this in FEA, we need a like large deformation model, because rubber-like elastomers exhibit large deformation with nonlinear stress strain curve because of diffusion of free chains and nonlinear deformation of the cross-linked polymer network. So usually they are modeled using finite strain viscoelastic constitutive models. Here we have used the Ardabois model, which needs just two material constants. This is the nonlinear hyperelastic model. And so to model the viscous nature of or viscoelastic nature of the polymer elastomer, we use the three-term Prony series, which is called which is expressed like this. So the modeling is okay, but we need the material constants for this model. So these models, the material parameters for these models were obtained from experiments using carried out by carrying out uniaxial, biaxial, and planar shear test and relaxation test on neoprene rubber with 50 shore hardness, shore A hardness. The metal properties which are obtained from the experiments are given like this. So for redowas, we have mu equal to this much and lambda m is 3.95. We assume it as almost an incompressible because rubber, the Poisson ratio is almost near to 0.5. So we assume it as incompressible. And this is the Brownian series parameters for viscoelastic modeling. So we feed this data into Abacus and so we carried out some analysis. We use explicit time integration and with delta t as 10 power minus 7 to minus 9. And so this was the FE modeling. Now simultaneously we actually first we did experiments, then we went in modeling. So for experiments, this is our specimen, which you can see that this elastomer is in the middle and the aluminum plates are there. So we wanted to measure its accelerations at different locations. But so we thought of putting it inside we should put inside the rubber part, but because of the small size and all, we could not do that. So we put the accelerometers in the aluminum part, in the cover part at equal location 1, 2, and 3. This is the VST, the vertical shock tube facility, which we used. This is the test section in which we put this specimen. Then we attach this test section to the shock tube here inside the tank. So we use the PCV accelerometers with this kind of plus minus 10% and 10 millivolt per G sensitivity accelerometers. We used the adhesive. This adhesive played a very important role because until and unless your specimen is properly attached, this hole won't work properly. So we worked too much on this. So you got an adhesive. And so we use this kind of, although we in our analytical study, previous studies, we got some other structures which also gave a good response. We chose this because we could attach some accelerometers properly in this structure. So we also had to put some protrusions like this to install the accelerometer. So this was kind of a change we had to do the specimen. So these are the experimental results compared with the computational results. So this is the first run, which I'm just presenting because we also have another results. Here you can see that except the first initial peak, at later times, the response, like this black one is like Abacus and the blue one is from the experiment, shock tube experiment. This is at location 1 and this graph is at location 3. So if you see the peaks are not matching in the beginning, but later times they are matching. So the peak acceleration as seen from FE model are going above 500 G actually. They are going above 500 G. These are the reasons which we found later. The sensor the range was plus minus 450 G. So we thought this peak they are not catching because of the limitation of the sensor. And also at later times it is matching. So we thought that might be the reason. But nevertheless, we can see that at location 1 and location 3, if you see the response, they're coming later. So something is being captured. So, but still it's not correct. So what we thought was let's reduce the pressure so that the peak accelerations are lower. So we went with this, this pressure profile. This is like a 2-bar pressure profile. So this is the result for that when we subjected the specimen for this kind of load, this load. So accelerations, and this we then filtered using a low pass filter, which was the frequency range of the accelerometer. So after that, we got this result. This is like at location 1, like this location. So as can be seen that there is a better match than the earlier, and also when I zoomed it, like it's quite good. So this is at location 1, and the time of shock arrival is also quite good there. The multiple reflection are attributed to this high P speed in the aluminum, which is almost 6,000 meter per second. And so now next what we did was at all 3 locations I I took the ratio of the acceleration of the amplitudes. I mean, normalized the amplitudes, acceleration amplitudes with respect to the first acceleration and then plotted. So this blue one is the experiment and the red one is Abacus. So if you can see, like this reduction in the amplitudes along the length is being captured in the FE model. So it was made sure that the adhesive which we used for attaching the elastomer and the aluminum was like have a similar acoustic impedance as the rubber. If we would have used some screw or something, it would have added more rigidity. So we didn't do that. So we wanted to go with adhesive only. So there might be some uncertainty associated with the blast wave characteristics for the adhesive when it bonds the metal and the elastomer. So that's why we suspect there are these differences. So which we are working on right now. But still, if you see this trend is going down, like this abacus is going down. So abacus results are going down. So we went ahead with our FE model and we got some results. So for FE analysis, we considered these three configurations. You see, this is like 5x1C 5x configuration with aluminum and on the top and bottom. Then we consider a same height neoprene rubber and aluminum. Then we consider third all three aluminum, and we subjected this to a large amplitude blast profile. These are the locations in where we found some response in our FE study. Like location 1 is in the core part, elastomer part. Location 2 is in the elastomer part at half distance, and location 3 and 4 are similarly in the aluminum part. So these are the results. So at location 3, in the where we subjected this specimen with the shock profile, we got this result. Like you can see that the stresses in location 3 in the case of 5x1C 5x are lesser than the other two, lesser even than this blue one, which is like that neoprene rubber. So this is the one result. Second result is at location 2 in the core. You can see because it is elastomer, these two like in the waveguides where this CR is present, like this 5x1C 5x and CR, you can see that the amplitude will go down because of the dissipative nature of the rubber, and this will keep oscillating because it's aluminum. So this was quite obvious, but this result is like good. So next, this is so next what we did was after some time, like after some location, how this at what time the waves reaches to that location, we thought of checking. So as can be seen at location 4, which is in the at location 2, which is in the rubber, if you check this is like the black one is in the straight aluminum, and this blue one is in this magenta one is in CR straight, and this red one is the 5x1C. As you can see that there is a quite difference between the incidence of these two waves at those locations, which is of the order of 100 to 200 microseconds. And similar thing we observed in the aluminum as well at location 4, but this is not that much. In rubber, it is this much, around 100 to 200 microseconds. So this phenomenon of low energy speeds can be applicable in the scenarios when your rise total time is of the order of microseconds, and additionally stresses will dissipate in the rubber part. So this delay is important. In summary, in the study we did in the study, blast wave mitigation characteristics of novel waveguide inspired from the switcher structure observed in nature. In the woodpecker in particular is investigated. We considered some configuration with 5x1C 5x configuration and carried out experiments and a numerical study on it. The results from the experiment and the FE analysis are comparable, not exactly matching, but they're comparable. And the stress history obtained from the model suggests that along with stress reduction, the energy propagation is getting delayed in these kind of structures. So further research needs to be done where we will implement better boundary conditions and other setup from the experiments as well as modeling. In future, we plan to do this like proper structural optimization of this where we'll have two responses and like multiple objectives where we want to reduce the amplitudes and the energy speeds, considering responses at different locations. This can be the formulation. Next, we wish to use this in sandwich structures, where we will also carry out the shock tube experiments on this. Later, this dynamic mode decomposition also we plan to do so that we will get to know which frequencies are getting attenuated because of these kind of structures. And later the support rotation, ductile ratio, and backface sheet deflections, which are the important parameters in the studies of blast mitigation. We are planning to do this. So this study is basically a preliminary study to work ahead on these kind of aspects. So so these are the group which we work with, and thank you very much.
Thank you. Any questions from the audience?
Error is percentage I didn't calculate, but it was like, if you see this slide, yeah, if you see this slide, this is like 0.9, here we got 0.75. This the experiment was 0.6, we got 0.45 something in the abacus. So the error is almost like 15 to 20%. But we are planning to improve on this. But at least we got some reducing trend at both the responses at both the locations were going down. And this at location 1 also, like, this is quite good match, we feel. So I think, but still we have to improve on this. Yeah, we are using the accelerometers now. We may also look into some other sensors as well. The size constraint is there. That's why the major.
Yeah. If you look at your graph, the graph for comparison. Yeah, this comparison. Could you please explain this a little bit better? You are actually getting higher pressures in the case where you have used your special structure.
Sir, the stresses, if you see, this is the red one. The red is 5x1C, 5x core.
Yeah.
So the stresses in that direction are lesser compared to the straight core.
Okay. Magnitude is
magnitude
less.
is less.
Magnitude is less.
Yeah,
That's what you mean to say.
Yeah,
But,
yeah.
It could also mean, you this either you have compression or the tensile stress.
Yeah,
So it looks like the reverse kind of a thing, right?
But
Happening.
all are negative, so I think
all are compressive stresses. Okay, so overall magnitude has
reduced.
decreased, is what you are.
Yes, sir.
trying
But
to say. Okay.
actually, lot of things are there in study, so I didn't put results. So some other.
Okay.
Yeah.
Any other questions? If I have a quick question. So this could be a high strain rate phenomenon, right?
Yes,
so in your constitutive model, normal constitutive model, if you use for FE analysis, that may not give correct answers, right?
Yes, sir. Actually, for high standard problem, there is the Ogden model is there, and Aruda Weiss also in literature people say sufficiently works. But the thing is, Aruda Weiss needs 2 metal constants, and Ogden needs more than 4. So based on the data which we had, this Aruda Weiss was kind of stable, and then that's why we went it. But as you said, there are different models like Ogden model which works specifically.
Because you are generating is close to 500 to 1000. No, you are generating 500 G to 1000 G, right?
Yeah, 500 G acceleration. So,
but that woodpecker, are you sure it is generating 1000 G? Because 1000 G seems to be a very large number. No? I am not
yes,
sure.
sir. Actually, I mean, in literature it is said, but
1000 G means, so if you assume, say 10-20 gram mass for this thing, then it may experience close to 100 kilograms to 500, 100 kilonewton to, correct, 100 Newton to 1000 Newton. Yeah, correct. That's very
the mass is small, I think that's why.
Yes, sure. Okay. No, it's a high speed. Yeah. The forces are between 100 to 1000 Newton only. Yeah, but it should have a very good damping mechanism there.
Yeah, damping mechanism very good. People are really looking into this, but there are different aspects. We looked into one aspect. So if we consider the whole as a model, there are a lot of other mechanisms inside the woodpecker beak.
Okay. Any other questions? Okay, and we'll thank the speaker. go to next talk. FBG sensor for blast wave measurements in shock tube environment by Gautam Hegde, Suraj Kumar Mondal, Gopal Hegde, plus Jagdish and Shogun. So the work is going to be presented by Professor Gopal Hegde. You hear me? Hello. It's okay. Yeah. Good afternoon. This is the title. Actually, the first student was supposed to present. He is attending conference in US. Second one is Suraj Mandal. He was here up to yesterday evening, but he's already working. Company has called him for urgent work, so he left and it came to me. Good that he sent the slides to me. I somehow downloaded and putting it here. I couldn't modify the slides. If any mistakes are there, please excuse me. So this is the title. Okay. See, this is the overall outline of the talk. Introduction, pressure measurements in shock tubes, principle of FBG sensors, vertical shock tube, design of FBG sensor for pressure measurement in shock tubes, modification, results, and summary. You're all shock wave experts, you know, I need not have to go to the details of shock waves and shock tubes. When you talk about shock, the first parameter you want to measure is the pressure, then the temperature, and other things add up. And you all know that optical diagnostics in aerodynamics and shock wave analysis is ultimate because we can understand a lot of physics and chemistry using optical techniques. But for measuring the basic parameters, not much optical techniques are used, even though they're very good. There are so many limitations and issues also. This is our main objective, to introduce optical sensors in shock tubes and many of the aerodynamic studies. With this intention, we started this work. And this is the shock tube, you know how it works. I don't explain all these things. There will be a driver section, fuel section. This is for shock tube for generating shock waves in the laboratory. So we are working on that part also. First, we try to work on this blast waves. Shock waves are in a way controlled way, and blast waves, we don't have the control, but still blast waves can be generated in the laboratory. And Jagdish and his team have built a vertical shock tube to generate blast waves. I think this is the first in the country, maybe, vertical shock tube for blast wave generation. So this is how the shock waves and blast waves are shown here. In a shock wave, normally you get a test time, but you in the shock blast wave you don't get it. In shock waves, this is necessary because you can understand the physics and chemistry of the shocks in this test time. Here it is different. So here blast wave is an area of pressure expanding supersonically outward from the explosive core. There's a leading shock front and a compressed gases. Blast waves are created exclusively by the detonation and explosive material. You know that these are all explosive, and country has a serious problem in the borders and all. Jagdish has one project for blast wave mitigation. For that purpose, he has built this shock wave. So we started working on that one. Pressure pulse without flathead region or zero dwell time is necessary. That is what there. So here driver tube length is tailored such that the expansion wave just catches up with the shock wave at the end of the wall of the driven tube, initiating an exponential pressure decay as seen in the blast wave. This is how the theory about this
And sorry, this is the vertical shock tube. I think the previous speaker done some experiments. I think you're also doing some more experiments with him. So this is the driver section, driven section, and this test section. And this is how the conventional pressure sensor is used. Now it is used everywhere. This is a diaphragm-based piezo-resistive sensor, and the dimensions you know better. This is about few centimeters diameter, about 5 mm to principle behind the working of this pressure sensor. And we also have used MEMS-based pressure sensors, but still it is not fully established in some situations, but we have tested that it is working very well. Now we are going for optical-based pressure sensors. And so before that, let me just say the limitations with this one, okay? Use sensors for pressure measurement in flow facilities are electrical-based, mainly piezoelectric and piezoresistive. Sometimes thermocouples are also used, but they are obsolete. But still, they are a bit expensive. And the main thing is mounting these pressure sensors in test models and or even shock tunnels. You need to make special holes drilled and electric wires taking out and all these things. Fiber-based optical sensors can be excellent candidates for flow divers in shock tunnel environment, but we have to explore a lot on that. FPG sensors are miniature size, about 200 micron, even less than with the jacket. Normally it will be 150 microns diameter. Lightweight, can be mounted directly on the model surface without any modification. And cumulative side, they are okay, minimal intrusive to the flow. There is no disturbance to the flow. You can directly expose the sensor to it. So this is how the sensor works. Okay, this is an optical fiber, and it is normally silicate fiber, germanium doped silicon fibers, and a grating structure. That means a periodic variation in refractive indexes. So it acts as a wavelength selective filter by reflecting a particular wavelength called a Bragg wavelength and transmitting the remaining wavelengths. And Bragg wavelength lambda b is a function of grating period and the effective refractive index of the core of the fiber, and is given by the next equation is given. This is the periodic variation in the refractive index, and this is the broadband source. And matching this Bragg this period Bragg one wavelength, that is called the Bragg wavelength, and that wavelength is missing here. Then this is the optical fiber you might have seen. It's a commercial communication optical fiber, and the principle of working is this is the fiber Bragg rating on the fiber, and this is the connector, the broadband source. Light goes, and the transmitted light is detected here, and the reflected light is detected here, and this is what the Bragg wavelength. Depending upon whatever the parameter we measure falls on this one, there will be a shift in the Bragg wavelength. You measure the shift, okay, you can correlate the parameter what it is. This is the basic principle, and this fiber sensor has well established in structural health monitoring, particularly in aerospace structures. This is well established but for this high pressure and harsh environment yet to be explored. That's what we are working on. And this is the fiber sensor we used. Okay, this is the connector. It's hardly difficult to see this one. This is the with the jacket, like a electric wire. This is a protection, and actual sensor is sitting somewhere here. So this is a facility we have in IISc. We fabricate the sensor at IISc itself, and the cost of the sensor will be around maybe 2,000 rupees, not much. And okay, UV laser source is there, and there is a face mask, and we have the fibers we import, germanosilicate fibers. We'll expose. Sorry. Okay, here the facility. We write the drag rating here, and then we fuse the fiber like electric wire. We fuse the fiber wherever we can increase the length to any extent. Okay, so this is the facility, and these are the advantages. Okay, it's a lightweight, no doubt. The dimension only too small, about 125 micron. The actual diameter of the sensor is 150, even 125 micron. That's all. Since it's a single mode fiber, the core will be around 10 to 20 microns, even less than that. Okay, and the sensor can be modified in different ways to measure various things. Then this is multiplexable wavelength encoded information, hence independent of intensity, immune to electromagnetic interference, okay, environmental ruggedness, okay, explosive environment, compatibility with the telecom fibers, sensitive to multiple environment parameters like strain, temperature, refractive index, pressure, etc. Even bio sensors also have been made using this one sensor. No danger of sparking, as fibers are electrically insulators, minimum obstructions to the flow. So now this is the basic theory of this sensor. Two things, thermal expansion coefficient and thermo-optic coefficient. So this strain which falls on the sensor, so that has been analyzed like this, photoelectric coefficient and longitudinal strain of the grating. So with this, you can ultimately what you need to measure is measure the shift in the wavelength because of whatever the parameter falls on. Then you can do a lot of things. Okay, processing is very easy, not that difficult. And again, okay, total sensitivity of the Bragg rating is given by this equation. And for germanosilicate fiber, these are the things we, whatever the fiber sensors we use. Effective strain optic constant is 0.21. Coefficient of thermal expansion is this much. Thermo-optic coefficient is 8.6 into 10 to the power minus 6. And wavelength, what we use is around the broadband source is 1550 nanometer. This is also communication wavelength. Strain sensitivity is 1.2 picometer per microstrain. Then temperature sensitivity is 13.7 picometer per degree. This very sensitive fiber, and this is what we have fabricated. This is a probe we fabricated to use the blast waves in this column. Okay, design and development of FPG sensor probe for vertical shock tube, and this is metal, and this has been designed in such a way that it can withstand the blast wave. And the fiber sensor is sitting somewhere here, and this is taken out through this one, and this is the jacket of the fiber. You can take it to any location for the measurement, and this is put here. And to validate this sensor, we also parallelly put the standard conventional sensors together on the another hole here. And this optical fiber, this is the PCB sensor. Then these two whole unit is put into the shock tunnel, vertical shock tube here. Okay, inside the tunnel you can see, and both the sensors are here. This is driver and driven sections on the top. Maybe that's also there. Yeah. Okay. This has been suspended here, and there's a diaphragm here. It's a complicated operation as well. A lot of safety issues have to be taken into. So this is ultimate measurement. This fiber is taken out somewhere and put it here, arrangement up top, connection and sensor assembly mounted on the wall of this one. Entire photo is shown here. Okay. And this is the interrogation system we used. And other standard procedures we followed for the conventional sensor. Okay. So as usual, nitrogen gas was used the driver and air is driven section, air in the driven section for the experiment. Aluminum diaphragm as usual. So depending upon the thickness, we had different pressures, and this is a standard procedure. Okay. The diaphragm burst pressure is recorded at the end of the driver section using a pressure gauge. The signal from this sensor in the driver section used to trigger the FPG and piezoelectric PCB sensor in the driven section. The total recording duration of the pressure sensor was about 20 milliseconds from the start of the trigger. So because initially we didn't have a trigger facility, later we introduced that one because PCB sensor can be triggered easily, but optical sensor, we found a method for that one. We're still improving it. So finally, this is the blast signal. This is the PCB sensor response. This is the FPG response. So whatever the interrogation system gives is the strain, and we have to do FFT and a lot of processing we have to do. Ultimately, we convert that wavelength shift into pressure. And this is the profile of both the sensors. They look almost similar. Okay. This is the first time we are introducing optical sensor. We can get the fragility of the sensor and also optical limitations. I think we got some encouraging result. However, the pressure measurements, a lot of difference over. And later we realized the reason is, the shock pressure front impinges on the FPG sensor perpendicular to the longitudinal axis. The combination of transverse strain and photoelastic effect causes an increase in the Bragg wavelength. That's the shift we measured. A pressure sensitivity of 464 picometer per bar is used to convert the wavelength shift data of the FPG sensor into corresponding shock pressure signal. A conversion factor of 0.725 millivolts per kilopascal. This is for the PCB sensor. So first signal corresponds to the blast wave as seen by the instantaneous jump, followed by the exponential decay pressure. The width, the peak, or the decay time is found to be 6 milliseconds. I think they are almost matching. However, there is a numerically, I think the pressure is not matching. We realize that there is a lot of difference in what we use. This system is slower. Whatever the interrogation system we have is about 5 kilohertz, and PCB they use 1 megahertz. That's why the difference. This is a second experiment for a pressure of 16.5 bar, and the first one. Okay, this is just an air column. We did the experiment, and the first one is about 10.6 bar. We got the signal, and for the second experiment with different diaphragm thickness, about few millimeters, and this is the pressure we achieved, 16.5 bar. And here also, as you know, I think because of the blast, the shockwave strength, the pressure is higher normally, but here also it is higher, but not matching as such. Okay, 4.52 bar here. This pressure and this pressure they are talking about. FPG and PCB pressure sensor responses to blast wave are found to be similar. The slight difference in the peak shape and the pressure amplitude could be attributed to the difference in mounting the two sensors. That's also there because this sensor is fastened to the surface. We have put it inside it. We can also do that one. That modification is also we are trying to do. And the trick here is we failed because our interrogation system is of 5 kilohertz and this is 1 megahertz. So that's why we are not able to see the full pressure by the time the shock might have passed through or the blast might have. And same thing we repeated in the sand column, filling the column with the full of sand, because this we have one project from the defense to design the bunkers to measure the shock strength and do this. This experiment is going on. So here, okay, same way we have mounted and filled this one with full of sand, and this sand is collected from somewhere, okay, from Rajasthan. This is what I heard. The sand column was prepared by elevation with a fall height of about 10 centimeter. That's a funnel, and slowly I think they have put it in. And as usual, this nitrogen gas was used, and this is the burst pressure, about 16.3 bar. There will be stress wave, definitely. There will be the impingement of blast. As usual, I think it is inside the sand. Definitely, there's a shock strength is more here. Okay, this is signal. And here also, I think signal is almost matching. The only difference is the decay time is less here in optical sensor. So the advantage of optical sensor is very sensitive. The response time is faster. It is about a few microseconds. And this is slower. This is about 8 bar blast pressure, and this shock pressure, and this is 1.75. This is, I think, not acceptable, definitely. The peak pressure value recorded by the FPG and the PCB sensors are this much, 7 respectively. This variation could be due to the unpredictable nature of the interaction between sand particles, like compaction, rubbing, when the sand column is impacted with the blast wave. So that physics also you have to understand. We have done the experiment with even glass beads also. We got similar results, and we are trying to improve the results. Okay, FPG pressure sensor system was designed and developed to measure the blast wave pressure profile in the vertical shock tube. The blast wave impact was perpendicular to the FPG axis. Blast wave experiments are carried out in air and sand column at different blast pressures, and pressure signals were recorded. These signals are validated with flush-mounted piezoelectric pressure sensor. The pressure profile is matching, though the differences in measured pressure values are found to be higher, and further experiments are in progress to improve the result. And recently we have procured a high-speed interrogation system that is working about 5 megahertz, and we are working on it. We are getting training on how to use it. It's a black box. I think in India nobody is making it. The government is asking us to, why can't you make this interrogation system in India itself? We are working on that also. And we are modifying the sensor mounting and other things. Hopefully we'll be able to use this sensor in this harsh environment. I think that's a possibility. I think these are some references given. Harsh environments, I think it is here. I think this also somewhere it is published for high pressure. I think this is what the slides. Yeah. Good that they have prepared good slides. Manageable slides they have given. And we would like to thank especially LHSR for providing the facility put built by them. Thank you. I think that's the end of it. One more is there. Any questions?
Thanks, Professor Hegde. Any questions from the audience?
So we did experiments in the supersonic ejector also.
Yeah, I think.
So I think during those, one of the sort of things that came up was that these sensors are more sensitive to temperature than pressure. The sensitivity to temperature is much greater than that of pressure, and so we did some additional work to separate pressure and temperature sensitivity.
Yeah.
So maybe, do you think
Exactly.
the same effect is happening here?
I don't know whether in this situation there will be a drastic change in the temperature in the last waves. That's also in mind. Temperature compensation has to be done to get the right value.
No, because blast waves are also shock waves. There also there is an increase in temperature, and that increase is much higher than what you see in supersonic facility.
Yeah, exactly. Thank you. For that one, we have to put one more fiber optic sensor with a metal tube to compensate for the temperature, and that we are looking for how to put in the shock tube inside. In your facility, I think we had enough. Here, if we put it, there will be a protrusion inside the system, the column. So that's what we are designing it. Hopefully.
Professor, this is the first time I'm also seeing such a use for this sensor. We have worked with electrical engineering professor Balaji Srinivasan here.
Oh, yeah, I know.
He made the FPG sensors for
Exactly.
gas turbine engines, and they tested it in our labs. Anyways, there they used for pressure measurement, strain-based measurement. They put like a metal tube, which expanded, like very thin metal tube kind of thing, inside which the fiber is stuck to the wall. And then now that tube is going to sense both the temperature and the strain. So they had some gratings in the fiber which will give temperature, and some gratings in the fiber which will give you strain. They used both of these together to tell the pressure and the temperature variation along the length.
I think we recently did the similar work for his ejector and eject facility. When we first did that, that's
So
called.
you guys have also done that.
Oh, yeah, we did that. We did that one. For this one also, we are thinking, but there are some constraints in the design that we are still working.
Yeah.
Putting the metal tube. Yeah, exactly.
Then 1.4 micron, you are working 1.5 micron, similar range,
Hmm.
but they were working in kilohertz only as a gas turbine engine. The instability that happens is in kilohertz.
Yeah, that
They used
range is.
kilohertz, and it worked out very well for them.
Other questions? There are no other questions. Let's thank speaker again. And let's close like that. So let's break for tea now. And we are behind time by 30 minutes. So we need to be back by 4:20 at least. So the session begins after at 4:20 after the tea break. Thank you.
Welcome to the last session of the SIS, which will run from 4:25 and every speaker will have 15 minutes for their presentation, followed by 4 minutes for Q&A. Our first presenter is Balaji Pinakar, speaking short language layer reaction information. Co-order is Professor Srishan Rao.
Good evening, everyone. This is Balaji. I'm a research scholar at LHSR Lab, IISc. My co-author is Dr. Srisha Rao, who is my supervisor. Today evening, I'll be talking about shock boundary layer interaction in confined Hoff nozzles. Yeah, confined Hoff nozzles is an intriguing word. Please bear with me. I'll come to that in a couple of slides. There's no big difference in the outline that has been standard, like more or less we go through the same thing. Directly opening up to the context, this cartoon of scramjet requires no introduction for this audience in this room. It's basically it has bespoke components: inlet, isolator, combustor, and nozzle. This part of work was interested in the isolator, where the whole purpose of isolator is to isolate the pressure fluctuations coming in the combustor to reach the inlet further, which might lead to the unstart of the inlet. So the major thing that happens in this isolator is about the shock boundary layer interactions, because it's a duct and boundary layer would have developed, and a single shock that forms in there, which interacts with the boundary layer, can form and start forming into a train of shocks. There has been more than 100 to 200 paper works that have been reported officially, where broadly it can be classified into few segments and classifications. Like it can be divided into shock train shapes, which could be oblique or lambda shape, starting from 1970s to very recent times, or the shock train length estimations. And also there is a recent work in 2015 with an innovative way of doing a shadow graph in both the planes, top plane and side plane, which was able to see the corner separation, also the bending of the shock based on the aspect ratio. And again, other works also involve about shock train leading edge detection. Hertzel et al. Has given something like around 6 different techniques in which it can be detected. And further, the oscillation, inherent oscillations of this shock train, basically many theories have come up, and people have worked on coherence analysis and all to find out from where does the perturbations get transmitted. And also there is enough amount of work that has been done on forced oscillations, where the forcing can be done by the back pressure forcing based on a butterfly valve or a throttling valve. And to the recent times where the predictability of the shock train leading edge has also become a recent part of studies, and fluidic control based shock train control of the leading edge is also a very recent work in 2022 that has been published. Now, in order to understand these things, we need ground test facilities, and most of these ground test facilities are whether it's a pressure blowdown type or an in-draft type. Essentially, it contains a nozzle, a CD nozzle with a duct that carries on, whether it is a pressure type or a blowdown type. And the way shock train is generated is essentially you start the duct with a desired Mach number flow and then increase the back pressure either by a flap mechanism or by a throttling mechanism to create a shock train. In designing these facilities, in general, people go with decently huge dimensions such that the starting shock just gets pushed out and desired Mach number is established in the duct, and then shock train is brought in by choking the downstream. But in certain situations where from the constraints from the mass flow regulations or from the dimensions where we may need to go for a smaller dimensions, is that the case where whether every time the tunnel starts is a question, because we had faced a situation where the tunnel couldn't start or the nozzle couldn't start because of the separation that has happened. So this anchoring into this looks like more or less like a nozzle flow separation. So looking into the flow separation in a nozzle, more or less the work broadly classifies the separation into two types: free shock separation and restricted shock separation. But this is one of the Schlieren images from the literature. It shows about the free shock separation. But most of these facilities, when we see, they are the nozzles are basically overexpanded nozzles, and they basically expand into the ambient conditions, which is not the case with the isolator kind of facilities where we have a nozzle and then we have a confined duct. So so these two are the two tricky parts which we couldn't fetch something for our case from nozzle flow separation literature. So again, going back into the isolator flows only, we were trying to find out some cues if can be implemented to solve our problem. Well, this is the shock train length empirical relation given by Woltrup and Billig in 1973. But in a recent study by Gamba et al., what they have done is they have manipulated this work, this right-hand side into a form where they've introduced this Q term. Basically, this is the Q term in which in the denominator we have something called C theta, which is nothing but 2 theta by h, that is a flow confinement. So it is the work what they have presented was that the confinement ratio plays a crucial role in type of the shock train that comes up. But this is a general classification till then. How does whether it is a normal shock or an oblique shock based on the Mach number. But if you see these two dots, this is what they say that, okay, this the circular dots, what they say that the Mach number still be less and still the leading edge shock could be an oblique shock, and the Mach number still could be higher, and leading edge shock could be a normal shock with bifurcated foot. So they were saying, they were suggesting that the confinement ratio plays a crucial role. So from this, we took the cue if confinement ratio is a factor in the problem that we were facing of the flow separation in the nozzle followed by a confined duct. So that becomes a motivation for this work to narrow down onto if there is any number for this confinement ratio that can dictate for a lower dimension experimental setups. And this C theta, as we have seen, it is 2 theta by h. depends on theta and h. So the independent parameters that that we could vary is momentum thickness and duct height. And momentum thickness, again, based on the location at which this throat exists and also the P naught. These three are the independent parameters that we were able to control. Yeah, this is a experimental facility that we have at LHSR. Like this is a schematic and the real image. Excuse me for this test section. This test section is not exactly the test section what we have. This is a schematic, a referred image. So this is a inlet manifold where we get a high pressure line from the reservoirs, and then we have a isolator valve, pressure regulator, and a quick acting valve. And then we have a settling chamber, and then we can connect it to any test section, modular test section that we can have. And then followed by a diffuser and the pipeline in between, and the exhaust line goes to the vacuum. So the exhaust line can be exhausted to atmosphere and also to the vacuum. So we can operate it either in a pressure blow-down mode or pressure vacuum mode. But in these studies, we have operated in pressure vacuum mode, and we have a solenoidal valve in the end. To show the sequence of operations, this is a wall pressure data, that is wall static pressure data that is extracted at the exit of the nozzle. Yeah, so the sequence of operations is the moment solenoidal valve, vacuum valve gets opened, the whole this section will be exposed to the vacuum. And then once the pressure solenoidal valve opens, everything would be kept at a high pressure. And once it gets cut off, there is a residual air that goes off. And then once the solenoidal valve gets cut off, this can be vented so that it all comes to the atmospheric pressure. So these are the broad classification, and we have a pretty steady, except for the transients of the order of 100 to 200 milliseconds because of the time taken for the solenoidal valves to open. More or less a kind of a steady flow that we have, small fluctuation. So we take in that stage, we take some something like 4 seconds of runtime. We take it somewhere between 2 seconds to 3 seconds as a to calculate the average pressure data during that time. Yeah. So coming to the schematic of my test section, it's basically a duct which has it's a rectangular duct of span-wise width to be 50 mm. The width into the screen is 50 mm, and it has a rectangular duct upstream which is close to 100 mm. This is modular. I can make it 0 or 100 in 2 steps. And this nozzle design Mach number is 2.5, and the exit again height can be made into 2 steps, either 10 mm or 15 mm, where I actually basically move the plates, top and bottom plates distance apart. But the overall length of the test section is constrained. So these three are the independent parameters, and this is an experimental matrix that I have. Just to note, like in my sequence of operation, when the flow starts, the nozzles are actually exposed to a pressure ratio. The initial pressure ratio is at least a order lesser than the isentropic pressure ratio. That means it is not like a case of overexpanded nozzles. Like we are giving decent amount of pressure ratio for it to start. And then the next part comes is in the theta. We have not done any velocimetry measurements, so we need to rely on some estimate. So this is 1/7 rule to go for it. In Gamba et al. At 2018, they did a velocimetry measurements, and they have fitted to the this 1/7 law relation with a small change in x. That offset is very less, something like around 10% of the value. So for our case, we took the start of this duct as a virtual origin. So that's an estimate again, but somewhere to start with, we have taken that. Yeah, and the diagnostics, to come to the diagnostics, we have done high-speed Schlieren and also the pressure diagnostics for sidewall and top wall pressure measurements. It's a typical Z type with horizontal cut has been used, and it's a nanopulse laser of Silex 640 with 10 nanoseconds of pulse width. And we have used an SA4 phantom camera, photon camera with 22,500 FPS. And the pressure measurements, again, there are piezoresistive sensors, which is semiconductor based. And it's two type of sensors based on the location that we are using, either half a bar range sensor or 1 bar range sensors that we have been used. And accuracy is of plus or minus 2.5% on full scale. And data acquisition is used using picoscope DAQ. And all these things, including with the sequence of operations, are all synchronized using Arduino. Yeah, so coming to the results, first we change the duct height. So, okay. Yeah, so this is the first case is by putting the nozzle at the downstream, that is 100 mm downstream. So there is a decently grown boundary layer till the throat of the nozzle. And there we have two cases where the exit heights is, one is 10 mm, the other is 15 mm. These are the time stampings that has been done for the Schlieren. If we see that even after 1 second, it remains, the flow remains separated, and there is a shock that gets reflected here. And whereas if we see in the 15 mm exit heights at almost 130 millisecond, the starting shock gets pushed out and the boundary layer gets attached. And yeah, this is attached boundary layer. And this, if we look at into C theta values, it is close to 0.188 for here, and this theta estimation is close to 0.113. These are the average pressure data, as I was talking about. This is a nozzle exit and this is a nozzle throat, and the non-dimensionalization has been done with respect to the length of the nozzle. And the origin of this is at the start of the nozzle. So, yeah. So as we see at 15 mm exit heights, it's pretty started, whereas this remained unstarted for some time. This is a zoomed in view where it appeared to be like an pre-shock separation kind of thing. And the starting shock is creating a separation bubble there because we're getting the separation and reattachment shock too. Coming to the effect of momentum thickness, as I told, we have moved the nozzle upstream and to see the variation in theta. And then if you look at it, it's almost half of it. And then both are at 10 mm exit heights. So if you see here, this case has started by within like 1 second, it has got started. Yeah, it took some time for it to start, but the boundary layer gets attached. And this is for a higher pressure of 1.58 bar P0. The initial of 1 second here has actually reduced to something like 400 milliseconds. It gets attached immediately for the same heights of 10 mm exit heights. Yeah, as I was talking about the P0s variation, influence of P0 we were checking. When the flow remained unstarted, the P0 hardly had any effect except for the slope in moving the foot of the oblique shock, but it didn't have much effect when it remained unstarted. But when it got started, it had slight variation because we can see the slope that indicates the speed at which the starting shock gets pushed out. It did had a slight effect. It did had a significant effect when the upstream boundary layer was minimal. That is when we moved the nozzle upstream. Within 400 milliseconds or 300 milliseconds, the starting shock gets pushed off. Whereas here it remained. I mean, it got pushed off only after a second, almost double the time. Yeah. So these are the average pressure plots. The one thing which I wanted to stress here is even though these two are the cases where it was unstarted, but P0s are different. The levels of P by P0 values are lower as I increased P0 because that tried to favor the pushing of the shock, but still it remained unstarted. Yeah, to summarize my work, it's like the effect of C theta was actually checked on to how does this nozzle start when we go for a smaller dimension test sections. These three parameters were varied. If you see this plot shows the average pressure data on the top wall at the exit of the nozzle. So this is an isentropic pressure ratio. These are the conditions where the nozzle remained unstarted. If you look into those cases, the confinement ratio was nearing to 0.2. I will not be able to exactly precise on it because we didn't measure the theta. It is an estimate. As a and also the number of data points are a bit less. So we are actually as a future work, we are trying to expand this number matrix by going for a different Mach number, and also if possible do the velocimetry measurements to come on to this C theta value, which can be a design guiding rule for these kind of geometries. Thank you.
Right. You said that you kept the test section length constant, right?
Total test section, yes.
Total test section length is constant, but when you removed the initial portion before the nozzle,
Yes.
did you put it on the other end?
Yeah, it's swapped. This is swapped.
As
So-
in,
So the initial test
nozzle
section,
and the downstream portion went ahead and this portion went to the end.
right.
Okay. In that case, the back flap valve effect would be like.
We
farther
don't
away,
have a
right?
back flap. We don't have any
Showed
flap.
in your picture. I
No,
think.
we don't have any flap. So we don't have any flap. It is directly connected to diffuser via vacuum.
Okay. How are you changing a back pressure then? I stepped out.
No, we didn't. We are not changing any back pressure right now in these cases. Even though our objective was to study the shock train, we were about to keep a butterfly valve. But even before that, we had a trouble of starting the nozzle, even though we were giving the pressure ratio. So the whole study is about why is this nozzle unstarting and the effect of confinement ratio on this. So there is no back pressure maintained. It is directly exposed to the vacuum of close to 8 millibar or so. It is exposed, and pressures of close to 0.9 bar to 1.58 bar are given as P naughts. And so the pressure ratio was decent enough at the start because as the time goes, the vacuum starts filling. But still, for our 4 seconds of runtime, still the vacuum was within the limits. But still, this was a case. So, that's the point. Like we were not using any back pressure flap.
What is the mass flow rate for your tunnel?
For this case, it comes close to 0.1 kg per second for this dimension of the order. Yeah, it's a small throat. That was a catching point here. Like if the throat was bigger, when we went for 15 mm, throat was slightly above 5 mm, close to 5 mm. So it was able to push the starting shock. So initially we were a bit intrigued by whether it is the starting shock or what was it causing it to anchor. Then we increased the FPS, then we got to know that it is the starting shock that is unable to go out. It is interacting with the boundary layer and it is creating the separation. So it is all about the strength of that shock boundary layer interaction at that point and the dimension that is available.
Okay, thank you.
So I have one question.
Yes.
What is the possible or influence of expansion fan on shock boundary layer interaction in your case?
Ideally, expansion fan should not cause any adverse pressure gradient. So
Have
it
you
should be in favor of it, but we didn't find any influence as such in.
Did you observe any measured any shock?
No, sir, no oscillations, no oscillations. It is like the moment I get the starting shock, when it is trying to go out, it gets almost anchored at that point.
Here the moving downstream.
Yes, it is moving downstream slowly and it stays there. Yeah, it doesn't come back. No cyclic thing going on.
Okay, let's thank the speaker again.
Thank you.
Okay, there is a slight change in the schedule. Our second speaker is Mr. Mohammad Shahid Habib Khan. He will be talking about numerical simulation of shock boundary layer interaction in an axisymmetric half isolator. For this, Jatinder Pal Singh Sandhu and Professor Sandhanu Ghosh.
a master's student in the Department of Aerospace Engineering at IIT Madras. The title of my work is Numerical Simulations of Shock Boundary Layer Interactions in an Axisymmetric Half Isolator. My co-authors are Dr. Jatinder Pal Singh Sandhu and Dr. Shantanu Ghosh. So first, going deep into the work, we have a little introduction about shock boundary layer interactions. The shock wave is basically a non-isentropic feature in the flow that causes an abrupt increase in pressure. Due to this increase in pressure, an adverse pressure gradient is generated, which, if sufficiently large, can induce flow separation during the shock boundary layer interaction. This can have negative effects on the flow field. It can lead to total pressure losses, increase in drag, other mechanical loads, etc. Here we have a little illustration of shock boundary layer interactions in the separation region. Here we can see the flow is developing near on the surface. Here in the blue color, ramp is shown, which is acting as a shock generating device. That blue line is basically a separation shock, and a separation shock foot can be observed near the surface. Near the ramp, we can observe a small separation region forming. This is due to the interaction between shocks and the boundary. Let's see some literature regarding this. Gary S. Settles et al. Were among the first one who studied this length of separation region using different compression strength. They used a planar configuration, and shock was generated using a 2D compressor corner. They used the Mach number of 2.85, and the ramp angle they used were 8 degrees, 16 degrees, 20 degrees, and 24 degrees. What they found out was that in the 8-degree case, no separation region was formed. In the 16-degree case, incipient separation was there. That is just the starting of the separation. And for the 20-degree case, separation was there. And with respect to the boundary layer thickness, its length was around 0.65. While for the 24 degrees case, its length was almost equal to 2. Later, Brown J. et al. Performed a similar study, but on a positive curvature configuration. SBLIs were generated using a cylindrical conical flare configuration. They used a similar Mach number of 2.85, and the ramp angles which were used were 12.5 degrees and 30 degrees. In the 12.5 degree case, no separation was observed. And in the 30-degree case, the length of separation region was almost equal to 2. Here, based on these two studies, we can observe that in the positive curvature, for the same separation length, the compression strengths are higher. Recently, Vanderberg and Narayanaswamy performed a study on a negative curved half isolator geometry. They used a Mach number of 2.5, and they used the ramp angles were 16 degree, 20 degree, and 24 degree. Here in these two different domains were used. The experimental domain which were having the domains were differing in the different streamwise extent. The experimental domain was having a 380 mm length before the leading edge of the ramp, while the computational domain was having the 300 mm length before the leading edge of the ramp. In the computational work, fully turbulent flow assumption was used. They found out that the length of the separation region was higher in the HI case, that is in half isolator, compared to the planar cases. However, in all these cases, in the computations, fully turbulent flow assumption was used from the beginning. And in the two different domains lengths were used, and it was not clear why. That is why in our study, we wanted to perform the transitional flow and transition modeling over the domain which matches with the experimental domain and see how the results compare with the experiments. On our work, numerical simulations were performed on over a three-dimensional geometry as shown. The model was first developed by Vanderberg and Narayanaswamy. We used one compression strength with ramp angle alpha equals 20 degree. H by R value was 0.246, where H being height of the ramp and R being the inner radius of the isolator. The free stream parameters which we used were Mach number of 2.5. The free stream temperature was 140 Kelvin and the pressure was 32.5 kilopascal. The calculated values based on these parameters were for the U infinity and Reynolds number were slightly different from what was mentioned in the paper. The figure shows the isometric view of the model. Here, phi is basically the azimuthal angle in the span-wise direction. Phi equals 0 represents the center plane. In the red, we can see the shock-induced separation region forming, and the dotted line there shows the leading edge of the ramp, and the other, the oblique shock is also visible in the figure. In our case, the flow simulations were performed using an in-house finite volume-based solver, FES3D, which is also open source. It solves three-dimensional Favre-Average-Navier-Stokes equations. Third-order muscle scheme was used for phase reconstruction, and Awesome scheme was used for inviscid flux reconstruction. Second-order central differences were used for viscous flux reconstruction, and for the turbulent modeling, we used the Mentor's K omega SST model, and for the transition model, one equation local correlation-based model were used. Now the computational setup. As mentioned before, we have also used two domains. Domain A matches with the experimental extent, and we have done transition modeling over it. And domain B, only the fully turbulent modeling was performed. The initial cell height was set at 1 micrometer, and the stretching ratio was set at 1.05 to blend the mesh near boundary layer with the outer outer cells. Here we can see the mesh design for the computations. It should be noted that in this, every third grid line is shown. The extent of the domains in Y and Z was same, while in the X, it differs. In Y, it was from 0 mm to 95 mm, that is in wall normal direction. And in Z, it's from 0 mm to 50 mm. Another thing that should be noted that only the half of the domain was used for the computation, as it is expected that the results will be symmetric about the center plane, which was shown in the reference paper before. The boundary condition setup. We have used the supersonic inflow boundary condition. So number 2 represents the no-slip adiabatic fall over which the flow is happening. Number 3 is the symmetry boundary condition, and others are basically supersonic outflow. Now we have obtained the boundary layer data at the plane of symmetry, 50 mm upstream of the leading edge of the compression ramp. For the domain B and the two cases, the experiment and the RANS cases, the boundary layer thickness was 3 mm, while for the domain A, it was 3.7 mm. This is due to the fact that the boundary layer development length in the domain A is higher compared to the other cases. Now we'll go through the results which we have got. These are basically density contours at the leading edge of the ramp. A is for the experiments, B is the RANS computations by Narayanaswamy, and C and D represents our simulations. Here C1 represents the separation shock, BL represents the edge of the separated boundary layer. We can observe a higher density region between C1 and BL at the leading edge, and that region is qualitatively very similar in the RANS computations for the three cases. In experiments, it's slightly different. It is the BL region starts much closer to the wall compared to the simulations. Later we have also found the density contours slightly downstream of the ramp. Sorry. For the experiments and for the domain A, we have found the contours at x is equals to 30 mm, while for the RANS and for the domain B, it's at x is equals to 35 mm. Here we can observe that the qualitatively results are very similar. However, some differences can be observed. In our computations, the eta represents the high density core region. And we can observe that the core region is slightly larger in our computations compared to the reference paper work. Also, if we compare the images A and C, we can observe that the core region is significantly smaller in our computations compared to the experimental work. Next is the streamwise pressure contours at the center plane, that is as phi is equals to 0. A is for the RANS computations by Narayanaswamy, and B and C are our computations. in the domain A, that is in figure B, the transition model, we have performed the transition modeling. And if C1 basically represents the separated, represents the oblique shock, C2 is the series of compression waves which was generated due to the reduction in area. T is the triple point region where the C1 and C2 interacts, and C3 is the outer shock generated due to interaction between C1 and C2. Now we can observe that the T region is not very clear, is not very clearly identifiable in the domain A. Also, the pressure ratio values in our computations are slightly higher compared to what was mentioned in the paper. These are streamwise velocity contours at the plane of symmetry. These figures give us a nice understanding of the separation region which was formed. If we see carefully, the length of the separation region is same in all the three computations in absolute terms. That is, the ending and the starting and the ending point is almost at the same location. However, if for the domain A, if we take it with respect to the boundary layer thickness, the separation region length will be smaller as the length of the boundary layer thickness is higher in the domain A. Now we see the streamlines for the different at the center plane. In the first figure, we can clearly see a flow recirculation region forming near the leading edge of the ramp, which is a clear indication of the separation that is happening near the ramp due to the shock boundary layer interaction. The second figure shows the isometric view of the streamlines. In this also, the separation and the reattachment region is clearly identifiable. The streamwise velocity contours are also shown in the background for the reference. The one thing which we can observe from the isometric view is that in the center plane, the length of the separation region is slightly higher compared to when we go in the offspan direction. This can be due to the compression waves moving radially inward due to the negative curvature of the geometry. In conclusion, the RAM's computations were performed on a negatively curved geometry to study the shock boundary layer interaction and its effect. Two different domains were used, one for the experimental and other for the computations. We have observed that there is not significant difference on using the transition model. However, our results compare better with the experimental model for a fully turbulent case, but when we use a shorter domains length. Some references which we have used. That's all from my side. Thank you. Question?
Okay, thank you. Time for a few questions.
Just a clarification. What is the nature of your compression shock which you have on the ramp? It's
sorry, I didn't get the nature of the.
No, the compression ramp shock, whatever you are having, is it also axisymmetric in a way?
No, it's a 3D half isolator, like it's curved.
Yeah, it's a 3D half isolator. So your compression ramp shock is, can I call it conical? It's like a conical shock?
Not conical exactly. It's like it's following the curve of the ramp.
Okay. So this happens, and afterwards the flow inside the isolator, whatever you have, the non-boundary layer flow also, were you seeing any rotationality in that flow also?
In non-boundary layer region, it was not a region of concern. Also, we have not observed anything like that in the above the region after the boundary layer. We have not observed anything like that.
Okay.
In our simulations.
Okay. Sorry. Okay.
Hi. Can you elaborate on how you designed the curvature of your ramp?
As in, it's the mentioned. Sorry. Yeah. So let's see if this figure. So we have made the mesh in the inlet plane first, and we have extruded it till the leading edge of the ramp. From minus 300 mm to 0 mm, we have extruded it. We have basically translated it, that mesh. And then again from the ramp trailing edge till the end, we have done the same thing what we have done before. And between the ramp region, we have basically joined these, made the domains, and have basically joined all the domains to make the block.
Not about the domain, about this. Yeah. Okay.
Yeah, this is the geometry which has been used in our computations.
Okay. Okay.
Yeah, this height of the ramp is that h by r value is 0.246, and r was given in the paper, so h is anyways clearly known.
Okay. Thank you.
I have one question. In your geometry, there is spillage effects. How did you account that in your simulation?
Sir, if we see this boundary conditions, mainly in the 4, 5, and 6 are simulated as supersonic outflow. This was done in the computations, and this accounts for the spillage, which will be there in the experiment.
One quick question. Your shock standoff distance is around 70 mm.
Yes.
And your upper wall is around, show me the
Upper wall is it's
around
still
90
95 mm.
So the top wall is too much close to the shock. Will it be there any reflections?
I mean, that 95 mm length was chosen based on that there won't be any reflections.
Standoff distance is too high. It is around 60, 70. So I think it is too close.
I mean, see,
upper wall.
It was not there in the reference paper, and we have used that same dimensions for our computations also.
Okay, let's thank the speaker again. And we will move to the last presentation. And the author is Khande Vivek, and topic is study of shock-induced flow separation due to three-dimensional slender protuberances. And co-authors are Saurabh Balduraj and Professor R. Sriram.
Good evening, everyone. I'm Vivek. So my guide for the current project is Professor R. Sriram. So my topic for the current presentation is the shock-induced flow separation due to slender protuberances. This is an extension of the work previously done by the Saurabh Bardwaj on the scaling of shock-induced separated flows. So this is the outline of the presentation. Shockwave boundary layer interactions is a common phenomenon in applications involving supersonic flows. So when a boundary layer is subjected to a shock, it experiences sudden rise in the pressure, which causes increase in the boundary layer thickness. And when the shock is strong enough, it may also cause separation. So these figures to the right are from a paper by Dellery, which show the overall flow organization. So the figure in the top is a case where there is no separation. And the figure in the bottom is a case with separation. We can see that because of the separation, the flow is the complications in the flow are increased. So here, the pressure would start rising on the onset of the interaction, and it would reach a constant value inside the separation bubble. And again, it would rise across the reattachment shock. So a lot of initial work has been done focused on two-dimensional SPLI, where even theoretical correlations like free interaction theory were also proposed. Relatively less focus was kept on three-dimensional SPLI. So in the cases involving three-dimensional shocks, the separation as well as the gradients are three-dimensional. And also because of the shape of the shock generator, additional parameters need to be added, unlike the two-dimensional flows. So unlike the two-dimensional flows, here after reaching a plateau pressure, we observe a dip in the pressure ahead of the shock generator, which is a protuberance here. So, and also in two-dimensional SPLI, we observe in the separation region, the streamlines are closed, but here we observe a horseshoe vortex, which has the streamlines which are not closed. And also in some previous works, multiple vortices ahead of the protuberances were also reported. So because of all the complications involved in the three-dimensional flows, it is very difficult to obtain a correlation which accounts for all the cases. So in the work done by Bharadwaj, a generalized scaling was obtained using shock nose radius as a parameter, which would account for the variations in the shapes. So this is the scaling law obtained in that paper. So we can see that when the shock nose radius is smaller than the boundary layer thickness, this correlation would be invalid. So that brings the objectives for the current presentation. The current study focuses on slender protuberances whose shock nose radius is less than the boundary layer thickness. The one extreme of such case would be where the shock nose radius is 0. That would mean an attached inviscid shock. So the results were validated with the experiments. Further work needs to be done in order to obtain the scaling law for the case of slender protuberances with studying more geometries. The experiments were conducted in gas dynamics lab of IIT Madras. So the figure to the top right shows the pressure ports used for the experiment, and the figure to the bottom right shows the oil flow visualization for one particular case. So the separation length and the pressure measurements were used for the validation. So here in the current study, 4 different geometries were considered. I would be referring the first 2 geometries as sharp elliptical protuberance and blunt elliptical protuberance for the ease of conveying, and the case 3 and 4 as blunt triangular protuberance and sharp triangular protuberance. So for all these cases, the inviscid shock nose radius is less than the boundary layer thickness. And for the last case, the shock is attached, but the inviscid shock is attached, but in the viscous simulations, we find a separation. ANSYS Fluent was used for the computations, and it was performed using HPC facility of IIT Madras. The implicit density-based solver with K-epsilon turbulence model was used, which was also the method used in the previous paper by Bharadwaj. And the boundary conditions replicate the experimental conditions. So this figure shows the typical mesh used. As you can see, the protuberance is extended towards the outlet. This was the method used in the previous paper in order to avoid the divergence issues because of the reverse flow behind the protuberance. The mesh is refined near the interaction region, and the Y plus is maintained less than 1. The mesh was refined multiple times using adaptive meshing. And this plot shows the peak pressure or the plateau pressure ratio versus the size of the mesh. As you can see, after the first refinement, there is not much variation in the peak pressure ratio. The similar method was used for all the cases. Coming to the validation, this figure to the top right shows the percentage error between the experimental and computational pressure values calculated. The color as well as the size of these points indicate the absolute pressure value. So as you can see, except for these 2 points where the absolute pressure is too high, the error on all other points is comparatively lower, like very less than around 6 to 7%. And this orange dashed line is the separation shock. This table has the measurements of separation length obtained from the experiments as well as the computations. Except for the case 3, which is the blunt triangular protuberance, the other 2 cases show a decent match with the experiments. Coming to the results, These two figures show the Mach number contours on the midspan plane for case 2 and case 4, which is where case 2 is the blunt elliptical protuberance and case 4 is the sharp triangular protuberance. Here in case 2, we can see the separation shock interacts with the normal shock portion of the reattachment bow shock. And we can also observe the accelerated zones here. These were also observed in the cases with blunter protuberances in the previous paper, but these regions were found to be supersonic in that paper. But here these regions are subsonic. In case 4, as the inviscid shocks are attached, we don't find the stagnation zone as we observe here. So, and the accelerated zones are also not existent in the separation region here. So these two are the pressure contours on the bottom plane of the test section, and these two are the streamline patterns on the midspan plane. These are for the case 1 and case 2, which is case 1 is the sharp elliptical protuberance and case 2 is a blunt elliptical protuberance. As we can see from case 1 to case 2, as the body becomes blunt, the separation shock also becomes blunt and it also moves further. So this was also observed in the previous paper that the separation shock radius was almost linearly varying with the inviscid shockness radius. So we can also see here the horseshoe vortex is becoming bigger, and also the core of the horseshoe vortex moves farther from the protuberance with as it becomes blunt. So does the pressure minima. So it is also observed that the shock angle in the midspan plane was found to be similar around 30 degrees for all the cases, which was also the case for the protuberances considered in the paper by Bharadwaj, where more blunt protuberances were considered. These two show the pressure contours for case 3 and case 4, which are blunt triangular protuberance and sharp triangular protuberance. Unlike the previous slide, here as the body becomes sharp, the separation shock has become blunt. This might be because of the lesser variation of the inviscid or inviscid shocks in the spanwise direction. And we can observe that the horseshoe vortex almost vanished here. This might be because this can be because of the greater relieving effect here. And here also we found the shock angle to be same as the previous cases, around 30 degrees. These are the pressure distribution plots. So the top plot shows the pressure distribution along the center line for all the cases, along with one case from the Bharadwaj's paper, which is a cylindrical protuberance with diameter and height of 15 mm. So the x-axis is non-dimensionalized by the width of the protuberances, which is indicated by D. As we can see, the peak or plateau pressure here decreases slightly with as the bodies become more slender. But we can see that local minimum pressure for the cases is almost same. This would indicate that the apparent dip in the pressure is decreasing. So this is also in line with the decrease in the size of horseshoe vortices, which have been shown in the previous slides. And here in the last case, where the inviscid shocks are attached, we don't find the pressure dip. This is a pressure plot at a spanwise location of 37.5 mm, which is around 2.5 times the width of the protuberances. This is shown for the cylindrical protuberance with cases 3 and 4, where the width is around 15 mm, so which is same as for this case. So we can see that they show a lot of similarity at this particular spanwise location, especially the case 4 and the cylindrical protuberance. So even though the separation shock interacts with a completely different family of shocks, which is swept shocks, we find a similarity in the pressure distribution at this particular span-wise location. This pressure distribution is such that the 0 marks the point of separation shock, and this and XS indicates the position from that separation shock.
2 minutes more.
This was also reported in paper by Dolling, where it was explained as the flow development being majorly dependent only on the incoming flow characteristics rather than leading edge geometry, unlike in the pressure distribution near to the center. And this plot is plot of separation length versus the inviscid shockness radius. We can see that in this particular region, there is a significant change in the trend. So like this would suggest that more cases need to be considered here in order to capture the variations. And this is for the case where inviscid shock is attached. So in the previous works which are done on swept shock induced boundary layer interactions, the scaling laws were developed for upstream influence, where it was observed that for a range of included angle of the sharp protuberance, the dependence on the included angle of the upstream influence was not very evident. So this would suggest that there is a possibility that the scaling law which would be proposed for the slender protuberances with detached inviscid shock can also be extended with reasonable accuracy to the case with attached shock. So these are the conclusions. So we found significant deviations in the pressure distributions, and also some deviations in the flow ahead of the protuberance. But yet we found some qualitative similarities, like the pressure distribution at the span-wise location of 2.52. And also the variations are like, they were not very sudden, like the horseshoe vortex was diminishing slowly as the bodies were becoming slender, and the dip in the pressure was also following the same trend. So the major difference with the case where the inviscid shock is attached is that the dip in the pressure and the horseshoe vortex were almost non-existent, and the separation shock became more blunt compared to other case where they were linearly increasing with the radius of inviscid shockness radius, which would also increase with the bluntness. So we can say that more cases need to be considered where which have shockness radius value of quite low, and also the dependence on the of the upstream influence on the included angle of sharp protuberances need to be studied further. So we might require a different scaling law for with the inclusion of included angle as one more parameter. But since there are some works which present that the dependence of the included angle is limited, we can possibly extend it to bodies with we can possibly extend the scaling law for the bodies with attached inviscid shock also with reasonable accuracy until a certain limit of included angle. These are the references. Thank you.
Okay, thank you. Time for a few questions. Could you please show me the contour, pressure contour? Why the pressure is negative?
This is gauge pressure.
Now in streamlines at the top, I cannot see any expansion waves. What is your grid solution at that point? Expansion wave, top. You can show that bow shock also. Zoom out and then. Are you able to see some expansion waves from that? Okay, let's thank the speaker, and I thank all our presenters and participants.
I would like to thank the session chair, Professor Lijo from Government Engineering College, Thrissur. I would like to invite Professor M. Ramakrishna to hand over a memento. Professor Lijo. Thank you, everyone. Tomorrow's session will begin at 9 a.m. IST. Thank you all.